mute themselves, or right now I think you've muted everyone, right?
They all are on mute, but if they raise hand, I can put them on unmute.
Right, because when I start, it's very important because once I start presenting, I can't see the screen. I can only see my screen.
Right.
So when somebody wants to answer, either they can, even chatting doesn't work. Only through Zoom it works. That the chat will supersede the window. Otherwise, you have to allow somebody to speak. So just remember that.
Of course,
And
I'll,
one,
I'll do that.
yeah, that's, and yeah, of course, with today with online training programs, still there's a lot of that kind of interaction which you expect from a face-to-face meeting. It's not there. We'll try our best. So as soon as I ask a question, you will see from your screen who is raising his hand, or, and of course, make sure that the same people, after some time, you should ask other people to answer. Because otherwise, this becomes a switch session where just two or three people are awake and the rest of them are on Facebook or whatever. So this is a request to all of you. My name is Ramdas, and today I'm going to take you through a little bit of statistical learning, and this should be as interactive as possible. And I do understand that some of you might have some problems with software. I hope all of you have at least Excel available. And I would also expect all of you to, maybe work your way through some of the problems, maybe not all, and ask questions. And as you know, the golden rule is that I will try my best to clarify issues. If I can't clarify, I will try to confuse. And if I can't confuse, then I'll say we'll take it offline. So beyond a certain point, any questions that you have, in fact, there should be a follow-up. You can send your questions to Ritu or Neha or whoever, if there are questions. And whatever questions I don't answer today, I will answer in a mail to everyone. So Ritu, with your permission, may I start the proceedings? Or you
Yes,
want
sir.
to say a few words about what
I'll
a
I'll
training
just
man I am?
formally welcome you.
Okay, that's
Let
fine.
me just allow
Yes,
me
yes,
to.
please do,
Yeah,
please do.
yeah, sure. Very good morning, everyone. This is Ritu Kandari, and it gives me an immense pleasure to extend to you a very warm welcome on behalf of Indira Gandhi Delhi Technical University for Women, who has clubbed us all for this 1 week online AICT training learning faculty development program on data sciences and its application. I welcome our first speaker of the day, Mr. Ramdas Menon from AICTE Solution. Also welcoming Professor Jasdeep Kaur Dhanova, co-coordinator of this program. We are going to have hands-on session today also. So starting with the first session on the increasing relevance of statistical mathematics in 21st century by Mr. Menon himself. Next session will be on effectiveness of mathematics and natural sciences by Sir himself from 2:30 to 2:30 from 12:30 to 2:30. Sorry. Post lunch we have a session starting at 2:45 on data science using R by Dr. Ashish from Triple IT Gandhi. Now, without further ado, I will take this opportunity to introduce our first speaker of the day, Mr. Ramdas Menon. Mr. Ramdas Menon is a postgraduate in chemical engineering from IIT Madras. Mr. Menon is having 30 years of diverse experience in engineering project management, chemical process engineering, HR, and Six Sigma deployment. He is a certified black belt and reliability engineer from ASQ. Mr. Menon was a Six Sigma faculty at GE, TVS Electronics, and Pfizer. His specialties include Lean Six Sigma, design of experiments, chemical process simulation, and pilot plant studies. Now, I would just like to request all the participants that if you have any question in between the session, you can just raise your hand. We can unmute you in between also. It is not that you have to wait till the end of the session. Also, if you want to ask any question, you can send your question in the chat box or in the Q&A section of your control panel to host and presenter both so that we both can see it. Sending message privately to someone won't help because sir might not be looking at the chat window all the time because he'll be sharing his PPT. So please make sure that you send it to the host and the presenter both. Thank you. Over to you.
Thank you very much. In fact, I just wanted to correct Ritu. Thank you for the introduction. It's not that I will not be seeing my chat window all the time. I will never be seeing the window because I'll be only looking at the screen and also this Excel sheet that we will be working on. So it is very difficult to conduct such a program online, especially without software available. In fact, this program at 2:45 is something which I also run. That is data analysis using R, But for that, in these 2, 3 hours, we not really have enough time to cover even the basics. So,
Right.
but yes, I do not wish to take more time. Let me start with the content straight away.
Yeah.
Yeah. So share.
Now, if you want, so you can put your video off. That is up.
Right. I now let me go to where now stop video.
Yeah.
Right. That's good. I hope all of you can see this. I'm going to start putting it in the slideshow mode. Ritu, if there, I hope you can also see whatever I'm sharing.
Yes,
And
I
if there's
can
any,
see.
yeah, if there's any problem, immediately stop me and
Sure, sure, sir.
so
I'm here
right,
only.
right, right.
No need.
So I'd like to thank both Jasdeep and other members of the Indira Gandhi Delhi Technical University for giving me an opportunity to speak before all of you. As Ritu pointed out, I started life as a chemical engineer, and in fact, many first-rate statisticians of the 20th century, I know at least one who started off as chemists or chemical engineers. So the sheer variety of data that we have to handle today, in fact, there is a new subject called chemometrics, which is basically statistics applied to chemistry and chemical engineering. So the basic statistics as a subject, considered to be very, very dry, very useless. Today, it is the subject to know. Of course, this doesn't mean that it supplants your domain knowledge. All that I tell to everyone is statistics as a subject should supplement your domain knowledge, not supplant. So this is a very brief table of contents, and here we are going to talk about the focus of today's program. We'll talk about a little bit about learning. Then, of course, scatter plots and correlation before regression. Vidu, can you see the whole screen? Because I can see only part of it. I can see some window here. Everybody can read the whole
Yes,
second sentence, right?
it is readable, sir. Yeah.
Right, right. Very
I
good.
think what you're saying on your screen, you can hide that. There must be an option to hide that so that you are also able to see
More
what you're.
options, more options. No, I can't. Let me try. Okay, now it's okay. Now it's okay.
Yeah. Right.
Focus on regression as an integral part. Regression is a very, very wide-ranging term. Various types of regression models. These are some of the things that we will try to cover today. This last part, it's really ambitious. I don't know how much I can cover. Anyway, I have very little material. Probably some of you might not have been exposed to logistic regression. Typically, when people talk about regression, they stop with SLR. So there's a lot more to regression than SLR, simple linear. Multiple linear regression also possibly some of you would have done. Then of course, very few people actually are aware of these things, tests of model adequacy. Like when do you decide which kind of model to take? And then of course, logistic regression, then of course, tree-based CART is basically nothing but classificational regression trees. And this is just a conceptual slide on statistical learning. So it's a vast set of tools. In fact, there are books and books written only on regression. And you have, of course, two kinds of regression, if I might say. So one is the original, the so-called classical regression, using least squares and others. Then, of course, you have these tree-based methods, which I will talk about later. They have their advantages and disadvantages. And of course, statistical learning is of two types. One is, I'm not sure how many of you are familiar with this phrase, supervised learning. Supervised learning, most of regression as we understand is supervised learning. Why supervised? Because the idea here is to predict an output given several inputs, right? So an example could be, to predict the reaction yield. If you know, for example, what is the monomer, what is the reactant flow rate, what kind of reactants, what kind of catalyst you are using, what temperature, etc., etc. One could be that. Another could be, for example, a lot of these kinds of regression and experimental design work has been done in the automotive industry. So, for example, you might be interested in building a regression model on what factors actually affect the NOx emissions of an vehicle. So, basically, collect data and try to build a model. And the word operative word here is supervised. Supervised meaning the goodness of our model is supervised by the output, in the sense that very briefly, let me tell you. So what people do is they generally have one set of data called training data. That's the data that has been collected. Use the data to build a model and then use that model to predict. So it's supervised. That's why it's called supervised. So predict wages given education, age, and experience, or predict yield of reaction if you're given the flow rate, catalyst flow, etc. So this is what most of regression is all about. Then, of course, there is another type of regression, logistic regression. I'll give you a very um, major difference between this kind. For example, wages. Wages is what is called a continuous variable. Your wage can be 100, it can be 101, 2000. In other words, you can even break it down. A continuous variable is a variable which you can break down into smaller and smaller increments without loss of meaning. So it is meaningful to say that the reaction yield is 40%. It is also meaningful to say that the reaction yield is 40.2%. So if you can keep subdividing it, then it's continuous variable. On the other hand, there is a very large class of problems where the output is not of any continuous type. It is of a yes, no type, pass, fail. So for instance, there are actually several treatises written on logistic regression. In fact, medicine is one subject which uses a humongous amount of logistic regression. For example, predicting diabetes, for example, given certain aspects or attributes about a person, what is the chance that he is a diabetic? So for instance, so how people generally go about these things is, again, you collect data, and that is called training data. Training data simply means whatever data you collect to build a model. So you might, for instance, want to collect information on that person's age. Obviously, the older you are, higher the probability of getting diabetes. Then, of course, your weight. Then, of course, the kind of diet that you eat. Again, that could be what is called a categorical variable. Categorical variable, I would assume that you know what categorical variable simply means, a variable where you have categories. For example, I can say I am having carbohydrate rich diet, I am having protein rich diet, I am having keto diet. It is just very set of categories. It doesn't really mean which is better or which is worse, just some categories. So once you know what kind of diet he has, then again, what kind of job is it? For example, again, that's a categorical variable. Is it very sedentary? Like, is it somebody who goes to office and sits at his desk all day? Or is it semi-sedentary? For example, somebody like a teacher. A teacher, for example, stands, I'm not talking of the pandemic days, I'm talking of the pre-pandemic days. So a teacher would typically be standing in a classroom, moving around, sitting down, and then after that, she probably goes to her room and probably sits. So it is not completely sedentary, it is semi-sedentary. Then, of course, on the other hand, you have a salesman. A salesman, for example, would be somebody who's always on his feet. I mean, he should be on his feet. So therefore, one of the variables could be kind of job. Then, of course, your habits, consumption of alcohol. Again, you could have three categories: somebody who is a casual drinker, or somebody who's a teetotaler, somebody who's a casual drinker, somebody who drinks regularly, and somebody who's a drunkard. So maybe there are four categories. So if you know various attributes about a particular person, you first of all collect data with all these attributes, and then you have the final decision. The response here is not wages or reaction. It is something called diabetic yes or diabetic no. So it's a yes, no answer. Once you have this kind of training data, you can actually build a logistic regression model. And a logistic regression model, again, is just, these are all fancy words which statisticians use to bamboozle people. It's just an equation. It's an equation where on the left hand side it's a probability. It's not a continuous number, it's a probability. And on the right hand side, you'll have basically all the terms, some constant plus some multiplying factor into first variable, could be age, plus another factor into weight, plus another factor into race, plus another. There could be so many factors. In fact, humongous amount of studies have been done in medicine using logistic regression models. The logistic regression model again is a kind of supervised learning. Why? Because ultimately the goodness of your model, how do you actually check the goodness of your model? Anybody would like to come back here, because I've given a bhashan now non-stop for 10 minutes. How would you, for example, and don't give me any statistical answers, give me some common sense. How would you check if your model is good, bad, or ugly? Anyone? I think people have already fallen asleep. Yeah, okay. Relevance, I can, yeah, this is a good thing, Ritu. I can see somebody, Vikas has answered relevance in terms of result. Yeah, that's a very formal sounding answer. Can you give something which is less formal, something which is even.
Subro sir has also written something with variances. So I would like to request the participants to please send it to the host and the presenter
Yeah,
both,
then I
so
can.
that sir also see. Yeah.
Correct, correct. Anyway, so there are two good answers. So basically, simple thing is how good your prediction is and how well it matches. So let's assume that you build this logistic regression. In fact, I was planning to do a session only on logistic regression because it is a topic which is not covered at all. So for instance, let's assume that you have built some big fat equation with some 10 terms, and you are now ready to test it. So how are you going to test it? You take some random guys, somebody whom you don't know. Okay, so what's your age? So much. What's your weight? So much. What's your race? To actually, it has been found from statistical studies that race, Asians are more predisposed to diabetes than others. Then, for example, what kind of diet do you have? What kind of job do you have, etc., etc. That could be, are you a smoker, casual, not? Are you a drink? Do you drink? There could be several 8 or 9 questions, and based on that you put it in your equation, and boom, it gives you a probability, high probability or low probability, and then you say, okay, this guy is a diabetic. So the more number of correct answers that you give, the better your model is. So that's why it's called supervised, because the goodness of your model is supervised by the output. Supervised by the output. On the other hand, this is more tricky. The unsupervised learning pattern is more tricky. We are not going to cover much of it here, but I just wanted to give you an idea of what unsupervised learning is. For example, the idea here is to understand relationships, structures, and patterns in the data without any supervisory input. So there is no answer like wage is so much, or reaction yield is so much, or for example, the nitrogen oxide emission is so much. Typically, when you're doing regression in automotive industry, you actually are looking at, in fact, the automotive industry, all the industries in general, they don't have too much of a use for logistic regression. There, it's a question of numbers. Can you predict, for example, can you predict what the reaction yield is going to be like? Typically, when you're running very large chemical reactors, you're interested in understanding the yield. So you ask somebody to build a transfer function. Okay, can you build a transfer function? In fact, all of these have extremely high industrial use. In fact, one of the most important statisticians, in fact, in my opinion, the second most important statistician in the 20th century. Would anybody like to, has anybody heard the name of George Box? Anyone? Yes, no? Maybe one of you can say yes. Even if it's not yes, you can always say yes, right? Because there's no way I can cross check. Anybody has heard of George Box? And maybe you could, if you've heard of Box, maybe talk about no, sir. Okay, somebody said no, sir. Very honest, Subro. Thank you very much. Anybody wants to say yes? Because if you say yes, the next question is going to be name one contribution. And don't say box plot for Christ's sake. Okay, Sunita is one more person who said no. So there are two no. That's fine. So do look up George Box on the Wikipedia. I would say he's probably the the second most important statistician. Anybody would like to take a guess on who is probably the most important statistician of the 20th century? Again, this is relative, because you could have two types of answers. Maybe one of you can give one or two names. In fact, this particular name, Pearson, that's a very good answer. Pearson is a very good answer. Of course, that's not the name which I had in mind, but I'm happy to hear happy to see some people at least responding. Pearson of the Pearson correlation and the chi-square test. It's called Pearson. Anyone wants to give any name? Spearman. Spearman, very good. Spearman is the Spearman also has a has a correlation coefficient, which is meant for ranked data. John Napier. Okay, the Napier guy, John Napier. I'm not really sure is a statistician. Napier, in case many people have not heard, John Napier was the guy who invented the logarithm scale. Okay, somebody said Bayes, but Bayes, yeah, you're right, logarithm. Bayes actually is not 20th century. Bayes is 18th century, and Bayes is used. Bayes is very famous for the Bayes theorem. But you're not coming up with the name. It begins with F. Maybe I'll wait for 20 seconds more. Any other statistician you want to name, or you can desperately look up Wikipedia or maybe Google. I'm sure all of you have your computers open. Anybody heard of Ronald Fisher? Ronald Fisher? Ronald Fisher, by common consent, of course, just for Fisher index, yes. No. This Fisher is not that Fisher. The Fisher you have written, Fisher, is a Fisher spelled Fischer. That is not Ronald Fisher. This is some other Fisher whom you've named. Ronald Fisher was actually a polymath. Polymath meaning a person who was skilled in many areas. He was actually primarily an evolutionary biologist. C.R. Rao is a very nice answer. C.R. Rao is a very good answer. C.R. Rao actually, for your information, did his PhD under Fisher. And C.R. Rao's methods, in fact, his matrices that he developed were actually used by Taguchi for his Taguchi designs. But yes, C.R. Rao is also a very great statistician, still alive. He just completed 100 years last year, and he's still alive. More about that later. Coming back to Fisher. So Fisher was this person. A lot of statistical tools. In fact, everybody I'm sure has heard of the ANOVA, right? The analysis of variance, which is one of the, I would say, the most important tool in statistical analysis. The ANOVA was created by Ronald Fisher. And then, for example, the concept of experimental designs, your Latin squares, Greco-Latin squares, then factorial designs. All of these were created by Fisher. So anyway, so we were talking about box. In fact, we went to Friedman. Friedman, yes, Friedman is the guy. Yes, F test, you're right. Caesar and F test, you're right. And somebody mentioned Friedman. Friedman is a great guy, but I would not say he's the most important. Friedman is the person who, if I'm not mistaken, came up with the cart, the concept of the cart. Friedman, Olsen, and some two other guys. I forget their names. Friedman, Olsen, Stone, third guy's name I forget. They came up with the concept of the cart. Cart being the classification and regression trees. But the reason why I went to Fisher is we went to Box. I said Box is the second most important statistician. And why I mentioned Box is Box actually started off life as a chemist, And this was during World War II. And World War II, there was a lot of experiments being done in the United Kingdom on using poisons in warfare because the other side, Germany and Italy were also using a lot of poisonous gases. The English were also developing poisons, and there was a necessity for a humongous amount of statistical testing. And that is where Bock started utilizing started building up on certain ideas. And then he joined the ICI. I don't know if you've heard of a company called ICI, the famous paint company. And the paradigm shift that Box brought about was before that, the guys like some of the guys that you mentioned, for example, a guy like Pearson or even Neyman, they were all only into theory, nothing else, only theory. Box was the guy who made a movement from theory to practice. He said, theory is all fine. I mean, theory is good. But if it can't solve industrial problems, then that theory is not of any great use. So as you know, every chemical plant, it could be say a 1 crore plant or it could be a 10,000 crore plant. All owners are interested in only one thing, and that is increased productivity. If you have increased productivity, you have increased revenue, increased profits, and so on and so forth. So at ICI, Box actually developed some very, very powerful, statistical quality control. Yes, but that's Box is not so famous in statistical quality control. I was talking about Box, but thank you for the number. Yeah, very good. Sriharan has mentioned Box Benken designs. Actually, Box Benken designs are not very popular. There is something called the Box Wilson designs. The Box Wilson designs are also called central composite designs, CCDs. And the CCD is one of the great, shall we say, applications of statistical theory to problem solving. Box actually developed the CCD in collaboration with a guy called Wilson, and they were actually used to improve the productivity of the existing reactors in ICI in the UK. So so here again, all the kind of work that Box and co-workers did is all basically supervised learning. So today we are looking at machine learning and artificial intelligence and much higher concepts. So the you could say that even up to the 80s, a lot of the statistical modeling that people did was of this type. Can you build a model which will predict something? Can you build a model, say, which can predict the sales of a particular item, given for example, the season, for example, the kind of population that you have, the kind of demographics that you have? It's possible to build all kinds of models, but all of them basically are supervised learning in the sense that there is a certain output. ARIMA. Okay, Saurabh, that's a good answer. ARIMA actually, I do not know if people know what it stands for. It stands for Auto-Regressive Integrated Moving Average. That's what ARIMA stands for. And that is used in actually the time series. The time series prediction actually, but time series is a very specific case where time is the only variable. When you're talking about general regression, yes, time series also uses regression. In fact, that's why it's called auto-regressive. But more about that later. I will get distracted. But thank you very much for all the pop-ups that are coming on the screen. At least people are engaged. A lot of good things I have seen today. For example, people are mentioning all these terms, ARIMA. I'm very surprised to. In fact, I also run a program on time series where I cover ARIMA and your EWMA, exponentially weighted moving average, all those kinds of models we cover. But coming back to now this slide, unsupervised learning is where things begin to get a little bit difficult. For example, there is no output. The question could be which kind of customers exhibit similar purchasing behavior, or for example, which type of gene expression data for cancer treatment are similar, and etc. In fact, here I would like to give you an example of unsupervised learning. It's a slightly politically incorrect example, but I would like permission, especially now considering that I am addressing the Indira Gandhi University for Women. But the thing is, this is a very famous case study which I have seen in two textbooks, not textbooks actually, more of reference books. It's by Victor Mayer Schonberger. It's called Big Data. It's a classic, and probably you can see that also. So unsupervised, the best kind of example which I wanted to give about unsupervised learning is you might have heard of a retail chain called Target. Now, everybody knows only Walmart, but Target is also a very, very big retail chain in the United States. And the story goes, again, it's not a story, I've seen it in Victor Mayer Schonberger's book. So the story goes like this, that before the proliferation of email spamming, email has existed for quite some time. I built my Yahoo account way back in '98, but the email marketing has caught on, probably over the last 10-15 years. Before that, what people would do was, you go to a supermarket and you give your name and address, and they will send mailers. In fact, the word mailer comes from there. They would send you some ready-made printed information about the products that they have. They would just mail it, and you will find that your letterbox, when you open it, the useful letter might be only one. maybe a 4 or 5 bills from your utility companies, and the bulk of it would be these unsolicited mailers from these retailers. So it so happened that there was this gentleman, a middle-aged gentleman, his wife, and he had a teenage daughter. And he got a mailer when he opened his mailbox for babies products, for newborn babies. And he was very offended because his daughter was not married. And what the hell do you mean by sending this kind of um, advertisement? Are you implying that there are small children in the house when we don't have? And this fellow actually went to the nearest Target store and he picked up a fight with the manager. And the manager profusely apologized. He said, no, no, I'm really sorry. I just don't know how it's happened. Anyway, he profusely apologized. He gave him some, I think, some gift or something and said, I'm not going to say, do this again. My sincere apologies. Please come and avail of a discount, etc. Something, something, and sent him off. Now, what happened was a month later, this guy comes back. This angry father comes back and he apologizes profusely to the manager. He said that, there have been some goings on in my house while I was not there. It appears that my child is going to deliver a baby. Now the question is, how did Target know? How did Target know? Again, it's a classic example of, so algorithms were built. So this is where, this purchasing behavior. This is actually extremely important for retail people. So what they do is they again try to build again, this is some kind of a not exactly a logistic regression, but again data, basically it's called data mining. So a person, if he buys product A, B and C today, let's suppose he buys today, and you also find that the same person is buying products E, F and G maybe a month or two later, and then he buys say J, K and L the third month. If there are three patterns, what people do is you can automatically predict the fourth and fifth member. So that is what Target had done. They found there was a certain pattern in the purchases made by this girl, and they said that if this is the pattern which is made by a particular person. I hope nobody has tried to call me because there was some kind of a call here. So I keep my phone open because in case somebody wants to get into the program, sometimes they call me. So no one has called me, I hope. Okay, right. Then what I will do is I will now vibrate. So this kind of unsupervised learning is also very, very important. And that's the message I wanted to come across, wanted to give you. In fact, what I will do is during the interval that we have from 12 to 12:30, I will probably go and fish out that book and show it to you so that you are convinced, or you could also check with the linear regression. Basically is
Yeah, there may be some network issues. Please be patient. We'll just connect with soon.
Can you hear me?
Yes, sir. Now you're audible.
Yeah, the thing is, there was an internet problem at my end. It's been resolved, hopefully, but the share button has gone.
Okay, okay. I'll just
Yeah, please, please. Thank you
clean
very
your room.
much. Thank you very much.
So you may try now. Are you there, sir? Can you hear me?
Yeah, sorry about it. This was internet playing up at my end. I hope all of you are here.
Yes, sir. We all are here. We were just waiting for you to
Yeah,
join.
it's always happened. This is a classic example of Murphy's
Yeah.
Law. So you can once again give me the share permission. I hope it doesn't go this time.
Sure, sure.
Yeah, thank you very much, and I apologize for.
Not your fault. Definitely not your fault, sir. That's just a technical glitch,
Yes,
and it
yes,
happens every time we conduct such
yes.
FTPs online. They're saying they're being so kind that they're waiting and listening patiently. Yeah,
Right.
now your slides are visible, sir. Yeah.
Okay. Thank you very much. I sincerely hope it. Okay, so good. So what I wanted was I'd ask this question. I don't know if people had the time to think about it. So the first is one, two, three, four, all of these are supervised. So only the last one, identify risk factors. In fact, today's statistics is going hand in hand with medicine. There's a humongous amount of statistical work in the medical industry. By medical, I mean medicine, your medical imaging, all kinds of stuff. We'll start with correlation. Correlation is a much maligned technique. So we try to see if there exists any relationship between two or more sets of data. That's all that we try to see. We are also interested in how strong the relationship. And somebody I think mentioned Pearson, Carl Pearson. This correlation coefficient is due to Sir Carl Pearson. And then, of course, you have a positive correlation, whereas one value increases, the other also increases. And then you have negative correlation, where when one increases, the other decreases. One, of course, one is you in real life, you will never find +1 and -1, but you will find numbers very close to them. A value of 0 indicates no. 0 means it's not exactly 0. Some number which is very close to 0 on either side, positive or negative, means no correlation. And this, of course, is the definition of correlation. This is the Pearson product moment correlation coefficient. I don't know if you've understood the significance of this equation here. If you just have a collection of n data points, that is x1, y1, x2, y2, x3, y3, and so on, up to xn, yn, then by just knowing these data points, by just calculating this, and today, of course, in Excel, you can do it very easily. And there's just one problem with it. It does assume some kind of normality, and that is why the Spearman correlation coefficient is used, where this normally distributed assumption may not hold true. Anybody would like to, what is this? No, this is just a product moment correlation. Don't break your head too much about this. The general definition of moment here, in fact, just let me see. Somebody's persistently trying to call me. Hello? Ah. ஆமாம் ஆக்சுவலி ஆமாம் இப்போ நான் ஒரு மீட்டிங்கில் இருக்கேன் ஒரு 3 o'clock அப்புறம் கூப்பிட்டா போதும் ஆ இல்லை நான் இப்போ ப்ரோக்ராமில் இருக்கேன் ப்ரோக்ராம் இந்த மிடில் ஆஃப் ப்ரோக்ராம் அப்புறமா கூப்பிட்டு அப்புறம் So somebody asked a question on moment. Actually, moment, I don't want to get into that right now. Basically, if you have these x minus x bar, if the first moment is when you raise it to the power 1 and sigma of that is 0. The second moment is variance. The third is skewness and the fourth is kurtosis. But this is just called product moment correlation coefficient. You're looking at both x and y, and this it's very easily implementable, and this will straight away give you an idea of the strength of the relationship. I do not know how many of you are familiar with this Correl function. Just can I see some yeses or nos? How many of us have heard of this Correl function in Excel? Correlation function? Anyone? Okay, somebody has asked a question. Can I see the questions? What is the need to understand? Somebody had asked that question. I couldn't read it quickly enough.
It says, what is the need to understand variance when standard deviation is already there?
No. See, the standard deviation is a derived concept. The basic concept is variance. variance is nothing but, I may be going off topic in the sense that that is more fundamental. So if you have a set of data, say, forget wise, just have a set of say 10 data points, and you can calculate the mean of that. And then from every data point, you subtract the mean. And if you sum up those differences, it becomes zero. But if you sum up the squares, that becomes what is called the variance. It's also called the total sum of squares. So total sum of squares, and if you divide by n minus 1, that's called the variance. And the variance is actually a more fundamental quantity than the standard deviation. In fact, when we look at, when we study topics like measurement error, measurement repeatability and reproducibility, we always look at the squared components. We always look at the variance, not the standard deviations. But yes, for choral function, I saw a couple of yeses, so I would assume that people know what the choral function is. And yes, that's very good. Shubhra has said yes. So there are a few points to be borne in mind before calculating the correlation coefficient. And that is here, this is a point which many of us miss out. And I'll just take a minute here. The first thing that you should actually do is to draw a scatter plot. So you can see even with this kind of data, the correlation coefficient has some meaning. Correlation, or even, for example, your regression. For all these, in fact, if you see C, D, and E, where the answer is given as no, meaning basically the correlation coefficient doesn't really mean anything here in these C, D, and E. But if you put the data in Excel, it will always return some kind of a correlation coefficient. It's like, the question of fitting a line. In fact, regression is all about fitting. At the simplest level, regression is all about fitting a straight line. Now, what you need to understand is, if you look at, for example, D, I hope people can see my cursor moving around D. Ritu, can you see this cursor moving around this slide called D?
Yes, we
Yeah,
can
good.
see that.
I hope people can see that. You see, technically or theoretically speaking, it is possible to fit a straight line here. It is possible to fit a straight line here. For example, if you fit a straight line here, it will just pass through this point. And if you fit a straight line here, it will fit something like this. So any regression routine, or for example, any correlation, this kind of formula that you use, it will always return some answers, but you always must look at the picture. A straight line or a correlation actually is meaningful only when the data itself is more or less straight. Of course, there are tests of model adequacy that we will check later, but correlation will be meaningless for the data shown in C, D, and E. So that's why it's very, very important that we always do a scatter plot. So this is called this R, and this R is going to be very useful because the square of this quantity called R squared is going to be very important in regression analysis. But the basic quantity is R. And of course, this everybody knows it by now. In fact, this particular statement was first said by a very, very eminent English statistician by name Maurice Kendall. I do not know if you are familiar with the Kendall's rank correlation coefficient. It was the Kendall who said that correlation does not imply causation. And there's a very interesting story about this, which I'll probably tell you in a couple of minutes. Some thoughts here. In fact, this is very, very important. The sample size is actually a very, very powerful weapon, and in the wrong hands, it can actually be deadly, because if you collect enough data, then even a very weak correlation can be shown to be statistically significant. And in contrast, small samples will yield a significant outcome if the correlation is very strong. If two variables are actually really related, it will show you a significant outcome, in the sense that the correlation coefficient will be high and the p-value will be low. But when you have a weak correlation, I mean something which is intrinsically weak, but if you collect enough data points, you can actually convert black into white or white into black. So that's something which you need to bear in mind. And this is, of course, a very nice picture here you can see. This is about 0.6, roughly it will be 0.6, and this will be 0.9. So this is perfectly positive. This is more or less perfectly negative, and this is a slight spread over it. And then, of course, these two are more or less zero. I mean, you'll not get virtually no correlation. And I'm going to ask you a question here. Can you name, and instead of asking this question, I'm going to give you some variables, and maybe you people can also give your own examples. So I'm going to give you some sets of variables here, and you need to tell me if it's going to be correlated or not. So, and after this, maybe we can make it more participative. So height and weight of individuals, the correlation will be very high, medium, low, or zero. Yes, no. Pavitra, thank you for the answer. Yes, but I want to give me what. How much do you think? Will the height and weight correlation be closer to 0.8, 0.9, or very nice answer, Alka Vinayak? Unfortunately, I don't know enough to be able to say that about Asian. 0.7 is a good number. High? No, no, no. It will not be very high. It will at best, I don't know about this Asian part, 0.65 somebody said. In fact, I have enough data on this also. You can do it yourselves. I make it a point that whenever I go for any program, I always take down the names, heights, weights, age, and experience of the participants. So height and weight correlation, at most 0.4, 0.5. You will not get more than that. This is what I've seen. Person's intelligence and his height. How much do you think the correlation will be? Will it be close to -1? Will it be close to 0? Or will it be close to +1? No relation. No, I want a number. Himani says 0. 0. Okay, that's very nice. So 3 people have said 0. It'll be very close to 0. Okay. And no, no, no. It won't be close to -1. 0.2 is an inspired guess. No, it will not be as high as 0.2. It will be very close to 0. Maybe 0.01, 0.02. A student scores in mathematics and physics. High. Okay. High is a good enough answer. 0.6. Okay. Yeah, it'll be around 0.7, 0.8. Company's EPS and share price. EPS, by the way, stands for earnings per share. It will be high. Yes, very good, Shubro. I think Shubro is a high energy participant, right? A lot of answers. Thank you. Thank you very much. Age of an employee and her experience. Age of an employee and her experience. Okay, I'm not going to comment on this much because there is an example coming up, and then maybe you can. Time required to fill a position and the level of the position. This is an HR example. For a brief while, I was also heading HR in one of the TVS companies. High. Okay. Okay, the number may not be very significant here. High, yes, definitely high. Because if you're going to say level, if you're going to give senior position levels as higher numbers, then the higher the number, the more the time required to fill the. It is very easy to get assistant engineers. You know, if you just step out of the house, you'll be able to get some 3,000 people, and it's not a difficult thing. But if you're going to look for a VP of sales, or if you're going to look for a director of marketing, then the time, I mean, you'll probably have to start negotiation, and negotiation itself will take a lot of time. So definitely, yes, time required to fill a position and the level of the position, definitely there's a very high correlation. Then number of hours studied and performance in the examination. Is it going to be low, medium, or high? Ramesh, thank you very much. Shubro says medium. Ritu's come up with a number also. Very good. Can't predict. Okay, that's Dolly. Thank you. I'm seeing some new names now. Dolly, Bharati. I'm very happy to see new names. Most of the time, it's your old names. So good. I'm happy to see participation. Number of hours studied and performance in examination. Yes, I would like to think it's high, but it's not really high. I would say it's medium. Medium, because there are several. So this is where the concept of multiple regressors will come in. It's not only time. It will be several other factors which will actually help you to predict the examination, the performance in examination. Okay, so now here, this is a very small example which probably, if you have your Excel sheet open, I don't know if you have your Excel sheets open with you today morning. In fact, yesterday evening I sent it out. The VP R&D of a large company feels that more spending on R&D actually translates into higher profits and has collected data over the last 6 years. What do you think? So, what do you think should be the first step? You can chat, you can use the chat window. Not really. Okay. So Shubhro, your answer is good. I mean, not really in the sense that, I'm going to come back to this. As I said, please remind me if in case I forget to tell you of the story, another very, very important story regarding Fisher. And again, I use the word story in a very formal sense. It's an actual event that happened. Somebody, Shubhro, said not really. Um, okay, but somebody is giving you data. See, this is where you have the flip side, the plus and minus point of data. Now, if how many of you actually have that Excel sheet open? Quick question. Just say yes if you have it open and no if you don't. I just want to see a few answers. Bharati says yes. And Sriharan says yes. Okay, that's 2 yeses. Shubhro says yes. That's 3. That's very good. I'm happy. At least 3 out of 90. Vikas, yes. Okay, I would assume that all of you have. So one thing which you could do quickly is, you can either participate in the discussion. I find that it's always better for people to actually do some work. So you can see here, I'd like you people parallelly, you can go to Excel. I'm sure you know the menu option today. In fact, Excel has improved vastly from the time I started using it. I have just come to the ordinary mode here. You can actually go to this is the actual sheet which I've given you. I've only unfortunately sent you only the first sheet. So profit versus R&D spend is here. And here, of course, I've done some calculations here. And what you can just straight away do is you can just select, I'm sure all of you know it. I'm just showing it once. You just select the data. I hope all of you are familiar with this. I'll just take 20 seconds to show it to you. R&D, you select the 2 columns and then you go to insert. You go to insert. It's as usual, it's taking a long time. Okay, insert, and then you can see recommended charts. I have Excel 2016 with me. I don't know if the same thing works in the previous editions. You go to recommended charts and click, and you just click, and I sincerely hope the damn thing doesn't hang. It just please share the Excel sheet again. Here, I think Ritu, you will have to help. If you have not sent it to her, maybe you can send it again because I don't know your email IDs. I'm just opening it here. So Alka was the person who asked if you have the sheet open.
I'm sharing over. Yeah, I'm sharing over the WhatsApp group.
Right, very good. WhatsApp, of course, I'm a bit old-fashioned. It's always better to share by email so that people can actually, because today everybody wants to work on mobile, so that's fine. So you just click the recommended charts. Scatter is recommended, so you just click that and say click OK, and you'll find that automatically the chart is stored up. And for those of you who are not very familiar with this, you can go to plus here, and you can go to access titles, and it'll immediately show up both, and you can go here and you can write whatever you want. You can put here, this looks like your R&D spend, and this looks like your access, this looks like profit. And you can see, in fact, you don't need to be an Einstein to figure out there's a slight non-linearity here. It is definitely non-linear. And then of course you can go and you can change the color. I mean, I'm not really getting into all these things. If you like dark red, you can put whatever colors you like, but I'm not getting into the coloring bit now. I'm just going to look at, you can see here, Alka, I hope you can see the screen. You can use the Corel function. I've used the Corel function here. You can see Corel. I've just selected the 2 arrays and put enter. You will get 0.909. And you can also use the Pearson's formula here. Straight away, you will get same answers. Coming to the statistical part, now you have 0.91. 0.91 actually is a pretty decent number. 0.91 is very high number, and definitely the R&D head can say that, look, the more money you spend on R&D, the more, shall we say, more innovation we can do. We can come up with newer products. In fact, right now, my small little firm, we are about 3, 4 people. We are actually the process excellence consultants to a very large company called Pidilite. Pidilite, as you know, makes Fevicol, one of the world's most famous brands. So, but the thing is, the good thing about Pidilite is, they are not content to sit with just one product. So they're constantly innovating. So innovation, R&D, all these things go hand in hand. So I think it was Subro who said no relationship. Actually, a company which invests time and money in innovation, and again, innovation is a very, very wide term. It includes R&D, it includes out of the box thing. A lot of R&D, actually, contrary to what you might think, is very boring and plain stuff. But yes, just because there is a correlation, it doesn't mean that the R&D spend is causing the profit. Yes, but it only tells you that there is some relationship and the numbers also prove it. That's all it shows. And coming back to the story which I was telling you, in fact, I've even asked this to many doctors. Many doctors also were not able to uh, remember, or in fact, they didn't know this answer to this question. But let me just ask this question. Are all of you familiar with a study done by two medical statisticians by name Doll and Hill? Even doctors I know couldn't answer the question, but just let me answer. Doll and Hill study in the 1950s. What do you think it was? No, sir. Okay, Subra, I really like your speed. You are the first off the mark. So Doll and Hill, though you could actually cross-check it on Google. Doll and Hill were the people who first came up with that landmark study which correlated smoking and lung cancer. It was a truly landmark study, and it earned both of them fellowships of the Royal Society. It was very famous. And I'll tell you the flip side to the story. Both Doll and Hill were students of Fisher, and Fisher was a lifelong smoker. You could never see him without his pipe. And Fisher said, just because it is correlated doesn't mean that one causes the other. And people were on sticky ground because, yes, there are a lot of fraudulent correlations going on. So what statisticians say is you can use a statistical tool. In fact, correlation is one of the correlation and regression and one of the most widely misused tools. If you select data, you can always prove correlation. You can get very high numbers also, but the actual proof must come from physics, chemistry, or biology. The statistics can only show you the way. It can only suggest certain things. In fact, the Doll and Hill study was subsequently supplemented with a lot of proper, very rigorous medical studies, and then only smoking became such a bad name. In fact, I don't know if you are familiar with the magazines, the American magazines of the 1950s and 60s. Many of them would actually endorse smoking. You would find doctors endorsing smoking. Hey, it's Christmas time, and let me send this packet of cigarettes to all my friends. So it took a long time for people to change their attitudes. And Doll and Hill study was a classic which actually helped people to change their minds. So much for statistics in medicine. So this is what the thing looks like, and correlation is 0.909. I mean, what's your opinion? I've just left it open-ended. Opinion is that yes, it does not say that R&D spend is causing the profits, but there could be some link which can be investigated. So if I was in the CEO's position, I would have probably looked at, asked the R&D fellow, okay, what are the kind of business problems that you have solved over the last couple of years? What are the kind of new products that you have made, that you have released? What are the kinds of new products that you have in the pipeline? All these questions, if they can be answered satisfactorily, yes. Okay, now this is again very interesting. This is taken from one of the G factories, and I want you to take a strong look at the data before you can. The clicking the button in Excel is very easy, it doesn't take much talent. So HR has collected some data with the intention to determine whether there's correlation between the age of the employees and the corresponding time working for the company. Okay, so now this is what the data looks like. In fact, this is the correlation chart here, and the data I think is given here. In fact, data I have not given here. You can see it in the Excel sheet here. The data is here. I hope all of you can see this. Let me increase the size of this slightly. I hope all of you can see age and experience. So this is a random sample, more on sampling later. I don't want to get distracted. I already got distracted with unsupervised learning. There's a lot of material to cover. So age. So a random sample was taken. So the first guy or gal they met, what's your age? What's your experience in the company? Age, experience, age, experience. So like that, you have, I think, some 43 data points. For 43 data points, so let me just go and so if you do the same thing, you can actually draw this scatter plot here, and the coefficient of correlation is 0.914. And in fact, for somebody had asked, right? I am not actually in this Excel sheet, correlation regression sheet. There are a lot of cases where you have. There's one more case which I remember. You can see here one exercise for all of you could be, put all the heights together. These are all the various companies I've gone to. I've just given a selection. If you just put everything into one set, that is just two columns, weight and height, you try to see what the correlation is. This is another company where I went, I think way back, 10 years ago. So you'll find a lot of people, a lot of HR personnel actually, they like to come up with this kind of data, that is age and experience. Now, my question to you is non-statistical in nature. What do you think is the HR head's agenda? Correlation is very high, which means that as the employee age increases, the service in the company also increases. This is what it means. But what do you think is the agenda of the HR manager? Anyone? Maybe gratuity, okay. Okay, that's a good answer. Anyone? Gratuity, okay, no. Anyone else? Anyone else wants? Because this is a non-statistical question, but at the same time, I want people to start thinking. Anyone? Ritu, to see their loyalty and satisfaction. Okay, that is slightly warm. Loyalty and satisfaction. There is a particular word that people use. Yeah, loyalty. So can you expand on that? Anyone? The person who said loyalty and satisfaction. Sense of belongingness. Oh, very nice, Subro. Thank you very much. In other words, you are saying that the HR manager wants to show. Anybody would like to agree with Subro, disagree with Subro? Subro seems to be supervising my learning here because he's the only guy who's first off the mark. I think there are, how many people are there right now? 90 people. Ritu, can you check from your screen?
Right. Yeah,
90.
the 90.
90. And so far, I think about 10 people's names are Alka, then there is Abhishek, then Bharati. Um, I have not seen more than 8 or 10 different names. Okay, so what I'm trying to say here is, I'll try to give you an answer. This person is trying to show a positive correlation, and it's actually there. The correlation is about 0.914, which is a very good number. So what the HR manager is trying to say here is that this company is able to retain talent, because if there was no correlation, then what would happen is if you were to go and talk to a random employee, whether he is 50 years old or whether he is 25 years old, his average experience in the company would be the same. If it's a revolving door company meaning people, it's the ayaram gayaram, people come from one end and go out from the other end. So the average duration of stay in this kind of a company, a revolving door company, would be around 2 or 3 years. Somebody gets in when you are 45, you go out when you are 48. Somebody gets in when they are 24, they go out when they are 27. I mean, the length of stay is independent of that person's age. On the other hand, if the company is able to retain people, then somebody joins at a young age. Employee retention, you're right, Sriharan. Employee joins at a young age. If the company is very good, it gives him a decent salary, it treats him well, it gives him learning opportunities, challenging opportunities. So chances are people will stay. So the older an employee is, the more he would have served at the company. So this was an attempt, but of course, in reality, life is much more complex. In fact, there was another company where I went. In fact, that's the data which I've shown there. Um, I do not want to sound very patrician or otherwise, but I found that the average quality of the employees was pathetic, actually. Most of them pathetic guys. Pathetic in the sense, again, I do not wish to appear, aristocratic or anything of the sort. It's just that many of them had started and they were at the same level all their lives. Many of the people did not know why they were coming to office. So, so therefore, employee retention could also happen because they were unable to find jobs elsewhere. So there could be many, many factors as to why people stay. It is not necessary that the company itself is an attractor of talent. It could be that these guys just can't find a job anywhere and the company anyways couldn't care less, and so people are staying. So anyway, so that becomes a discussion in HR rather than stats. So this is the point about correlation and causation. And here again, you can see, for example, by the way, this was actually published by somebody. The ice cream sales and the number of shark attacks. The ice cream sales and the number of people attacked by sharks. It was found that there's a positive correlation, and I think this was also published. Then again, marijuana with cancer pain. So, one of the common explanations is both your X and Y, which you're trying to relate, could be responding to changes in some other variable. So actually this data, this ice cream sales and number of shark attacks, was actually taken from a town on the seaside. And naturally what happened was, when the temperatures increase, more and more people go into the sea and more ice cream sales happen. So but they are both changing because of some other variable, which is the temperature. As the temperature increases, more people go into the sea, hence chances of them being attacked by sharks are more. So that's increasing. As the temperatures increase, more ice cream sales happen. But it doesn't mean that ice cream sales causes shark attacks. The reason why I've given this example is, this might sound very stupid. In fact, people would probably, but the thing is, if something is nicely packaged, you can sell anything. So many, yes. So many people actually use a lot of statistics to actually push their agendas. So you could see here again, iPhone sales and deaths of people falling downstairs. There's a very humorous website. I'm showing you the presentation in the next slide. So these are examples. In fact, this is a very important correlation, which actually I've taken this from a very, very eminent statistician's textbook called, and the name of this person is Chris Chatfield. I don't know if you people are aware of Chris Chatfield. Chris Chatfield is a fellow of the Royal Society and eminent statistician, and I took it from a book called Problem Solving, and in which Chatfield says that his aim is not to teach statistics. His aim is to show that using statistical tools, it is possible to prove or disprove anything. So for example, if you see here, this is from actual data published in the United Kingdom. So you have annual deaths from liver disease, right? And basically it was from a time series. So from the I think it was from the late 60s to early 80s, proportion of households owning a microwave oven. So when you have a time series where you have both kinds of data, somebody had the brainwave of plotting not the time series, but actually one against the other. So as the proportion of households owning a microwave is increasing, the annual deaths from liver disease is also increasing. Hence, conclusion, if you own a microwave oven, chances are that you will die from liver disease, which is a stupid conclusion. A lot of people actually believe this, and it took a lot of scientific work to actually disprove it. People started believing it. So people, when they publish statistics, you have to be very, very careful in publishing, because As I said, crooked statisticians can publish and get away with anything. If you take the next one here, this is basically an attempt at humor. I don't know if people are familiar with some of the idioms in the English language. In fact, in the United Kingdom, people don't say that a baby is born because you don't want to talk about these things. So you say, so if a small child asks, Mama, Mama, where did my little brother come from? The parents say, a stork. A stork is a kind of bird. The stork delivered the child. So somebody actually took this is by the way from one of the best books on statistics. I don't know if you can read it. Box Hunter and Hunter, Statistics for Experimenters. This is the Bible of all practicing statisticians, especially experimenters. This graph is taken from there. So number of stocks and population increase. So if you're plotting these two, you are able to get a positive correlation. So, but then this has no relationship, right? The population of a country cannot have any relationship to number of stocks. So how many believe this? Hopefully not too many. And then of course there is an entire website devoted to these spurious correlations. In fact, more iPhones mean more people die from falling downstairs. And this kind of cheering the team will let you cause weight. And to increase auto sales, you should be undertaking trips to Orlando's islands. All kinds of, by the way, it's from tylervision.com. It's a very popular site. So you have all kinds of people peddling all kinds of nonsense. So you have to be very careful about correlation. So of course, the other extreme is Ronald Fisher. Ronald Fisher, I'm sure he would have known because he was also a biologist. He would have known that definitely consumption of tobacco is injurious to health. And even when a study was presented, he said, no, no, correlation does not mean causation. He's right. So it took a long time for people to actually accept that smoking actually was positively correlated with lung cancer and that smoking was one of the prime causes of lung cancer. The study is by Doll and Hill, and if you're interested, I can send it to you. And one more point about the study, it's a very interesting study. All the participants of the study were doctors. Every single person who participated in the study was a doctor. Anyway, so much for Doll and Hill study. This is again a very important point, which I have found very useful. Suppose you don't find correlation, it doesn't mean that there is a lack of causation. So for example, if you see this graph on the left, if you are looking only in this interval, you may find that the R value is very close to zero. But so therefore, check the range. If you actually sufficiently increase your X variable, you may find, for example, if you increase from here to here, you will find that there is a distinct trend. There is a negative correlation. So time taken to complete task actually decreases with increase of training, which is a very sensible thing. And then again, this is again a very interesting example here. If for example, I hope you can see two different kinds of objects here. You can see crosses and you can see filled circles. So this again is an example from a learning and development team had actually made a presentation. So if you don't distinguish, if you put all the data points as of one single type, then hours of training and error-free execution, there is no relationship. This looks like a zero correlation. But if you actually do it by trainer, if you see trainer A, if you separate out trainer A's people who have undergone trainer A and then measured their times, then you'll find error-free execution is increasing with hours of training. Right? On the other hand, trainer B, there's not really so much of a correlation because there are guys who are doing very well even with very little training. I hope people got this point. So lack of correlation versus lack of causation. It's like, the other example, it's a very nice example which one of my friends made. If you have, this is on team building. Suppose you have four very good people in a team. You have a team where you're trying to do a new product launch. So you have a whiz kid marketing guy. You have a best guy from production. He can give you quick answers on whether it's possible to produce it. You have somebody from R&D and you have somebody from finance. So let's suppose you have a cross-functional team. They're all very good guys. They may all be very good guys, but there is no guarantee that they will work well in a team. The reverse, however, you can be sure. If they're all bad guys, you can be sure that the team will be terrible. So correlation and is like that. You really can't say anything unless you actually make an effort to do stratification and maybe look at the data in various different ways. This example, again, this is taken from botany. It's an extremely interesting example. I'd like you to take a look at this. It is desired to extract a drug from the leaves of a certain kind of tree. And it is believed that the drug content increases with the height. So if that is so, so if you have trees, so you have leaves at various levels. So then this guy says that it's better to pluck leaves from the top because it will have more content of the drug, and therefore it may be more economical to process those leaves rather than work with leaves which don't have much content. So now if you need to pluck leaves from higher levels, you need to buy ladders. So this is a commercial decision. So you'll find in real life, this is what I keep telling people who attend the programs that I do. I also do a lot of Six Sigma training. So in real life, nobody is going to ask you calculate median, calculate first quartile, calculate correlation coefficient, calculate this. No one is going to ask you that kind of question. People are going to ask you a simple question like, okay, I've got the data. Should I buy the ladder or not? So therefore, and you're going to take a decision based on data. So what's the data you're going to get? You're going to get the data of the drug content of the leaves with the height. And data is an M2 to N26 for those of you who have the Excel sheet. And this is what the data looks like. What I'd like people to do is, if you already have the data with you, the data is already available in here. Can all of you see this? Height and drug concentration columns M and N, everyone? Everyone, yes? At least one yes? Yeah, okay, Ritu says yes. Anybody else? Dolly, okay. Now, how many of you actually have this in your Excel sheets? Because I've been given non-stop bhashan now. How many of you actually have the Excel sheet open? Sriharan says yes. Okay, would you like to actually calculate the correlation? You can actually go down here. I hope all of you know how to do it. Can you watch me doing this? You can go here and equal to CORREL, that is correlation. I hope all of you can see Corel. Open the bracket and select the two arrays. It doesn't matter which one you select first, because in correlation, we are not really bothered about. So M3 to M26 and then N3 to N26. Has everyone done this? I'd like people to do a little bit of work for a change. Have all of you got this result? Minus 0.7767? Yeah, 7786. Okay, maybe there is some copy paste error on my side. I don't know how you got that. 7767 is what I got. Okay. Fine, fine. That's fine. That's fine. No problem. Okay, so now the question that you're going to answer, no one is going to ask you the value. A question asked is, will you buy ladders or not? That's the question. Okay, Shubro says no. How many people agree with Shubro? Alka says no. Okay, that's two no's. Sriharan is also no. These are the only three guys who are working. What about the rest? Dolly, okay, that's four no's. Negative correlation, very good. So negative correlation means what? What would negative correlation mean? It means that the leaves are richer below or richer above. Inverse, very good. So that means the drug content is more, correct. Vikas is also correct. Drug content actually increases, it decreases with height. In fact, when I first gave this example in one of the pharma companies I worked, that guy was actually botany MSc or something. Can somebody give a scientific reason for this? He said, sir, there is no need for correlation. It's fairly obvious. But I don't know any biology. In fact, even today, I don't know any biology. But he said that the sap, which rises up the tree, there'll be more of the sap at the bottom and less on top. So obviously, it will be more below and less above. Okay, so, some caution, somebody was saying something. In this case, I will go with the statistical analysis because I would assume that the data has been correctly calculated, data has been correctly measured. Like if you now have a doubt as to how this concentration was measured, tomorrow somebody says the first 10 data points were measured using method A, second 10 data points were measured using method B. We don't know the relative efficacy. If you come up with that kind of an objection, I can take it. But if I mean, I would assume that that kind of an objection is not there. And so we will answer these people saying that we will not buy ladders. We will straight away go with plucking from the lower levels. So now, of course, we come to regression, and I would like to cover a little bit of ground before we break. We break at 12 o'clock. So definition of regression here. It's a collection of statistical tools that are used to model and explore relationships between variables that are related in a non-deterministic manner. I don't know if the word deterministic makes sense. For example, if you were to go to the top of a very tall building and drop a ball or any heavy object, is it possible to know the time it takes? A correlation is not sure, then can you completely? Can you repeat the question again, because it's coming and going, it's going too fast.
It says that, so if correlation is not sure test, then can we completely depend on results without any scientific backup?
No, see, it's like this. Correlation is a very useful tool. It's not the only tool that you need to use. In this particular case, and then again, like I said in the beginning of the session, all statistical tools are meant to supplement your knowledge. For example, this fellow I remember I ran a year-long program at Dr. Reddy's. This was about 8 years back. So a person who knows the subject will not be surprised. You need to be surprised where a statistical result is contrary to what you might think. In that case, you need to be careful. Otherwise, in fact, there is a very famous statement about statistics made by a chap called Andrew Lang, who said statistics should not be used like the way a drunken man uses a lamppost. Now, a drunken man will use a lamppost for support and not for illumination. The function of a lamppost is to illuminate, not support. Because you're drunk, you can't stand. You are not going to use, you should not be using a lamppost for support. You should be using the lamppost for illumination. So therefore, the idea of a statistical test is to illuminate certain concepts. Using statistics as a proof is not, in fact, even statisticians don't support that. The only area where thank you very much, Alka. The only area where statisticians make solid contribution is in the area of experimental design. I'll just, because since I teach the subject for a living, I'll just, and basically experimental design is one step more than regression. The principles used are the one in regression only. But what we do in experimental design is we change the factors in a certain way in order to find out which factor affects the response the most. So in a statistically designed experiment, you can actually say that, yes, it is this particular factor which has the highest impact on the mean. It is this particular factor which has the highest impact on the variation. It is this particular combination of factors which has this particular effect on the mean and or the variation. So these kind of strong statements you can actually make using DOE and also regression. Fundamentally, there is no difference between regression and DOE. The whole thing is built on the concept of sum of squares and allotting the sum of squares in a certain manner. So I'll just give a historical perspective on regression. Term was first used by Sir Francis Galton, who used the term regression analysis in his landmark study of the heights of fathers versus heights of sons. He used the least squares model. By the way, the least squares model was even before. he found that if a father's height was above average, the son's height was also above average, but not by as much in most cases. And a similar effect was observed for below average heights also. In other words, the son's height regressed towards the average. So it was Galton who first called the least squares line regression line. And we're going to come to the meaning of how many people are aware of the exact meaning of the word least squares? You can say yes or no. If it's yes, then I will simply close the session and go to sleep. Okay, Sriharan says no. Clever guy. Okay, Alka, no. Okay, there are so many no. So therefore, I can't cancel my next session. I thought I would cancel the next session and go for my sleep, but apparently I can't do that. So this least squares concept is something very, very fundamental, and I'd like to cover it right now before we break. Overview of regression. So correlation, what we try to do is we try to see if there's any relationship. And what is the kind of relationship? We will try to calculate something called R, the correlation coefficient. And I'd like to once again stress the fact the correlation coefficient is meaningful only after you see a scatter plot. So the first thing, in fact, when we started our Six Sigma program in GE, the first thing that people told us, plot, plot, plot. And after that, plot, plot, plot again. So plotting the data and looking at patterns visually is one of the most important things. And after that, you try to obtain relationships. One of the most shall we say easiest things to do is to calculate the correlation coefficient. The second is if the data, then you have other problems. If the data is not normally distributed, if it's not normally distributed, there are tests for. Anybody is familiar with the basic normality tests? Anyone? Let's say yes or no. There are several tests to actually check for the normality of data. Okay. Okay, again, no, sir. Okay, that's fine, Sriharan. Thank you very much. So normality tests actually, they're all, they are not very difficult, but today the advantage of using softwares like R or Minitab, unfortunately, normality test is not available in Minitab. Sorry, it's not available in Excel. And if you look at the web, you'll find some very painful implementations, very, very painful. But it's possible to very easily gauge the extent of normality using tests like Anderson-Darling or even Lilliefors, Kolmogorov, and Smirnov. There are a lot of tests available. Wilk, Shapiro, lot of tests are available, and all these tests are available in standard packages like R. Hopefully, all of you, if you're going to attend the session in the afternoon on R, do try to see if you can get something from there. So the first part is to see if there's any relationship. And then again, I was trying to complete this here. If the data is not normal, you can actually rank your data, use the ranked data rather than the actual data, and then use the Spearman's correlation coefficient. That also works. And regression is used when it is difficult to predict the value of the dependent variable using basic physical and mathematical modeling. That's a question which I asked a short while ago. If you are on the top of a tall building, in fact, this method is used to estimate height of tall structures. You drop a ball from the top, and how do you estimate the height of the building from the time? Anyone? It's not black magic, let me tell you. If you know, I would assume that there is a equation of motion. Alka, can you tell me the equation? Fantastic. Ut plus half at squared, u equal to 0, put a equal to g, half into g into t squared. So this kind of a relationship, this is called deterministic. It is very well known. In fact, projectile motion. If the reverse problem, you throw a ball into the air at a certain angle, it is possible to calculate how far it will go and then drop. It is also possible to calculate how high it will go. If you know the initial velocity and the angle at which it is projected, it is possible to calculate A, how high it will go, and B, how far it will go. So these are all deterministic systems where there are equations available or they are available. They're easy or difficult, but it's possible to actually calculate. On the other hand, you use regression where you suspect there is a relationship, but it is impossible to actually calculate it. And I'll give you a very, very practical example. uh, the steam, steam requirements in any large plant, the steam requirement could be critical. You require steam for various applications. You might require it for heating. You might require it for running some engines. You might have a lot of requirements of steam. So now the question is, how much steam do you require every month? Because in order to generate steam, you need to have that kind of feed water. You need to have that kind of chemicals to treat the water before it goes in the boiler. Then you may need to also buy adequate fuel to run the boiler. So these are all purchasing decisions. So if that fellow comes back to, so the purchase fellow comes and says, okay, how much diesel do I need to buy? And what answer do you give him? You need to be able to say how much steam you are going to consume this month, right? But you suspect, and it's not a very big thing for you to say that the colder the ambience, the more the steam requirements there will be, right? So the steam is also used for heating actually. So therefore, you might collect data over the last 24 or 36 months on ambient temperature and steam consumption. And then you might try to come up with a relationship between ambient temperature and steam consumption in terms of an equation. What is the dependent variable here? Is it steam consumption or ambient temperature? Which is dependent and which is independent? People are dead. I'm talking of two variables, the temperature. Okay, please, I'll repeat. So you're looking at the relationship between the steam consumption, amount of steam that you consume or generate, versus the temperature outside. Which is the independent variable and which is the dependent variable? Temperature is very good. Thank you, Alka. Temperature is the independent variable. It is the temperature outside which determines the steam requirement. Very good. Very good. Thank you very much. So once you know which is dependent and which is independent, you can actually collect data and so make a prediction equation. And then, of course, there are a lot of other things also you need to be able to talk about. You need to talk about the error in your estimate and other things which will come to later. But the basic thing is, can you given something? That's all regression is about. So in regression, we derive a mathematical relationship. Yes, Subro, please ask your question.
Let me unmute you, sir.
Yes, usage of AC in summers. That's a statement, yes. But Subro had a question to ask.
It's good morning, sir.
Yes.
Uh, Sir, in regression, we used to have two sort of equations. Y
Huh?
on x, in regression,
Yeah.
we used to go for two sort of equations
Hmm.
in basic mathematics, y on x and then x on y.
Hmm.
So if we are finding y on x, then what would I need to find x on y? Again, why they're asking in multiple books y on x, and then you derive another
No,
equation called x
I'll
on y.
come to that later. I'll come to that later. See, that I'll give you a practical example.
Hmm.
And of course, many books, I'm very sorry to say, they contain a lot of wrong information. But I'll give you a straightforward example where normally people develop a regression equation to predict y given x. So
Yes.
if I have a table where I have a lot of ambient temperatures and a lot of steam consumption, I build an equation and then I use the equation to say when my temperature is so much, what will the steam consumption? This is the standard usage. But the reverse also can happen, Subro. For example, in analytical chemistry, what we do is um sometimes you may be looking at the color of a particular solution. The color of a particular solution might change depending upon the concentration of the analyte, or for example the absorbance, some light related quantity that you measure, that might change depending upon how much solute is there. So now you build up a regression curve where you have the quantity of solute available and the absorbance. That example is coming up. And from that data, in fact, in real life, what would happen is you don't know what somebody gives you a solution. So you measure the absorbance and use that to predict what it contains. So regression is also used to build up a y-x relationship and then predict x given y. It's useful for both.
So can we say, sir, the demand for car increases because of increasing income? Can
Come
the
again?
reverse increase in income? The demand for car increases
Uh,
because of increasing income. Can the
okay.
reverse may also be hold good that the income has risen because there is more demand?
No, no, no.
Can it happen?
No, you see, again, I'm not an economist. I'm not an economist, but in fact, can I make a suggestion to you, Shubhro?
Yes, sir.
See,
Please.
this will become a philosophical discussion, but I just want to ask you, have you read the book called Freakonomics?
To some extent, I have known the name. Some few pages, not entirely. I have read.
Okay, that's an extremely interesting book, Freakonomics by Sam. I keep forgetting that guy, the two guys, they both have the first name.
Okay, sir.
Freakonomics by Steve. It's the first names are Stephen. But the particular book, Freakonomics, is actually an extremely good book where all these kinds of questions are asked and answered.
Okay, sir. I will
Okay.
get. I will get it.
Yeah. It's a very good book. Of course, there is a lot of controversy on the book also. There's a lot of controversy. So the book had a lot of controversies. I'll just give you. In fact, I'm sorry. I hope people are not getting bored with my endless stories. Can somebody say yes or somebody say no?
No, sir. Very interesting one, sir. I hope everyone is enjoying.
Okay. Some people. I was hoping somebody would say yes. Okay. The reason why I recommend Freakonomics is these are two. This one guy is an economist and the other guy was a journalist. This economist fellow was a professor at Harvard University. He said that the tools used by economists, regression is again a very important tool, can be used to explain many real life problems. I'll give you one of the most important applications which actually brought a lot of notoriety in the right sense to this particular gentleman. So now what happens is in the United States, the up to class 10, the education is free. Unless you want to send your children to a private school, if you are just an ordinary middle class guy and you are staying in a particular neighborhood, your son or daughter is automatically assured admission into the nearest school. I'm talking of the publicly funded schools. And now the funding to these schools comes from the government and it is based on the performance of the children of that school. So now what happened was you might have a school which has got very bad students. There could be a variety of socioeconomic reasons why that happens. Now what happens is when the children turn in their answer scripts, typically the answer scripts, I'm talking of this this multiple choice A, B, C, D. They would be turning in question papers which are half filled or quarter filled. If they are submitted as it is, then the school would do badly and it would result in lower funding. So what many teachers were doing is after they collected the papers, they would fill in some of the answers. So now the question is, how do you prove that the school has cheated? Is there any non-random pattern that you can detect in papers which have been filled by the teachers and papers which have been filled by students? Is there any non-random pattern? So these two guys, actually, this particular fellow actually cracked this problem, and the National Union of Teachers in America filed a case against him. It became a big issue. So there are a lot of applications to statistics. In fact, I could give you certain examples if you're doing a face-to-face session about somebody had even claimed. Are all of you listening carefully? Suppose you flip a coin, what is the probability of heads coming up? Anyone? If you flip a coin, it's 1 by 2. Very good. Alka has given 1 by 2 and 1 by 2 is the answer. So in other words, if you flip a coin 100 times, you are expected to get 50 heads. Expected, right? You may not exactly get 50 heads, but it will be around 48, 49. So there are two questions now. So the question is now, if you get 51 heads, will you say that the coin is biased? Highly unlikely. It could be 51. If you get 52, I don't know, you may or may not be sure. If you get 53, again, I don't know. Suppose you get 99 heads, will you say that the coin is biased? Out of 100 trials, if you get 99 heads, yes, obviously. But if you get 51 heads, will you say it's biased? No, it's not possible. No, Ritu is right. So there is a number between 51, correct. So there is a number between 51 and 99 or maybe 100 where you will say enough is enough. There is definitely dal mein kuch kala hai. What is that number? That number you can get from an application of the chi-square test. So that's one application. But the more difficult application is like this. Suppose I were to tell you people, all you people who are sitting in the class, today evening after your sessions are over and if you have enough energy, please flip coins. Okay, flip a coin 100 times and just write down on a sheet of paper what you get, like head, tail, head, whatever you get. Flip it 100 times and just come up with a sequence. What statistics will tell you is, if you now give me all those slips of paper, I will be able to tell you by just looking at it which papers are fake and which papers are actually genuine. For example, it's highly possible that I asked you 90 people to do it. Maybe all 90 may not flip the coins, right? You will be tempted. Are you all listening? Are all of you listening? Okay, maybe you can mute your, I could hear some conversation. Maybe all of you can mute your phones. So this is a very interesting point. Again, an application of statistics here. So it is quite possible that some of you may not actually have the time to flip the coins. You will just write some random relationship, T, some you might write. There could be some person who is actually flipping. What statistics tells you is it is possible to detect this by just looking at the pattern. So there are a lot of interesting applications, Subro, but I'll get distracted once I start talking about all those. So coming back to regression and your original question, yes, in most cases we use regression to predict y given x, but you also use it to predict x given y. In this case, the x is more important. For example, typically concentrations of concentration of solutes in very small quantities typically require light absorbance techniques, either using an ultraviolet spectrophotometer or any one of those equipment. In those cases, the absorbance, which is the y, is what is known, and it is used to predict the unknown, which is x. So those are rare examples, but you use it for both. And this word error here causes a lot of problems. It's possible to derive a mathematical relationship, transfer function. We will see it shortly. The value addition comes from here. You should be able to say, like if we saw the previous question, right? Predict wages given income, given wage, given education. In fact, those kinds of studies are possible. Or for example, predict the reactor performance given flow rate of reactant A, temperature, and catalyst. If I know these three things, or for example, what will be the steam consumption given the ambient temperature? What will be the increase in blood pressure given the sound levels in a factory? What could be, so there could be, what could be the value of y given the value of x? Answer, develop a transfer function and put the value of the independent variable, you will get dependent. But the important thing here is a well done regression will also be able to tell you the error. The word error is not to be misinterpreted. The error simply means variation in the estimate. You should also be able to say that if the input is so much, chances are that your output will be so much plus or minus so much. You should be able to say that also. So this is how we go about regression. This is simple. Many of us actually, our life ends with simple linear regression, but actually there is more to it. There's your multiple linear regression. And then you have non-linear regression here also, where the equation is non-linear. Here typically we will have a quadratic term, sometimes cubic term, sometimes interaction term. That is a simple multiple linear equation would be of the form, y equal to some constant plus a into x1 plus b into x2. And if it is involves second powers, it's called quadratic. And if you have product terms like x1, x2 or x1, x3, then those are also called um, equations with interaction terms. Those will also be essentially nonlinear. Of course, all the above assume that y is continuous. And as I said, we will also cover logistic regression. In logistic regression, we will try to see whether we can get a yes, no. And there are some very, very interesting examples coming up. In fact, I wanted to give you one more example. This is actually done by a lot of. By the way, how much time do we have? You also need to tell me when I should shut up. Oh, I just have another 7 minutes. I'm very sorry to say that. Let me try to cover as much as I can. So typically, I want people to be able to, I don't care if I don't cover all the slides. I want people to be able to understand not only the beauty of the subject, but also the immense applications. Yes, Subro, you can ask your question.
Am I audible, sir?
Yes, I can hear you.
Sir,
Subho, sir, yeah. After asking your question, please mute yourself.
श्योर
Yes,
मैडम,
yes.
थैंक यू।
Yeah.
सर अभी हमने जब शुरुआत की थी तो आपके इस कर्व में कुछ कर्व जो थे आपके, वो एक कर्व था और एक कुछ लाइंस थी। तो लाइन शो द लीनियर रिलेशनशिप और कर्व जो है वो कोई लीनियर रिलेशनशिप शो नहीं करता। तो क्या हम ये मान लें कि दो कर्व्स डिपिक्टिंग एक क्वाड्रेटिक रिलेशनशिप और समथिंग हैविंग एक्स स्क्वायर एंड एक्स क्यूब पावर्स बढ़ रही है, तो वो भी कोई रिलेशनशिप एग्जिस्ट करेगा, यानी कि उस स्थिति में भी?
Yes, yes, yes. You see, you will permit me to speak in English if you don't mind, right?
श्योर श्योर सर, प्लीज।
Okay, okay. See, one of the guiding rules in statistical analysis, keep it simple. So we try to go with what is called a linear relationship. Okay.
ओके।
Now, your question is, your question, if I understood correctly, is can we also develop equations with second and third powers, right?
यस।
Yes, but the question is when. So that is where I'm going to talk about one more technique, that is the residual analysis. By looking at the residual analysis, residuals, are you familiar with the concept of residual, everyone?
यस।
No. Yes, that's very good. How many of us have heard of residuals? No, okay. One guy says yes, yes. Okay, Subro is yes. One person said no. Okay, so okay, so I would assume it's evenly divided. As they say, the half the story is there in the regression equation. The other half of the story is there in the residual analysis. So looking at the residuals, a pattern of the residuals, it is possible to say what kind of relationship we need to develop. For example, in fact, I'm just coming to that, Subro. As we go over the slides, probably things will
ओके
become
सर,
clear.
प्लीज सर।
But the answer to your question, yes, we look at quadratic, we look at cubic. Generally, I've not seen too many. And then, of course, we look at square root relationships. And in fact, there is a very nice transformation method called Box-Cox transforms, which actually will help you to decide which is the best relationship. But I don't know if I'll have time to cover that. But generally, you don't really require to use most of these. In most cases, a simple transformation, logarithmic or a square root transformation of the y data is enough to bring some amount of linearity. Okay, so regression here, I'm coming back to regression here. I do not know if people are familiar with the concept of R squared. I'll show you how to calculate R squared. R squared is actually a very good number. It's not the only number, a very good number to estimate the strength of a relationship. Actually, the higher the R squared, the better it is. And what R squared tells you is, it tells you how much of the variation is explained by the model, because the model will predict something, and between the predicted and the actual there will be some kind of noise. So R squared will tell you basically how good your model is. And for those of you who are familiar with hypothesis testing concepts, when we see the transfer function being generated, you will be able to say whether it is good or bad by looking at the p-values. And you can see an example in the multiple regression that we will see later on. So simple linear regression, in fact, I would like to take maybe what? Oh, I've got only 3 minutes left. So just give me. So this is what typically we are going to look at. I have a lot of slides, but what I'll do is I'll just focus on the essentials and send you the rest for reading. And later on, if you have questions, you can ask me. Typically, we are given y versus x. Your data will always look something like this. It will not look something which is in a straight line. Typically, it will look like this. And the question now is, what kind of line will you fit? So, it could be something like this. It could be something like this, which is slightly more acute. It could be something like this, which is again, this is more acute. That was more obtuse. So the question is, how basically y equal to mx plus c, if you want to fit, the m will decide the slope and the c will decide how far from here it will fit, right? These are the two numbers. And that is actually decided by Gauss's principle of least squares. And it's a very simple geometrical concept. I have also hidden some slides. How many of us are comfortable with partial differentiation? Or rather, before I go to partial differentiation, how many of us are comfortable with ordinary differentiation? Yes, okay, Alka is a very brave person. Subro is okay, very good. Okay. So anyone wants to say no? Ritu, okay, everybody likes differentiation, that's fine. So partial differentiation is nothing but an extension. So if you are looking at z as a function of x and y, partial differentiation, when you're differentiating with respect to x, keep y constant, and when you're differentiating with respect to y, keep x constant. It's not very difficult. But the basic principle here is what Gauss said. For example, it's very important to understand the geometry. Suppose this is the fitted line, right? Suppose this line in the middle is a fitted line. And this is the observed data point. And correspond, if you extend this point down, you will come to an x value. So given an x value, it is possible to predict a value here using the equation. And the difference between the observed value and the predicted value is what is called the residual. What Gauss said was the value of a and b, I mean basically a plus bx or whatever mx plus c or beta 0, don't worry about the notation. Beta 0 plus beta 1x. Beta 1 is the slope and beta 0 is the intercept. The value of these constants are to be determined in such a way that the sum of the squares of the distances from the points to the line is minimized. That is the basic principle of least squares. And a very nice derivation is, in fact, this is what is explained here. And this is what the result looks like. And I've also, in fact, I've hidden 2 slides. So we'll stop with this slide. In fact, this derivation, I think is, yeah, for those of you who are interested, I'm going to send these slides across there. It's not all the different. I'm not going to cover the partial differential here, but that's how it's done. This is taken from Montgomery and Runger. So you can see here, this is L. L is nothing but the sum of the squares of the deviations from the true regression line. I don't know what the true regression line. The true regression line is beta 0 plus beta 1x. So the first one would be y1, so y1 minus beta 0 plus beta 1 x1. The second one would be y2 minus beta 0 plus beta 1 x2. Like this, you are to sum up all the squares. So now if you just differentiate here with respect to beta 0 and beta 1. Why? Because beta 0 and beta 1 are what you want to estimate. So at that condition, the first derivatives of L would be 0. So you get 2 conditions here. If you simplify these 2, you will actually come to this equation which I have already given. So, but I don't know if people are interested in doing how the partial differential works. Those of you who are interested can actually follow the work. And the beauty about what I wanted people to just spend a minute to think about is you can actually get these 2 values from all the data points. So you can see here, this is sum of x into y. And this is product of sum of y and sum of x divided by n. And this is sum of x squared minus the sum of x whole squared by n. So this is basically the value of the slope. And by putting the value of beta 1 here, then you calculate the average y and average x and put beta 1 here, you will get the intercept. So this is how it's done. You can actually, if you don't understand partial differentials also, it's okay, but you can actually apply this formula and by hand, you can actually derive the equation of the straight line. So we will do that exercise later on. It's very, very important to understand this. And once you understand this, extending it to multiple regression just involves going one extra step. But this is very, very important. And this is one of the greatest contributions of Gauss to analysis, the method of least squares. So do look up, in fact, you can look up these two pages. I've just hidden them here. And this is what I've explained. I'm going to, we'll call it, we'll break for lunch now. And I'll see you, Ritu. I think we will see at 12:30. Is that okay to everyone?
Yes, yes. We have already informed them that we'll be resuming at 12:30.
Thank you very much. Thank you very much.
You want to break now?
Yeah, I'll go for a break in case I've been shouting non-stop.
Yeah, sir. That was actually an insightful and enriching session, and I must appreciate your energy. You have a lot of energy, I believe.
Thank you
Yeah,
very much. Thank you
because
very
you
much.
still have to take 2 hours of lecture after this
Yes,
today.
yes.
And this was really very engaging. I'm sure the
Thank you very much.
participants are going to agree with
Yes, I
me.
sincerely hope the participants also do not fall asleep in the second half.
Yeah, sure.
Okay then.
So they'll be coming back.
Yeah, I'll disconnect now and then join at 12:30.
Sure. You can do that. So I would like to ask the participants for query, if any, or we can take up the queries, all the queries after the end of second session.
Correct.
Yeah.
Right.
So thank you once again, sir, and thank you all in attendance. The next
Thanks.
session will be on effectiveness of mathematics and natural sciences by sir himself from 12:30 to 2:30.
Right.
So we'll
I'll disconnect now and come back.
Sure, sir. Sure. You can do that.
This is what I did. Can you see my screen now?
Yes, it is visible to me.
Okay. I don't know how to minimize this thing. Okay, right. So for any of these, any two sets of data, you can, like age and core experience, right? You just go bottom, and in fact, profit versus Here, can you see here this screen?
Yes,
Can
yes.
can you see the correl, CORREL correlation correl? Select the first array, select the second array. That's it.
Yes, we found Corel.
Equal to correl, open bracket. Select the first array, that is C2 to C7, and then the second array, comma D2 to D7.
So we don't need to take the header in this.
No, 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 no header.
Okay. This is where I was mistaken. Yeah. Okay, okay.
Then of course in Minitab and R, I don't know how it is done in Excel. Possibly it is there in Excel also. In Minitab and R, if you have say 6 variables, suppose you have 6 variables, right? And you want to check if there is some correlation between some or all of them. Then you need to look at 6 C2 combinations, 6 C2 to 15 combinations. So with just one stroke of a button, you can get all 15 at one go.
Oh, okay, okay.
So
So is there any difference between this Corel and Pearson formula?
Correl and
Pearson formula. You mentioned two.
it's the same thing. That's what I've done here. Pearson formula.
Yeah, we're getting the same result, but
Right.
is any difference in
No, it is the
finding
same
the
thing.
rate?
Correl, see what Excel will implement is nothing but well-known standardized algorithms.
Formula only, right? Okay, okay. Got your point.
So this was just a cross check, just to make sure that I have understood it correctly, or the people can also use formula directly from the book.
Okay.
Yeah.
So Subrosa says that correlation matrix can also be used. Yes, this is how I have done it. So I was just asking for how to do it on Excel.
Okay. How did you do it?
Yeah, we were using machine learning for it. Actually,
Oh, okay.
I was just researching on COVID tests and confirmed cases on COVID. So I was just trying to find out the relation between the two. Obviously, there exists a relation. So
Okay.
I was just trying to find
I'll
the
send you
correlation.
an article which I wrote.
Yeah.
You can send it to everybody here on the application of the Bayes theorem. You see, the conditional probability is something which is very interesting. The whole of Bayes theorem is building up on the conditional probability. The probability of A given B, and then you are trying to calculate probability of B given A, given the first. So I'll send you that article. Maybe you can send it to everybody, and then maybe people can have a discussion.
Yeah, sure, sure. We can do that.
So do I have everyone's permission to start? We're already 2 minutes behind schedule. Can we start? Let me see how many people are there.
Yes, with 60 people I can see, and I have announced on the group that the session is started now.
Okay.
Also, I would like to inform you that Anushri will be hosting the session now.
Okay.
So she'd be of help to you now.
Oh, okay. So how do you're sharing your screen now? Where
screen is already there.
see her? Can you, shall I put my video now or?
That is up to you. If you want, you can put your video on. Otherwise, if we can just go the way
Or
we
what
were.
I'll do is I'll put my video on towards the end of the session.
Yeah, that can be done.
Yeah, I will
During
also.
the Q&A session,
Yeah,
you can put your video on.
Yeah, right. So can I start with the session straight away? Anu,
Good afternoon, everyone. Yes, I'm here, sir. Myself, Anushri from Electronics and Communication Engineering Department. Welcome you all again. In this session, Mr. Menon will intensify our knowledge on the topic effectiveness of mathematics in natural sciences. So we can continue our session.
Thank you very much. Actually, now that you said so, I don't know how many of you have heard of a guy called Eugene Wigner. Anyone? No. Or I'm asking too many difficult questions on one day. Eugene Wigner was actually a chemical engineer who became a physicist. And can you people see my screen now? No.
Yes, sir, your screen is visible.
Okay, good. I'll just take my video off in a minute or so. So he wrote a very long essay. I don't know whether I sent it to Ritu or others or Neha. It's called The Unreasonable Effective. And that was the inspiration for the title of, though now I have made it more prosaic like regression. He wrote a very long essay. I'm going to share. He wrote a very long essay called The Unreasonable Effectiveness of Mathematics in the Physical Sciences. There is no science without mathematics. So and many statisticians actually are very upset because statisticians are considered to be second-rate mathematicians. So there's a big tussle between statisticians and others. Now tell me, can you see my screen?
Yes, it is visible.
Good. Okay, let me first remove my video because it will take up a lot of bandwidth. Yeah, right. So thanks to all of you.
So you're
Let me
sharing
get,
the slides only, right? Please go
yeah,
ahead with the
slides.
question.
Can you see
Right.
the slides, everyone?
Yes, yes.
Okay. So coming back, so we've defined residual. Again, what I want to tell people is now the slides are not moving. I seem to be stuck here. Okay, fine. So R squared value, R squared is typically what anybody who does regression, everybody just looks at R squared and then they do, the trouble is they don't go beyond it. So R squared is the percentage of variation which is explained by the model. Obviously, high R squared means good model. But as we will see later, R squared is only half the story. The other half comes from the residual analysis. So we will go slightly faster in this session because because in the first session, I was trying to build and rapport with the participants and talk about a lot of things which will make life interesting. I'll also send you people, all of you. I think all of you are in this program today are teachers, all of you, or rather most of you. Most of you.
Most of the participants are faculties from different organizations. Some of them are research scholars.
Oh, very good. So it's very important that you people should also maybe slightly increase your reading. I will send you a recommended book list. For free economics, what I told Subhro, that's a very, very good book. I'll talk about some other books also. So regression, of course, if somebody talks to you about regression, the first thing they will ask you is, hey, what is the R squared value? R squared should be as high as possible. Typically in science and engineering, here again, there is no cutoff. In science and engineering, we look for at least 85 to 90%. Again, there is no hard and fast rule. But in the social sciences, a lot of, in fact, some of the best books on regression are written by social scientists. In the social sciences, even 50-60% chalega. In fact, I myself was helping out one of my colleagues who is a very senior doctor in London, who is a psychologist and psychiatrist, and they were doing some studies on depression levels of people who are in jail for various crimes and all kinds of stuff, and a lot of statistical analysis was required. So I was very surprised to find that some of his students, I was just acting as some kind of a person reference point, just to check their analysis. So they had a very good understanding of stats, and some of the best books on statistics have been written by psychologists and psychiatrists. So now R squared is just half the story. The other part, of course, we also need to look. This is very important. I hope you can see the screen. R squared adjusted. This R squared adjusted is a very important concept because it will adjust for the number of terms in your model. So basically, there are many frauds who will conduct just two experiments, so two data points, and then you have an equation with two terms. So your R square will be 100%. So artificially high values of R squared, you can catch him by asking him to report R square adjusted. And you can see the formula for R square adjusted here. It is 1 minus n minus 1 by n minus p, where n is the number of data points, and p is number of terms in the equation. So obviously, if you have n equal to p, then this becomes a bogus number, right? This vanishes. So R square adjusted is what all of us need to talk about. And this slide that you're seeing right now is the only difficult slide in the entire set. And it's this. With the regression equation, we are now going to look at the regression equations, and I'll also show you how to estimate them. So the question that very frequently people ask is, okay, you have been able to predict. What is the variability in your estimate? Variability meaning the other word people use for variability is error. Error is not to be used in the sense of a mistake. Error is to be used in the sense statisticians use it. For example, you may be familiar with the term called SEM, standard error of the mean. The word error in statistics has a very specific connotation. It has to do with the variation. This formula looks very ugly. It looks very ugly. You can see here there's a t function coming here and a sigma squared and some S So formula you don't have to remember. But what this gives you is, given a certain prediction, it will also give you the confidence interval about the mean. So any standard statistic, unfortunately, this is not available in Excel, but it's not very difficult. It's not very difficult to calculate. If you know this formula, this is nothing but mu predicted. The mu is the value of y, mean value of y at a value of x0. And this is the uncertainty. T alpha by 2, T is of course the T distribution. Alpha is typically the level of confidence, typically 5%. So this will be at the 2.5% level on either side. And n minus 2, and the sigma squared is basically the kind of, it's basically squares error by n minus 2. I mean, I don't want to go into too many statistical details. But what this formula, this ugly looking formula will give you is, it will give you the variability in your estimate. And that is a very, very important thing to know, as you will see right now, And this is the prediction interval. This, many people get confused between confidence and want to spend too much time on it. Confidence interval looks only at the error generated from the data set. In a prediction interval, again, there's a little bit of conceptual statistics required, which I don't want to get into. In a prediction interval, we consider not only error from the model, but also error from future observations. So this is supposed to be more rigorous. So as of now, you have to take me at face value. When I tell you that this is the formula, as I said, this is an ugly looking formula, but you can actually estimate from any regression, you can actually estimate the value of a sigma hat squared. This is nothing but the sum of square of error divided by n minus 2, square root of that. And once you know that, you know n and sxx, this is nothing but, if you know, typically in a regression, you have x values and y values. So sx is nothing but the sum of the deviations of x from the mean. So if you have 10 x values, calculate the mean of that, and then take the deviation of each of the x values from the mean, and square it and sum it. That is sx. All these are readily calculable formula, and I can send you an Excel sheet with these. But the learning which I want you to take away is, in addition to R squared, you should be able to talk about R square adjusted. What is R square adjusted? R square adjusted adjusts for the value of R squared by considering number of terms in the equation vis-a-vis the total number of data points collected. In General Electric, where I worked, this kind of statistics was because when people are doing a lot of research, you know, you really don't have time to go much into detail. So when somebody is presenting data, one of the first things that you want to ask him is, what is the difference between R squared and R square adjusted? If the difference is very large, it means you don't need to be Einstein to figure out. If the difference between R squared and R square adjusted, if it's very large, it means he has not taken enough number of data points. So as I said, don't be worried if you're not able to understand everything at the first go. That's not very important. The example that I have here, this is an excellent example, and that's why I was when I saw this example in a business stats book, I was reminded of economics. You can see here, you can look them up, Ashenfelter and Jurasda. What they did was, they said, so how do you estimate the wage? What do you think could be a realistic wage? Because large investment decisions made by companies, you need to actually understand what the likely wage bill is going to be like. These fellows came up with a very nice way of estimating the average wage in a country. So net hourly wage, what they've tabulated, is based on a weighted average of 12 professions. You know, you could have plumbing, you could have carpentry, you could have, I mean, all kinds of professions. Hourly wages. So you get a weighted average, and the data is in cells E2 to G29 in your Excel sheet, and also on the next slide. And the question here is, how strong is the relationship between the price of a Big Mac? Everybody has heard of a Big Mac. It's the McDonald's burger. It's a very, very standard product across countries. In fact, how many of us have heard of the Arvind Eye Hospital? Anybody has heard of the Arvind Eye Hospital in Madurai? Anyone? Yes, no? I think everybody.
Sir, one of our participants, Ms. Alka, is saying that
Alka, yeah,
she has
okay.
heard about it.
Alka, yeah. No, it's a very
Mr.
interesting.
Ramesh is also writing.
Right. The why I mentioned Arvind Eye Hospital is, Arvind Eye Hospital is it's in fact even before your famous Shankara Netralaya in Chennai, where people from all over India come. That's based in Chennai. But Arvind Eye Hospital is based in Madurai. And it's of course a very, very famous hospital, and the owner is a very different kind of man. He went to the US to study advanced techniques in eye surgery, came back and set up the hospital. And he said, I want to do some social service. So 70% of the people, 70% of the patients pay for it, and the other 30% are subsidized. But anyway, I'm not talking about socialism or economics. I'm just talking about Dr. Arvind Venkataswamy. Dr. Venkataswamy, he said when he went to the United States the first time, on a weekend, one of his friends took him to McDonald's. It was in a particular city, and he kind of liked the food, the decor. It has a very standardized appearance, and in those days, it was a big thing. I'm talking of the late 70s, I think, late 70s. Then next week, he flew to another city, and his host said, "Hey, why don't we go to McDonald's and grab a burger?" And he found that the restaurant looked exactly the same. The food tasted exactly the same. Then again, a week later, it was the third McDonald's event. Again, it was the same. So what he said was, if something like a burger manufacturer, like it's something very ordinary, right? You make the patty, you collect the bun, you put the dressing, and then you put it in the paper and give it. This is simple operations. If even in this kind of an operation, they are able to have so much of standardization, the kind of work that we are doing eye surgery, we should be looking at even more standardization. And he said that it was McDonald's which actually inspired him to standardize his operation. So McDonald's is whatever you might say about the health quality of their foods, great company, and this particular it's a very revolutionary concept, trying to use the price of a Big Mac in a country to predict the hourly wage. So three questions here. How strong is the relationship? How would you answer that question, anyone? How strong is the relationship? What is the first step that you would do? First step? Yeah, correlation is a good answer, but that's not the first step. The first step always is to plot, plot, and plot. So can I request you people, if I'm going to escape here, I'm going to escape from the slideshow mode. Can you go to the Excel sheet which you have, in correlation regression? You've got the sheet with you. You've got your data in columns F to G. Can you people do correlation before a correlation? Can you do a scatter plot? That's the first thing that you should do when you have bivariate data. In fact, let me just show it to you. You can do it in Minitab also. I don't know if you people will be interested in seeing Minitab. Anyway, let me just keep it open here. Let me open Minitab for a change. Minitab, where is this damn thing now? Hourly wage versus Big Mac. While that's opening, I'll open this in Excel. In Excel, it's very easy. You go straight away to just select it here. Just go and say, I hope all of you are doing it. Are all of you doing it, or you are expecting only me to do it? Is anybody trying to do it now? Anyone has tried to generate what is called a scatter plot? So select the data here and then go to insert. Go to insert. Bharati, have you done it? Very good. I'm happy to see. I hope Alka, okay, yes, sir. Many people are trying. Very good. I'm happy to see people are working. So go to recommended charts. This is the good thing about Excel. There are some things which it does very well. So you go to recommended charts, and then of course the computer is slow. Ritu is very smart. She's already done. See, already it's been done. Just click this and click OK, and that's it. You are done. And then of course all the beautification. You can do all the beautification by going here and labeling. You can just go here, click, and then click access titles. The moment you click access titles, you'll find titles generated here. Go here and type here, then you change the color. You can give background color. I mean, you can do all kinds of things. But this is what it looks like. It looks okay. There is some element of non-linearity, but okay, we should be able to live with it. So let me just in fact, what I'll do is I'll just delete this. I don't really need it so much. A correlation coefficient, you can just put correl equal to correl, select these two, and then you can report it. In the meanwhile, I don't know how many of you are familiar with this thing called Minitab. Minitab, let me just open it. It'll take probably half a minute to open. It's taking time. Okay, so let me come back to construct a model to predict the hourly wage in a country given the price of a Big Mac. Now, where I want you people to actually do it, I've also explained how to do that. You can do it using Excel. You can also do it using first principles. You can also use Minitab. So Minitab, of course, it's much easier, but unfortunately, the only problem with software like Minitab is unless you're working in an educational institute like IGDTUW or others, it's very expensive. You know, every year you have to pay something like 1.5 to 2 lakh rupees. So it's very expensive. That's why today everybody is using R. And of course, you have Excel, which is not all that expensive. So regression. So before I come to all these things, let's look at, you can also do it in Minitab. You can go to graph and you go to scatter plot, just select scatter plot and select the two variables. It's fairly easy. You can select the simple scatter plot, okay, and you tell him that which is the Y variable, it's hourly wage, X variable is the Big Mac, and you can put label, you can write whatever fancy labels you want and just get something like this. This is what the scatter plot looks like. This is exactly the same. So in many ways, Excel is very powerful. You got exactly the same thing in Excel. The point now is, how do you develop a regression equation? I don't know if you people are familiar with how it is done. It's actually very easy in Excel, and I've also given you here in the slides. I've also explained how it is to be done. So the R value, by the way, is 0.81. I hope all of you got this number. Everybody's got 0.81. Just one or two of you say yes, no, maybe tomorrow. Okay, very good. Alka's got 0.81. Anyway, it's not a big thing. 0.81 means the correlation is fairly good. I won't say it's very good, but for, I mean, 0.81 is even acceptable for engineering purposes. For economics and social sciences, 80% is very good, extremely good. So I leave it here, and I'm now going to come to the actual development of the equation. See, you can generate the regression equation and relevant statistics like R squared in Excel, but these involve usage of array formulas. So is everybody familiar with array formulas in Excel? Array formulas? Just somebody say yes, no. How do you use array formula in Excel? No, okay. So this is one learning which you can possibly have. I look at 2 or 3 different ways, because the idea is we should be able to do most of the work using Excel. Or if you have if you have Excel, you can also use Excel and combine it with some stats books to actually do some reasonably good analysis. All that Minitab does is, it brings everything in one page. And for the corporate people who don't really have much time for these things, it's very useful. But otherwise, it's put the slides. I will do that. It's a good question that you've asked. There's a reason why I'm putting it here, Ramesh. And can you people read it better now? Is it better? There's a reason why I've put it in right now in this mode. I'll go back to, yeah. The reason is I need to frequently shift between PPT and Excel. And if I put it in slideshow mode, every time I have to escape and the computer will hang for 10-20 seconds. That's why. Fine. So now you can generate the regression equation and relevant statistics like R square, etc. in Excel, but these involve usage of array formula. I'm going to show you how it's done. But now tell me, in this example, which is the dependent variable and which is independent? Dependent variable is wage or price of Big Mac? Anyone? Price of Big Mac is what? Is it dependent or independent? No, it doesn't depend on us. There is one answer. Anyway, it's a good answer that you've given. Yes, the price of Big Mac is not dependent. You see, you should understand how people think. Suppose you go to a different country, you go to a strange country, it's very easy to go to the nearest McDonald's showroom and, hey, I want a Big Mac. What's the price? It's very, very easy to get that price. It is not so easy to go to some stranger and say, hey, what is your hourly wage? He might probably slap you. So the independent variable is the Big Mac. Depending on the Big Mac, how does the hourly wage vary across countries? Right? So the dependent variable is hourly wage. The independent variable is Big Mac. So as you can see here from the previous slide, somebody's collected data. In Argentina, the Big Mac costs $1.42. And the other great thing about McDonald's is pricing. Whole of Argentina on that particular day, I mean, unless they change the prices, the price will be the same, unless you have offers. So you can see, for example, in Great Britain, it is $3.14. Unfortunately, India is not here. In the Euro area, basically all those, Luxembourg, all those places where, yeah, got it. Good. Thank you very much. And you have Hungary, Indonesia, all kinds of countries. For example, you can see here Sweden is very high. Sweden is 3.6 is the Big Mac price in US dollars. Denmark is 4. These are some of the costliest countries in the world. Anyway, so you got the hourly wage in these countries, and this is the Big Mac price, and then you have the net wage, hourly wage, and then you're trying to build a equation. Now we are going beyond correlation. Now we're trying to build an equation, and as I said, I've given you an exact way of doing it. It's very painful, but then there are other ways also to do it. If you just wanted shortcut formula for slope or intercept, just type this index, linest, y array and x array. Y array is basically the dependent variable. That's why you need to know which is dependent, which is independent. So you have to name the y array first, then the x array. So just copy this formula blindly, you will get it. I'm going to do it right now for you people. So I go to this place and I go to Big Mac data, and it's not here. This is using some other. So correlation, Big Mac, okay, then let me look at, okay, I'll look at this here. So, right, so this Excel output, I'm going to do it once again for you. So I go to, it's slightly painful. So please bear with me. So you can see it's 4 by 2, 4 rows and 2 columns. So you select, you can do it as we go along. If you have it here, you can go back to your original sheet and just focus on those two. So I'm going to select 2 columns, 1, 2, 3, 4 rows. So select an area like this and then press Fn F2. Or if your F2 works without Fn, that's fine. You press Fn F2, it will start blinking here. And here you write down the formula, linear estimated, right? And then open the bracket. And you can see here, I hope you can see my screen. And let me increase the size if required.
Yes, sir, your screen is visible.
Thank you so much. You can see so Excel is telling you known y. So the known y's is here. I'm going to go here and select the known y's. I'll select the known y's here and then I put a comma. Then known x's. Make sure you select correctly, right? Sometimes people don't select correctly. So D3 to D29 and C3 to C29, that's here. And then comma, and then in this case, constant, it's you have to say true, because sometimes what happens in certain cases, which are not of importance now, where conditions demand that the intercept is 0, you can force the regression to make it 0. That way you write false. But otherwise the default is true. If you don't write anything, they'll take it as true. There is an intercept calculated. And then the next one is stats. It is basically true. So you type true and then close the bracket, and then this looks like a lot of black magic. Then you press Control Shift and enter, and then this is how it's meant. So this is slightly painful. Here. And I've explained all these quantities back in the PPT. In fact, you can see this is what I've copied and pasted. I've copied and pasted from here. You can see here. So this is the slope. So the equation is of the form hourly wage is equal to 4.74. I don't want to report this up half a dozen decimal places, just 2 decimal places. Hourly wage is equal to 4.74 into price of Big Mac minus 4.54. That is the equation. These terms may be slightly difficult for you to swallow right now. I'm just going to, this is standard error of the slope. This requires some very ugly looking statistical formula. Don't bother too much about it. What this tells you is, this is the uncertainty in the measurement of the slope. This is the answer. So you can see that the relative uncertainty in measuring the intercept is more. This is the standard error of the intercept. This is standard error of y, all the y data. The standard error is this number 2.93, which is nothing but SSE by n minus 2 square root of. Please don't bother too much about the statistical formula. That's not very important. This number is very important. The R squared number is very important. 0.659. That means this is about 66%. So what this tells you is about 66% of the variation in the data is explained by the model. So this is what the simple linear regression looks like. And I'm now actually it's possible to do this separately in Excel. In fact, I had sent this request yesterday. Let me just do that here. In fact, I've already done it here. You can see here. This looks slightly ugly actually, but let me just the standard error. Do you remember me saying the standard square SS of residuals by n minus 2 take square root, you will get 2.93. Don't bother too much about that. That is basically the uncertainty in the y numbers, the kind of variation in the y. Just a second. I'm going to now show you how to do this. Now, how you do it is basically you need to go. Do you people see something like this here? All of you may not have it in the data section. Do you have something called data analysis? I don't think many of you will have it. Can you see this data analysis option? Yes. Oh, that's great, Subro. What about the others? Excellent. So all of you have got the add-in. Very, very nice. That's very nice. So if you have the data analysis add-in already done, for those of you who don't have, anybody who doesn't have it, any no, I can see 3 yeses. Anybody with a no? I will assume that everybody has it. In that case, you just need to go to data analysis.
Sir, one of our participant is writing that no.
Okay, no, okay. So, okay, right. So that's good. Who is this participant?
Pavitra Gautam.
Okay, Pavitra. Okay, Pavitra and all others who are listening, if you don't have that, I mean, I sincerely hope this works because, okay, Sunita also said no. So you go to the basic, all of you have Excel too, because, you know, the options keep changing with the revision. I have Excel 2016. Here I go to File and I go at the bottom, I can see More. I click More and then I look at Options, and within Options, I'll see, you can see add-ins, and in the add-ins, in my case, it's already added in. In your case, you have to go and select analysis toolpack and add it. You'll have to go here and where's this thing now? Add-ins. It's taking a long time. See, Excel options not responding. Yeah. So add-ins, within add-ins, you'll have to, in my case, it's already done. In your case, you have to select that and add it in. That's all you have to do. It's not a big thing. You can do it by yourself. So what I want to say was, within data analysis, if you once you add that add-in, you will find that this option comes and sits here. And within this is very simple. You just go here and select regression and click OK. And once you get that, you select the input Y range, Y and X. It's very important that you understand what it means. Typically, Y is always the dependent variable. Y is the dependent variable. That is the value for which you are interested. And X is the independent variable. That is the predictor. There are many terms that people use for X. X is the most common word used. People call it predictor. People call it regressor. So these are different names for X. So this is the simplest case of, and unfortunately in Excel you can only do one Y with one X. And then of course default is in a new worksheet. It'll open a new worksheet, and then you can ask for all these plots, residual plots, etc., etc. We'll discuss all of them, and also the normal probability plot. So you can give all these plots and click OK, and you will get this terrible looking sheet. So this is what it looks like, and I'm not going to spend too much of time on all the statistics here. The most important ones, of course, are here. You can see the R squared 0.6596 and adjusted. So there's not much of a difference. So which means there are enough number of data points, standard error observations, And then of course, this is the intercept, you have the standard error, X variable, all you'll find all these things, but it's not written in a very nice format. And that is where even R, for those of you who are going to take the second session after mine, in R, of course, you have a very, very powerful function called LM, the linear model. And the linear model comes with all the statistics, and it's very, very useful. And once you're used to R, you may not really like using Excel for data analysis and plotting. R is very good. So anyway, I sincerely hope you make the best use of that session. Let me come back to my PPT again. So I'm just going to show it in Minitab, because in Minitab, for example, you can take a very good look at, for example, this is the scatter plot, right? And regression analysis, hourly wage versus Big Mac. You can see it's written in a very user-friendly format. So all that I need to do is to go to stat, then regression, and then go to regression, fit regression model. And here, of course, I've already done it. I want to, my response is the hourly wage, and my predictor is Big Mac. And here again, you have categorical predict. Let's suppose that categorical predictors, as I mentioned in the first session, where you have categorical data. For example, you want to also look at gender for men and women. So you might have category 1 and 2 for that. Or you might have, depending upon whether you're in an urban area or a rural area, there could be various kinds of predictors. So right now we have only one predictor. And if you just click OK, you will get these results. And this is what it looks like. You can see the way the data is presented, it looks much more wholesome than Excel. And this is, of course, a very important output which Minitab gives. So you can see something called the p-value here. The p-value for the regression is 0, means the p-value is much less than 0.05. So what we say is that the regression is significant. That's what it means here. Then you have a fitted line plot. So basically what Minitab has done is it has taken this scatter plot and fitted the best straight line. And these are the residual plots. Residual plots are something where a lot of people are not very familiar with it. I'll just take, so what is a residual? Anybody would like to tell me what a residual is? I defined the residual already in the morning, right? What is a residual? Very good, very good. Left out. Okay, left out. So residual in a very simple thing. It is basically the actual value minus predicted value. Actual value minus predicted value. So now, how will you calculate the first residual? You can see here. I'd like you people to be able to do it yourself. I can go here and write, predicted value. I can just make it. I can do it in Excel. I can do it in. Let me do it in Excel. That might be better. So I go here and I go to. I hope all of you are following along. So I go here and write predicted value. Predicted value. How will you get the predicted value? Anyone? Anybody? How will you get the predicted value? In fact, let me go and make it 2 decimals. Otherwise, you'll have some 40 decimals coming up. So let me go and standardize. Just a second, please. Anybody would like to? Okay. Format cells and make sure everything is only 2 decimals. Else you'll have some 500 decimal points. Okay. So the predicted value. Anyone would like to tell me how will you predict? For example, this 1.7 is the actual value. How will you get the predicted value? Anyone? Sunita Handa says 1. No, it's not 1. But it's a good answer. Predicted value. In fact, this reminds me, I'm very sorry, please don't. I mean, sometimes I like to bring in some humor just to wake up the people. It's like Saat Kand Ramayan padke, Sita kiska baap tha, asking something like that. The idea of doing all this jing bang is to come up with an equation. The equation is this. The hourly wage is equal to 4.74 times the price of the Big Mac minus 4.54. That is the prediction equation. So here I will go and say equal to slope into Big Mac price plus I'll always write plus because if it's a negative term, that negative term automatically gets added, right? So this is the predicted value. Is everybody clear how I got the predicted value? I'm using the regression equation to predict it. That is the basic idea of having a regression equation, to be able to predict. I can now do this, and the only thing, I don't know how familiar you are with Excel, but if I pull this formula down, I will get all zeros after some time. See, I'll get all kinds of strange results because Excel works on a relative principle. So these two numbers should be anchored. So I go here, L3, it should be $L$3. I hope you people are familiar with Excel to that extent. $L$3 means it will, okay, Alka says yes. And plus C3 is fine, it will vary, and it will be $M$3, $M$3. So now I can pull this down, and then I will get the predicted values for. So this is the predicted values of the. Now can you tell me how will you get the residual? Anyone? How will you get residual? Difference, very good. So it is nothing but actual minus predicted equal to actual minus predicted. So the residuals are very important. In fact, I find many people that are very enthusiastic only about R square. The residual is important. So that's the residual plots done in Minitab. So forget about the normal probability plot. Normal probability plot, you need to know a little bit of principles of probability plotting. As of now, let me tell you that this looks more or less normal, and there is a particular, I don't know if you're familiar with the Anderson-Darling test. I'll just copy these residuals here. I'll just copy these residuals, and I'll do a very quick test. Control C, and I go put into Control V here. Control V, and then I do, please bear with me. I'm just doing a very, very brief graphical summary here. So if you want to check whether it is normal or not, the p-value is 0.248 for the Anderson-Darling test. Can you people read my screen? So then I'll conclude that it is more or less normal. So that's how I check for normality, but that's not the scope of today's discussion. Coming back to the PPT here, we are looking at residual plots. So residual plots here, regression analysis. In fact, can you see here residuals versus order? This is the first plot. So first data point, second data point, like that you have 27 data points. For the first data point, you can see here the residual is minus 0.487. It's here, minus 0.1. The second one is 3.53. The second one here is 3.53. Can you people see what I'm doing here? Everyone, just somebody say yes. Okay, so this might look like a lot of mumbo jumbo, but I want to now ask you a simple commonsensical question. And that is, if you now, for example, you have a prediction equation, and now you are looking at the deviations. If your prediction equation is good, then you roughly expect how many members to be above the prediction value and how many members to be below the prediction value, roughly. From common sense. You have 27 data points, right? There are 27 data points, and each of these 27 data points, obviously the agreement will not be exact. In this case, for example, the actual value is less than the predicted. In this case, the actual value is more than the predicted. In this case, it's less. In this case, it's more. By sheer common sense, don't get into statistics. What percentage of the numbers do you expect to be less or more? Less than zero, residual less than zero, residual more than zero. This is not a very difficult question. It's a very simple question. Yes, Pavitra, thank you very much, Pavitra, for having saved my reputation. It should be half. Roughly, it should be half. So if one good way of testing it is, instead of this, you do the auto sum. Just do the auto sum here. I don't know if you're familiar with the auto sum. You go to home. The auto sum is right here. It should not be too different from zero. It would be exactly zero, but in this case, it's 0 to 3 decimals. It's almost zero. So if your model is reasonably well selected, the residuals also will follow this pattern. Some of them will be above, some of them will be below. The average will more or less come to zero. The sum will more or less come to zero. Some of the residuals will come to zero. So that's what you're testing here in this residual test versus order. And then you have, this is the histogram here, the same thing. You can see some of them less than zero, and you can actually do it by actual count. This is something very interesting. This one versus fits. Fits, everybody knows what a fit is. This is a fit. The predicted value is the fit. So for every predicted value, you can see here, for every predicted value, what is the residual? That is residual versus fit. You can do this kind of analysis. So here also, the pattern should be random. In some cases, it's below zero. In some cases, it's above zero. So this should also be random. Only if all the residuals are satisfied, then only can you say that the linear model that you have chosen is a good representative of what is actually happening. So these two economists were actually right. It's a very, I think it's a fairly famous paper where you are using something very simple. In fact, the price of a Big Mac is very simple to get, right? You don't even have to go to that country. You can call somebody and say, hey, how much does a Big Mac cost? So using a very simple regressor variable, you can try to get some idea of what is the hourly wage in that country. Where statistics actually helps, in fact, you can actually do the calculation using the slides that are given, but I am too lazy to do that. I am actually going to look at the prediction. You can actually do a prediction here. So now can you tell me, the question asked in the Excel sheet was, in fact, it's asked in the PPT. Can you now tell me, the question here, use the above to predict the hourly wage in a country where the price of a Big Mac is $3. What do you think is the hourly wage in a country where the price of a Big Mac is $3? How would you answer this question? Can somebody give the answer? Yes, Anushri is trying to say something.
No, sir.
Okay, because I got a notification saying a host is saying something. Okay, anybody wants to say something? How will you tell me, yes, Alka, what if linear model does not work? A good question, but we'll answer that question later. Right now, it does work. Yes, you're right, Alka. In fact, that's a question which everybody has in their minds. So answer is this. For the first, you need to understand your question correctly. What is the meaning of the phrase, if linear model does not work? It means your R squared is very low, right? B, your residual analysis is not pakka in the sense that you will find the residuals. I'll show it in the residual analysis coming up. Residuals are not okay. R squared is very low. In that case, what you do is you have two choices. A, transform the data. Transformation of data will, in fact, probably if you people are interested, maybe a couple of months later, we can do an advanced regression where I'll show you the various kinds of transformations. Transform the data or either transform the data first and then check, or you can use a different function. Instead of using only linear, you can use quadratic and all those options. Minitab also. When you go to Minitab, you go to stat, regression, and you go here, regression, fit regression model. It will tell you the model, what's a kind of model, terms through order, right? Interactions, terms through this first, you can select order and all those. So you can change all these things. Even you can even, in fact, there's a simpler, there are two options for regression here, the shortcut and the long cut. If you want to do just a fitted line plot, this is very simple. You see the default is always linear. You can also fit quadratic and cubic. And then, of course, if you use the formal option, that becomes too complicated. Now, I'm not going to answer that, but the basic answer to your question is Alka was the person who asked this question, right? In regression, you go here, fit regression model here, and model. This is where you change the terms, and the other one is the options. Options. So then again, you have transformation here, a natural lag or square root, or you can give your own value of lambda, or then of course there's you have the Box-Cox response also is available. So like that you can then of course stepwise regression. I don't want to get, this is when you have too many regressors. When you have 7-8 regressors, then how do you select that? Then you use stepwise regression, and that's how you keep. And then of course you can have come up with your own transformations. You can actually instead of, see, for example, we did y, right? If there's a huge amount of variation in y, you can create another column called log y. That's a transformation. Typically, when would you use a log? Everybody remembers what a logarithm is? Everyone remembers what a logarithm? What is the logarithm of 1000 to the base 10? Did. What is the logarithm of 1000 to the base 10? Nishaben, I'm happy, Nishaben, somebody's answered very good. What is the logarithm of 25 to the base 5? Oh, just a quick question. Very good. Okay, so some people know what logs are. Very good. So typically logarithmic transformation is used when the range of the data is very high. Like suppose this is not very much, right? You have 1.7 is the lowest, I think, and going up to 12. So roughly, do you have more than 12? I think you have a 14. Yeah. So 14, 1.5 to 14 is how much? How much is 14 divided by 14 divided by 1.7 is how much? 14 divided by 1.7 is what? Maybe about 8 times, right? Generally, if you have the highest data point by lowest data point, if you have that ratio more than 10 or 20, then you go for a transformation. Yeah. Thank you very much. For here, you don't require a transformation. So your answer to your question, Alka, you asked a very good question. In fact, I'm not sure if people know how to frame that question. When you say model is not working, you should first turn around and ask that fellow, what do you mean by that? First thing is R squared is low. Okay. Now, even if R squared is high, so what? Next is, have you looked at the residuals? So if the R squared is high, it doesn't mean the model is good. R squared is high means one of your regressors is correct. You go and look at the residuals to look for any funny patterns. I'm going to discuss those later. If the residuals are not okay, then you need to either transform the data, or you need to actually add more X's, or maybe you need to do some transformations. So that's the meaning of, that's the answer to your question. The prediction part, this is the regression equation. You can go, thank you very much. So you can go, I asked you a question, right? What is the wage in a country where the Big Mac costs $3? Answer. Yes, very good. Please use it and tell me. Thank you very much. Please use it and tell me. I think people are waiting for me to do the problem. You can actually, if you are very lazy, you know what you can do? You can go here, like I built up a table here, right? I just go here, I just change this number here and put 3. Is everybody watching? I just want to change it and make it 3 and see what the predicted value is. 9.17. Everybody got 9.17? Yes? I have a feeling that you people are expecting me. Huh? No, at least 2 or 3 people should say yes, otherwise I can't proceed. People might be sleeping for all you know. Or people are probably putting up Facebook updates, the most boring program ever in my life, or something like that. Did everybody get 9.17? Sunita got 9.17. Very good. So you can actually use Excel. You can also use Minitab. So what I did in Minitab was, and the value addition in Minitab, you can also do it in Excel. You can do it in Excel, and I'll show you how. So you go to stat, I go to regression, and I use, since I've already done a regression one, I can use this predict function. So I go to predict and I say when it is 3. I just put 3 and I click OK. I've already done it. I'll get this answer here. And 9.678, right? This is the fit. Now the thing is, can you see these two prediction intervals here? Prediction intervals and confidence intervals. This prediction interval is fairly wide. What this means is the actual hourly wage can vary between 3.4 and 15.9. That's a huge range, but this is what you can expect. You can be 95% sure that the actual wage of this country, where the Big Mac price is $3, it will vary between 3.4 and 15.9. And if you're asking me, how did you get these two numbers? The answer is already there in your slides. It's there here. In this prediction interval, this x0 is the x of interest. X0 is 3. X0 is 3. And x bar is the mean of all the x values. Sxx also you can calculate. N is the number of data points. Sigma squared is nothing but sum of square of error divided by n minus 2. All these things are available in this text here. And this is the t value. The t value for alpha by 2 and n minus 2. So you had 27 data points. So 27 data points, if you put the t inverse function, if you put 0.05 and 25, I think it should come to 2.05. And what's the answer coming to? 2. Just 1 second. That's the particular value of t that you need to use. So but the thing is, it's very painful. Minitab will do the whole thing. If you know what is this y0 here, y0 is the predicted value of y corresponding to x0. X0 in our case is 3. So if you put 3 and if you predict the value, you'll get this value here. Put all these numbers here, and it's very, very painful. Minitab does the whole thing in one shot. And you can see here, for as far as we are concerned, the prediction interval is more important. The prediction interval is more important. So you can say that the predicted value is 9.67, but there is a good chance, there's a 95% chance that it will vary between 3.4 and 15.9. So even if you don't have Minitab, any decent statistics book, I'll give, in fact, the reference list is also here. Any decent textbook will actually give you all the formulae. You just need to spend some time and put in those formulae. That's all you need. So is this part clear? I hope so. And what I'm now going to do, I'm going to skip the next. Example. I'd like you people to do it by yourself. I'm going to send this across. And regression Excel, I've also told you how to do all these things. This is of course the Minitab output here. This is a scientific and engineering example. Here again is just answer the last question. So you have the data here. This is basically the hydrocarbon content, and this is the in the condenser, and this is the purity of the oxygen formed. So again, people want to be able to predict what is the purity of oxygen formed if you know the hydrocarbon content. It's exactly the same way, and I'd like you people to work this out by yourself. You should be able to get this output if you tabulated data correctly, and I'm not going to spoon feed you. This is the Minitab output here, and by now, what I'd like you to take away from today's program is when somebody asks you, so what did you learn in regression? What are you going to tell them? You should be able to say that the first thing that you will look for is the overall look and feel of the data. It should be more or less linear. If you have any nasty patterns like curves or others, parabolic pattern, then you cannot fit a straight line. So the first thing you'll do is a scatter plot. The second thing you will do is, or rather the third thing, the first thing is visual feel for the data by doing a scatter plot. Second thing is correlation coefficient, right? And then you need to look for a regression. And of course, here you need to be very careful which is independent, which is dependent. Then you can, of course, calculate all these things. The most important thing, of course, is the R squared. 87.74 for engineering purposes is very good. And as you can see here, the difference between R squared and R squared adjusted is not very much. So here again, this means that the sample size also is fairly decent. And in fact, the predicted value of oxygen purity, you can actually, so you can see here, when the hydrocarbon content is 1%, what is the, typically that's what people want to know at the end of all this. Somebody will say, okay, you've done the regression. Now tell me, what is the value of Y going to be when X is so much? So that part is easy. You just plug in fact, Alka pointed out, you just, Nisha, I think also had pointed out. You just plug in the value of X in that equation and you'll get some answer, and that is this number. So getting in this fit is that number, 89.23. If you take this particular equation, 74.28 plus 14.95, if you go and put the value of hydrocarbon, you will get this number. You will get this number 89.2. The value add that statistics is able to do is, what is the prediction? So you should be able to say, and these formula have already been given to you. It's a very, shall we say, it's a very boring thing to actually do it by hand. But if you set it up by hand once, you should be able to do it. You should be able to say that the actual oxygen content in upstairs will vary between 86.8 and 91.6. There's a 95% chance that the actual oxygen content, oxygen purity will vary between 86.8 and 90. This is the value add. This is, by the way, the formula for the prediction interval. In fact, I have done it so that you can actually see how it's been done. 2.101 is the T value here. T value for, in fact, oxygen here. How many data points? I think there are 20 data points, right? Yes, there are 20 data points. There are 20 data points. So 20 minus 2 is 18. So if you do for degree of freedom 18, in fact, if you go here, you make it 18. This is basically 2.101. So that's what you got here. 2.101 is the value of the T function. All these numbers, these are all numbers which you will get from the regression table. This is the sigma squared that you've calculated, which is basically sum of squares of error. In fact, whenever you do regression, again, don't be too afraid by all these numbers. I hope you're looking at it here. This big number here, 173.377, is called the sum of squares total. Sum of squares total. And how do you get that? You can actually go here. You can go here and actually check in the oxygen here. You can see it here. Sum of squares total is basically. Can you see here? Can you see this part? This is the actual Y data. By the way, we are interested in Y data, not X data. This data here, which I'm going to now highlight in a light blue color, this is basically the oxygen content, the Y data. So let me put a nice little color here so that you can see it. So here, this set of data has an average. You can see the average here. Now what I've done here is each data point minus average squared. If you sum the whole thing up, you get 173.63769, and that is the sum of squares total which Minitab is reporting. Not prediction for always, or rather, I should be looking at here. 173.377, right? This is what is reported here, 177.377. And what is the sum of square error? Sum of square error is nothing but all the error terms, which is nothing but actual value minus predicted value minus fit. These residuals, if you square the residuals, right, and sum it up, 21.25, 21.249 is 21.25, and that is what you're getting here. And the difference between the two is the sum of squares due to regression. That is how basically the sum of squares are calculated. In fact, the whole of regression is based on partitioning the sum of squares. And this sum of squares error divided by how many data points are there? 20, right? So 20 minus 2 is 18. If you divide 21.250 by 18 and take the square root, you will get this number here, 1.18. You will get this number 1.18, which is being used here. So if you have a little bit of patience, if you have a little bit of patience and can actually work these things out, you should be able to do a good deal of value add in whatever regression you're doing. And as I said, in fact, I'm going to repeat the question again what Alka asked. How do you know if you have done a good job at regression? First thing, A, I have a high R squared. B, I have a high R square adjusted. C, the residuals show no significant patterns. The residuals are truly random. If even one of these is not met, it means the regression is not good. So this is a scientific and engineering example, and this particular example, I'm going to just talk about it. I wanted to look at this. This is again an example from industry, but from the agriculture industry. Again, you're trying to extract a drug from a particular type of nut, and which is always contaminated, and you suspect that amount of fungus and therefore toxin is related to the rainfall of the site. So you're trying to build a prediction equation between the toxin, which is Y, versus rainfall. The methodology is exactly the same, and I want people to be able to, and in fact, I'm going to use this extended thing for multiple linear regression. That will be the final topic that we look at. In fact, it's 1:30 now. I'd like to finish by 2:20 so that there is some time for question and answers. So basically, this is a very good example where you have the toxin, which is the Y. At first, people tried to relate only toxin to rainfall because rainfall was the most important factor. No? So is there an increasing trend between toxin and rain content? Like if sites which receive more rain, are they reporting more toxin content in the nut? The answer is yes. In fact, you can see here toxin versus rainfall. The R value is also pretty high, I think. The R squared is coming to 75.4. So the R value will be a square root of this. It will be a 0.85 or something like that. And you're getting here a coefficient here. So you can see the equation here is 10 point, the toxin is equal to 10.57 plus 6.73 into rainfall, which means if you know the rainfall at a particular place, you can actually calculate the toxin content of the nuts. And then of course, as a value add, you should also be able to calculate the prediction and confidence interval error. So this part you should be fairly familiar. You can just work these two things out. Even in Excel, you can do it. And I'm now going to we talked about model adequacy slightly, and I'm just going to talk about it in a little bit more detail. So model adequacy is basically, many people actually do not actually spend time over this. So assumptions are of course errors. Error, again, it's not a mistake. Error is basically the variation between predicted and actual. That is the error. So errors are randomly and uncorrelated. Mean should be zero. Mean should be zero. And of course, errors are normally distributed. We check that also. Order of the model. If all these things are correct, then you know your residuals should not show any unusual patterns. You can also standardize the residuals. I have not talked about in detail. You can divide each of the residuals by the square root of sigma squared. These are called standardized residuals. They are also called studentized residuals. It will also show you the same thing. And these are the following residual plots that we make, normal probability plots. This you can't do in Excel, but you can do this in Excel. Residuals in time sequence, it can be done. Residuals again, fitted plot. These two also, if you can do it, you should be able to get a fairly good idea. And residuals against independent. Right now we have only one X value. So you plot all the residuals versus the corresponding X values and see if there is any pattern. Are there too many residuals which are positive and very few negative? Means there is a pattern. Ideally, the residuals should be randomly distributed about zero. Approximately half of the residuals should be more than zero. Approximately half should be less than zero. So that's how you check residual plots. And here we have got examples of this. This A is a truly random. You can see this looks random. Here, this looks slightly shaky. Actually, here definitely it's this is definitely shaky because this is a double bow shape. This is truly random, and this is your this clearly means that there is a quadratic term that you've left out. You can see here, this looks like a parabola. Now, what's happening is, let's assume that you are trying to, you don't know what the actual data is. Probably the actual data is quadratic, but you don't know that. What you have done is you have fitted a linear model. Now, what is a residual? Everybody knows what a residual is. Residual is nothing but actual minus predicted. If your actual data has a quadratic term, and when you subtract the predicted value has a linear term. So what happens is you're removing the linear term and the quadratic term is left behind. So if your residuals show a quadratic pattern, it means that the original data also was quadratic in nature. So these are all various considerations by which you check model adequacy, and it's very important. Model adequacy is an extremely important thing. And if you find that you're getting some kind of a shaky pattern like this, then you use these variance stabilizing transformations. You can, one of the best is square root, or the ln stands for natural logarithm, either natural or common log, anything will work. 1 by y, that also works. Of course, this will not work when y values are very close to 0, so that's a minus point. That will also not work when for a logarithmic transformation. So there are some computational difficulties here, but by and large, these transformations work. So that's what it looks like. So the last part is again very important. This is something which everybody forgets, Addition of other regressors may be required. If you're getting a bad thing, and then what you do is you do transformation, you add higher order terms, you do all these things, and still you get terrible residuals. And what it means is you have probably considered a very simplified model. Probably you need more x's in order to explain the model. So addition of other regressors, and that's what the rainfall and toxin is a very interesting example, and we're going to look it up as the last example. This is the model adequacy test for all these examples. For oxygen purity, as you can see here, this looks absolutely random. This is for wages versus Big Mac. Here, of course, if you ask me, this is okay, but I'm not too happy with that, but theek hai, chalega. And toxin versus rainfall, this also looks perfectly. And there are statistical tests for it also. In fact, you can take all the residuals and apply the Anderson-Darling test. If it's normal, then it's normal. So, and then of course the normal probability plot. Too many points should not be far away from. For this, you require, if those of you are interested, you probably need to undergo a course in basic statistics, where we cover probability plotting and your basic measures of variation and your t-tests, ANOVA, and all those basic stuff, then probably this might make more sense. And then this is an example which I talked about in the first half. I'm going to skip this because I want to cover logistic regression before we close. I have another 18 plus 30, 48 minutes. So this is the one which I think Shubhro had asked us questions. So where this is in analytical chemistry, we frequently use Y to predict X. So you start with a set of standards, build up a calibration curve, and use the calibration curve to predict the X value. If you have some basis in analytical chemistry, this should not be too much of a problem. Example is given here. So you can see PABA is some kind of a dreadful chemical. I forget its name. Para-butyl acetate. I forget what it is. Okay. So you can see here when the concentration is so much, you have this number. So this is X and this is Y, and you build up a regression model, and then you rearrange the regression model to make this the subject of the formula. Because if you have a solution which has an unknown quantity of PABA, you measure its absorption, which is easy to measure, and then use this equation to find out how much of PABA it actually contains. In fact, most of your drug testing, right? Analytical chemistry has far more applications that you might care to think. For example, how do you know somebody has taken a dope or not for this sports testing? You take that person's urine sample, and then you run some of these spectra tests through it, And from that data, you try to conclude how much of substance is there in that specimen of bodily fluid that you have drawn. So all of them have immense practical applications. Transformations here. This is yeah, I think I'll very quickly talk about it here. So I'm sorry to go slightly fast. Again, everything hinges on the residual. So here again, there is a very simple. This is again a very interesting, because today we are talking about renewable energy. So wind velocity and the voltage that is coming out from a windmill, right? So this is the wind velocity in miles per hour, and this is the DC output that you get, right? Somebody wants to check, knowing the wind velocity, can I predict what is the voltage? So this is again non-deterministic, because it is not possible to really come up with any equation whereby if you know the wind velocity, you can predict this. So collect the data for every known velocity, see what is the output, and from here, maybe, for example, you don't have the value when it's say 4. Can you see 4 here? 4 is not here. You can 4.1 is here. So if you want to predict the DC output for any value of wind velocity within this range, regression equation is useful. Can people mute their microphones, please? Yeah, thank you. So this again, first step. This again, you can see here. I hope you can see my cursor moving. It's going up and coming down. So it's not as straight as you like to think, even though the R squared is high. Even though the R squared is 87.5. In fact, what is the square root of 0.874? Can somebody tell me? Square root of 0.874 is how much? Anyone? Or people have gone to sleep? What is the square root of 0.874? 874. Yeah, it will be 93. So 0.93 is a very high correlation. Thank you very much. Thank you, Sunita. Thank you. So what I've done here is I've combined both. I've done the regression fitted line plot, so you can straight away get the equation of the line and you can get the R squared. But all of you should be able to get this equation. Can all of you get this equation? Yes or no? How will you do it? I've just shown you, just copy the data and then select those 8 cells. You can either do it in regression option using your analysis tool pack, or select those 8 cells and put linest, and you should be able to get these two numbers, the slope and the intercept. So getting the equation is not a big thing. Getting the equation, any fool can do. The Excel will also report R squared. But the question now is, you now need to look at the residuals. You can see residuals, normal probability plot. Again, it's got a slightly peculiar. This you will not be able to do using Excel, but it is possible using R. This is dangerous. You can see here, it's a very clear it is a non-linear pattern. It may or may not be quadratic. It may or may not be, but you can definitely make out that this is strongly non-linear. It is not random. It's not random. And then again, if you see here versus order, how many residuals are there which are more than 0? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There are 14 residuals more than 0, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10,
So it's
11.
14.
Yeah, 12, 13, 14. And less than, less than 0, 1, 2, 3, 4, 5, 6, 7,
9.
8, 9. So there's a huge difference. So that's why I always tell people, you have to look at the residuals in order to be able to get the complete story. And in fact, this is a very interesting example. It requires a little bit of domain knowledge, but that's not so important for us. In fact, the asymptotic value, you can actually go back and check it. And that actually, therefore, a quadratic relationship is not proposed, because the trouble with a quadratic relationship is if you have a nose up quadratic, that is the nose of the quadratic is going up, means what happens is the value at some point will go up and then it will come down. And that does not match with the shape of the scatter. So therefore, in fact, if you see the scatter plot, that's why I always, you can see here, it's not coming down, it's more or less stabilizing here. So that's why one of the suggestions was, instead of quadratic relationship, you look at reciprocal. So instead of plotting y versus x, plot y versus 1 by x. So all that you need to do is convert the x column to 1 by x column and then do the regression for y and 1 by x. You will get an equation. That equation will be a much better looking equation. And in fact, the residuals for that, you can see here, this looks truly random. If you draw an arbitrary line here, 0, you'll find roughly half the points are going up and down. And what is the ultimate objective of doing all this? The ultimate objective of doing all this is knowing the wind speed, which you can easily measure. How do you measure the wind speed? I mean, just a general knowledge question. Anybody? Okay, I think it's anemometer. I'm not very sure. So the idea of doing regression is, as I said, statistics should always supplement domain knowledge. You measure what is easily measurable and then try to predict something which is not easily measured. So this is a very interesting example. And now we come to logistic regression. I'm going to spend some time here because this is a concept which poses a lot of difficulty to a lot of people. As I said in the first half, logistic regression, the y, that is the dependent variable, has a binary, invariably a binary response. So it is pass or fail, yes or no. Or it has what is called ordinal response. It could be, for example, very good, good, moderate. So it could be categorical. So when you have a response which is of the yes, no, or an ordinal nature, then you need to use logistic regression, and that is where all your simple calculations which you have done so far, or this leanest, finest, they will not work. So these are, of course, device works or does not work, candidate hired, rejected. For example, I had talked about this purchase car and not purchase car. Just for interest, the housing finance companies, I'm talking of mainly developed countries like United States or Western Europe, they actually collect huge population data, huge amounts of data on people's, basically your credit worthiness is an important factor. That is why, there's a lot of fight when credit data is leaked out. So once you know a person's age, weight is of course not very important, age, kind of job, kind of neighborhood he stays, kind of company he works in, kind of education that he had. If you have about 8 or 10 variables, and whether he has a car, again, what kind of car, high-end car, medium car, whether he has an existing loan or not, whether his spouse is working or not, or if you have, say, as much information about a particular person, it is possible to build a model whereby you can predict the probability of that guy repaying the loan. So once you identify candidates with high probability of repaying the loan, you can actually target marketing. You can start chasing those guys and ask them to take loans. So that is the basic principle of logistic regression. And as you can see here, it seeks to establish a relationship between categorically independent variable and one or more variables, all of which may or may not be continuous. The only thing here is, in fact, of course, we are going to look at the simple scale only, binary. We are not going to look at multinomial where you have more than 2 states. We are not going to do that. Or we are not going to look at ordinal variables. Ordinal variables is, where the response is in some kind of order. Like you want to predict whether the service will be very good, moderate, or bad. So where you have 3 levels and where there is a certain ordering happening. And then also logistic regression is used, but we'll not look at those cases. We'll look at 2 very, very simple examples. They're very interesting examples. And I wanted to spend some time on that. So the only thing is, this terrible looking equation here, this comes in here. the E is expected value of Y. Expected value, typically it's in the form of an exponential equation. Instead of just y equal to x plus mx plus c, this is in the form e to the power mx plus c divided by 1 plus that. This is the standard form of the logistic regression. And you can see here two curves like this. And the calculations are it's not possible to do it in Excel. I'm sure future versions will come up with that. So this is what it looks like. E of y is the expected value, and 1 minus e is the one not happening. This is the probability of something happening, and this is the probability of something not happening. So therefore, this quantity is called the odds ratio. And these are typically used also in a lot of your insurance related calculations, the odds ratio. But I don't want to spend too much time on that. I'm going to, this looks a bit flaky, but I'm going to take you to two very simple examples where people try to find answers to simple questions. So you can see, and of course the parameters you need to basically, from the data table that we have, you need to be able to calculate these two numbers. Basically everything depends on calculating this. So these two are calculating using this maximum likelihood method. You will have to take me at face value when I say that it's, I won't say it's very difficult, it's very cumbersome, but we don't want to get into the calculation details. But any reason, in fact, R is very good for these kinds of calculations. For any kind of statistical calculation, R is a very good language, and it's very easy to learn. Okay, have you all heard of the space shuttle called Challenger? Everyone? How many of you say yes or no? In fact, I remember I was doing my, okay, Ramesh says no, probably this, I don't know how old most of you are. In 1986, I was actually in my second year chemical engineering. And I still remember this Challenger. It had, the United States had just sent it up. It blew off. It just within 73 seconds after takeoff, and obviously all 7 people were killed. So that was a big, big slap on the face of the US, because even those days, Russia was still existing as a second power. It had not yet been dismantled. So the United States ended up looking very bad, and they did a very, very thorough inquiry into it. And I would like you people, especially since you are faculty members, I don't know how many of you have heard of the name of Richard Feynman. Anybody has heard of Richard Feynman? Feynman spelled Feynman. Anyone? Yes, no? Very good, Alka. So can you tell me what you have heard about Richard Feynman? Just name anything. Anyone else? Alka has been brave enough to say yes. Anybody else? Anyone else has heard? In fact, Feynman is one of the, shall we say, one of the stars of the 20th century. In fact, he was the most celebrated physicist after Einstein. Extremely celebrated physicist, and a slightly unconventional character also. I'd like to, in fact, I'm going to add this in the book list that I'm going to send you. He also wrote a book, an autobiography called Surely You Are Joking, Mr. Feynman. In the yes, you are right. Field theory. Are you teaching physics by any chance, Alka, Vinayak? Oh, very good, very good, very good. So I'm sure you know the story about how he came up with quantum electrodynamics. Anyway, that'll be too many stories for today. Maybe I'll tell it some other time. But Richard Feynman actually demonstrated to the whole world in a TV show how the O-rings actually failed. So you can actually see that video also. Today in the 21st century, we have access to all these things. We didn't have all these things when we were studying. So the root cause, it is, the failure was caused by the failure of O-ring seals. Basically, when you have two parts which are joined together, typically you have a seal used to prevent leakage of air from outside or from inside. And the O-ring seals were actually failed. The O-ring failed because it was not designed to withstand low temperatures. And the saddest news is failure data of the seals was already available before the launch. It is not that it was discovered later. So you have data here. Data is on before the disaster. 1 means, so you can see here at the temperature 53, 1 means it has failed. 56, yes. 57, yes. And you can see 70, it has 3 times it has failed and once it has not. So with just this data, temperature and failure. So this kind of a model, you will not be able to fit using your SADA linear regression model. It will not fit. You need to fit a logistic regression model, and you will have to take me at face value when I say that. Of course, initial ideas always do a scatter plot. So scatter plot you can see below. So this is 1 and 0. This 1 is fail and 0 is not. So initially you can see that when the temperatures are high, the possibility of failure is low. There are very few, only 2 cases where the temperature was around 70 and it failed. But when the temperatures are to the left of 60, I don't know if you can see this, all have failed. And I'll tell you one more thing. This is the temperature in Fahrenheit. The temperature on the day of the launch, can you guess how much it was? It was 31 degrees Fahrenheit. 31 degrees Fahrenheit, can you tell me? It's 32 degrees Fahrenheit is the melting point of ice. So on the day they had a launch, the temperature outside was sub-zero. Sub-zero means, by sub-zero we mean the centigrade scale. In the Fahrenheit scale, it was 31. So now what people did was they built up a regression equation. Regression equation, you can actually build it up. You can see it here. This is the equation. Y is the probability of failure. Y is the so in a logistic regression, you will find that the left hand side, the subject of the formula is in the probability form, is equal to 1 by 1 plus e to the power minus 10.875 minus 0.1713x, where x is the independent variable, x is the temperature. So therefore, what we have done now is, this is what it looks like. P-value for the temperature is 0.04 simply means that the temperature is a significant predictor. That's what it means. This is what I got from Anytime. You can actually calculate it yourself. At 31 degrees centigrade, the probability of failure is 0.996. There's a 99.6% chance that your ring will fail at 31 degrees Fahrenheit. So the data was available before the challenge. That is the biggest tragedy. That was the biggest tragedy. However, the engineers were unable to utilize this data effectively and present the case against using these O-rings. And O-rings were cheap items. So the entire space program went for a toss because of using some cheap items. So this provides a dramatic case as to why engineers and scientists must have a strong background in statistical techniques. So this is a very classic example. I'm just going to take one more example and then we'll close with multiple regression. Multiple regression, there's some slides, but I'm not going to cover all of them. This is again a very interesting example. As you can see, a sample of 20 families selected to study new automobile purchase. So as you can see in the United States, all these companies, the auto companies, the housing finance companies, loan companies, they all employ hi-fi statisticians to analyze the data that they collect. So the 2 variables of interest predictors is total income and age of oldest car. Now, without doing any statistics, what do you think will be the relationship? The higher the income, the greater the probability of buying the car, or less? The higher the income, the higher the probability of buying the car, or lower the probability of buying a car? Hey, this should not be too difficult. Hi, very good. What about age of oldest car? Very good. Thank you, Ramesh. What about age of oldest car? Let's assume that a family, in fact, most of the middle class families in the United States, and this regression is probably done 15 years ago. Most families, most middle class families have two cars. So husband and wife going to work, and then when the children become bigger, maybe you give them a car also. So most of the families will have two cars or three cars. I'm talking the middle class families. So there are two variables: total income and age of the oldest car. So tell me, the older your car, the more likely you're going to buy a new car, or less likely?
More likely.
Very good. Very good. Thank you very much. So that's why I said, statistics is just a tool. You should also have some common sense in trying to predict and then see what the equation predicts. So now the question is, what is the probability that a family with an income of so much and a car which is 5 years old will purchase a car within the next 6 months? So somebody has done a study here, income here in thousands of dollars, and this is the age of the car. Purchase. 0 means not purchase, 1 means purchase. So this is again binary data. 1 is purchase and 0 is not purchased. So from this data, again, you can build up an equation. Regression equation is e to the power y divided by 1 plus e to the power y. This is the probability. The probability of 1. Probability of 1 meaning the probability of purchase. Because 1 is the event that you're interested in, whether he'll purchase or not. So this is nothing but e to the power y prime by 1 plus e to the power y prime. And y prime is nothing but 7.0 minus 7.05 plus 0.0738 into income plus 0.988. So once you put the numbers in, the predicted probability. So once you, in this equation, if you put income as 45 and age of the car as 5, you will get the probability as 77%. There's a 77% probability that the person will buy a new car within 6 months. And you can see here the confidence interval here also. There is a 95% chance that the actual probability will lie between 38% and 94%. I mean, that is the kind of, it's a slightly higher variability, but you have to live with that. This surface plot again, I don't know if it makes much sense to you. So you can see surface. In fact, you can draw a line when you have one y and one x. But when you have one y, there is a purchase. And purchase again has two values. It's either 1 or 0. But you have two x's, income here and age. So as the age is increasing, see the ordinate is increasing. And as the income is increasing, also the probability is increasing. So the surface plot also makes some sense here. And I'm sorry to go so fast. It's now 2 o'clock. I have 2:07. So I have about 23 minutes left. I'm going to multiple linear regression is probably the last thing that I'm going to cover. Multiple linear regression again is just an extension of the simple linear regression. So it's of this form generally, beta 0 plus beta 1 x1, beta 2 x2, and this is what a typical surface plot and a contour plot looks like. Many people are actually not familiar with, not comfortable with this word contours. Can you tell me in which subject in our good old days when we were students have you seen contour plots? In which subject? Today you find contour plots in statistics, but in the good old days. Okay, Alka, I'm not going to reveal Alka's answer. Alka said an answer. I'm not going to say yes or no. Anybody wants to mention in which subject we looked at contour plots? No, just give me an answer by chat because others should not see that. Okay, Shubhra has also given an answer. Anyone? Okay, the answer is, yeah, anyone wants to say something? It's actually geography. In geography, we have contour plots. We have contour plots, right? So we draw contour plots to to look at different places, and then basically contour plots, if I remember correctly, are used to describe mountains. In fact, same principle is used in statistical analysis in a technique called ridge regression. When you do ridge regression, or when you're looking, in fact, even the terminology used in stats is like mountain climbing. You have two techniques called path of steepest ascent, path of steepest descent. They're all basically the terms are borrowed from geography. So contour simply means, for example, this line here, the one which I'm stressing here. Here, the value is 169. What this means is, at any point along this line, for example, here you see this is x2 as 8, and this is 169. All points along this line will have a value of 169. That's what it means. So typically when you have contour plots are very useful because let's assume, in fact, when we generate contour plots for, typically reaction yield, because I have this chemical background. So typically people are interested in improving yields. And then what people try to do is, they try to change the temperature, try to change this, trying to change that. So when you draw contour plots, you can say that on a particular contour, all the points will have the same value of the dependent variable. And what you do is, so suppose you say, I want a value of my response to be 186. So all points here have 186 as the dependent variable. So if I were to come to this point and drop a perpendicular here, then I'd say this is about, say, 8 point, how much is 8.5. So at x2 equal to 8.5, the corresponding value of, that was x1 here, x2 is also around 8. So you can actually get what conditions of x1 and x2 must be there to give you a particular value of a contour. So these are useful when you start actually applying it. You see the next one, this is the generalized multiple regression equation where you have several x's here. And these are all estimated basically again on the principle of least squares. I have not given the actual algebra here. It requires a little bit of matrix algebra. I don't know how many of you are familiar with that, but it's not very difficult, let me assure you. And the advantage of multiple regression is you can actually take care of quadratic terms, you can take care of interaction terms, you can just build separate columns. Two, you can hold a third column by multiplying these two and use that as a regressor. So all kinds of stuff you can do here. This is again so you can see here, because of this x1, x2 term, the straight lines have all become curved. So these are curved contours. So what this means here is, so suppose so once you generate these contours by doing certain experiments or by doing certain combinations, somebody wants to say, I want to hit a target of 500. For example, you can see here. Where is this? Okay. Let me go back to this others. I'll tell you how to read contours. I hope you can see my cursor. So I want to achieve a target of 500. So you can see it's 519 and 450. So 500 is somewhere in between here. And they say what conditions of x1 and x2 will give me 500. So you just go along the contour. Just go along the contour here. Fix any orbit point and then draw perpendicular to the left and to the bottom. You can say that at those conditions of x1 and x2, you will be able to get a value of 500 for your y. So generating contour plots is actually quite cumbersome, and that is where all statistical software. And how is the contour developed? Contour is developed by the transfer function. And how do you develop the transfer function? The transfer function is actually developed by data. So you collect the data and use any statistical software to generate a transfer function. Then once you have the transfer function, you generate the contours, and from the contours you come up with optimal conditions. That is how people use statistical analysis to work out. So again, here this is completely quadratic because you have quadratic terms here and interaction terms here. These are all I'm somewhat familiar because a lot of my work involves generating these kind of diagrams And generating the diagrams is not important. Anybody can do it. The important part is doing your experiments correctly, or doing your work correctly to make sure that the data which you generate is good. In fact, all of you are probably aware of this term GIGO. Everybody knows the meaning of the word GIGO, G-I-G-O. Everyone has heard of this word GIGO? No? Yes? Very good. Thank you very much. Garbage in, garbage out. So if your basic data that you've, thank you very much. If the basic data that you've collected is bogus data, then all these contour plots, surface plots all won't help you. Why are we doing all this? We are doing all this to basically predict. The idea of this entire regression, many people seem to forget it after seeing all these funny curves. So the step is first carry out your experiments or carry out data generation. Then from there, develop a transfer function, then the contours, and then the idea is to be able to predict what will happen given certain conditions. Typically, people might, marketing people again use a lot of statistics. For example, if you know the sales of a particular item in a particular area, typically they use a lot of demographic variables. It could be, for example, the population density. It could be, for example, the kind of income patterns of the people staying there. It could be the number of schools in a neighborhood. So there could be, in fact, I read a very scholarly paper on this actually was used by an apparel manufacturer to be able to plan the location of his showrooms. So how do you select? Of course, ultimately it comes down to negotiation, how much money you can pay. But on what basis will you select certain areas to sell your product? So what I'm trying to say here basically is everything depends upon the quality of data that you collect. If the quality of data that you collect is bogus, then all these terms, all these things that you generate will also be bogus. So the second order regression model actually is a very, very useful model, and a lot of people use it in industry. This is a slightly theoretical slide, so if you have various models, and I'm going to show you the example of that. If you have various models, like you have a regression module with 3 variables, another with 4 variables, somebody has opted a quadratic model, somebody has used an interaction term. Now everybody wants to show that he's a great statistician. How do you actually check which model is better? So one is, of course, the CP statistic, which I have not measured here, which I have not defined here. CP statistic is a slightly complicated statistic. It measures the total mean square error. Obviously, models with the lower CP statistic is preferred. And the other one is the press statistics. Most of the statistical software will show you press but not CP. Press is nothing but predicted error sum of squares, and this is a very useful concept, and that's why I explain it a bit here. It is defined as the sum of the squares of the differences between each observation yi and the corresponding predicted value based on a model fit to the remaining n-1. It looks like a lot of hogwash. So you suppose you have n data points, right? Out of n data points, leave out one. Leave out the first one. Are all of you listening carefully? You have n data points, leave out the first one, and fit a model to the remaining n-1 points. Okay. Then use that model to predict the value for x1. For x1, you should get a y1 predicted, and you now have the actual value. Now you see the difference between y1 and y2, see the difference and square it. Now leave out y2 and take all the remaining n-1 data points, use the same model, predict y2, and then see the difference. So this is a very, very, very painful way of doing it, and this, I hope people got the gist of what I was trying to do. N-1, yes, it is DOF. N-1 is always the degree of freedom. But here the N-1 is not degree of freedom. Here what I'm trying to say is, I'm trying to explain this in the form of a language, because this is a very important concept. So let's assume you should know what the press does. Even if you don't do the calculation, you should know qualitatively what it does. Let's assume that you have collected some data, you have done some research project, you have calculated some data, and You have given it to 3 people, and 3 people have given you 3 different models. 3 people have given you 3 different models. Which model is the best? Answer, use press statistics. So how it does is, in fact, you can see here, define the sum of the squares of the differences between each observation yi and the corresponding predicted value based on a model fit to the remaining n-1 points. So if you have n points, remove the first one, right? Fit the model with the remaining n-1 points and use that to predict the value for the first data point, and then calculate the difference and keep it aside. Then do it for the second point. Leave out the second data point, take the first, third, and up to n. Again, fit the model, come up with a prediction for the second point, and then calculate the difference and square it. So you will get a sum of squares for a particular model. Do exactly the same thing for model 2 and model 3. That model which gives you the minimum press is the preferred model. But these are very computationally intensive. I'm not sure if everybody understood what I was saying. These are very computationally intensive, and this is where statistical software actually helps. So the press actually provides a measure of how well the model is likely to perform when predicting new data. So the press statistic, so if somebody were to ask you, so I'm always looking at questions that people can ask you after you finish the course, not that I'm going to ask you. If somebody would ask you, what is it that you learned? And in fact, I would like you people to think about that, and I'm going to ask you this at the end of the session. This is the MLR for toxin content. So MLR stands for multiple linear regression. So you can see here, the SLR example, which I didn't do, which I want you people to do by yourself, is toxin relating only to rainfall. But now somebody has actually got other data also, other climatological data. And you can see here, before that, you can look at the data here, which is available in, just take a look at this. So for the first site, the first simple linear regression equation which I would like you people to do is to fit toxin with rain. You can actually do it, come up with an equation. The second set is now toxin with rain, the noon temperature of the place. The sunshine basically is hours of sunshine in a day, hours of sunshine in a day, and wind speed. Obviously, if there is more wind speed, that means moisture will be driven away more. So you expect that the toxin content will come down in a place where there is more wind speed. Ditto for sunshine. If there is more sunshine, there will be more evaporation, hence less moisture, hence less toxin. So there is an equation developed here. You can actually do it in Minitab. In fact, I'm going to let me see, open this. Just a minute. This unfortunately you can't do from Excel, but you can definitely do it in R. File, open. Oh, it's nearly 12:30. I think I'm just going to make it. So ATAL is here. So this is the last Minitab that we're going to open now. MLR toxin versus rainfall. Typically, this is how, okay, save changes, okay, yes. I hope people can see my screen. So you can see here, I'm sorry, for those of you who don't have Minitab, I'm sorry about it, but I'm not really sure how much of multiple regression you can do with Excel, but you can definitely use it. You can use R for that. So you can see what I've done here is the first one, the first regression analysis which I did. All that I did was, just go to stat, and it's a very user-friendly software. You go to regression and then you say fitted line plot, not fit. You go to regression, fit a model, and in the model you say which is the response. Response is the Y that you're interested in, the dependent variable, and continuous predictor is not rain. I think it is the second one actually. This one, this is the one. Yeah. So rain, noon speed, rain, noon temperature, and wind speed. Sunshine also, in fact, here, sunshine, where is this? Sunshine also should be there. Right, it's this one. You can see it talks about rain, noon temperature, sunshine, and wind speed. So all four of them are selected as the regressors. And you're getting some equation here which looks like this. This equation, and you are supposed to take a decision based on the p-value. This part probably you're not aware. So the p-value is basically comes from the concept of hypothesis testing. So wherever the p-value is less than 0.05 and significantly less than 0.05, you will reject the null hypothesis and say that this particular term is constant. So null hypothesis here would be that the constant is not a term in the model. P-value is very low, so you reject the null hypothesis and say constant is significant. Rainfall is also significant. And you can see here, this value is greater than 0.05, 0.142. So you will say that noon temperature is not significant. Then this p-value is very high. So sunshine is also probably not significant. And wind speed is very close to this. So once you do a multiple regression, this is the advantage of using softwares such as R or Minitab. You can select the terms based on the p-values. The p-value concept, actually, many people find it difficult to understand. It's actually very simple. For each of these terms, basically what we are trying to do is trying to find an explanatory model. We are trying to get an equation for the toxin content in terms of all these factors. If we didn't have any predictor, the best predictor is the average. 31.61. So if you take the average of all the data points, you will get 31.61. The average is always the best in terms of if other factors are not significant. What you're now trying to see is rainfall significant? P-value 0.001 means there is a 99.9% chance that you are wrong if you say it is not significant. So there's only a 0.1% chance that rain is not significant. There's only a 0.1% chance. So you'll take that and then you'll say rain is significant. In this case, sunshine, the p-value is very high. There's a 66% chance that sunshine is not significant. So the moment this number is more than 5%, what you will do is you will say it is not significant. So in the first cut, we'll retain constant, we'll retain rain and reject all three. We'll retain wind speed also. And then what we will do is the largest p-value we'll reject. And then we will rerun the regression by dropping sunshine. And that's where you find here, I have dropped sunshine here. And this time you find all the p-values. In fact, they're all less than 0.05. That is rain, noon temperature, and wind speed. All of them are significant. And then we use this transfer function to be able to predict. And it is the prediction that I've done here. You can do prediction in two ways. One is the original equation here, using with just one variable. And you can also run it using your multiple linear equation. And that's what I've done here in this Excel sheet, which I've sent you, but I've not sent you this part. I can send it if you're interested. Toxin versus rainfall. This is using simple linear regression, and this is using multiple linear. So you'll find that at the lower levels of rainfall, there are slight differences between the predicted toxin content. But for higher levels of rainfall, there's virtually no difference. You're predicting 25.4 here, 24.4, you're predicting 24.4 here also. So I'd like to conclude today's session. I know the last few minutes has been slightly intensive, but I want you people to be able to take away certain things. And that is, in a regression, we are trying to explain a y in terms of one x or several x's. And the first and foremost measure of success of a regression is your R square and R square adjusted values. If these are good, then we look at residuals. If the R square and residuals are good, then we say your model is a good predictor. where one of them is not good. In fact, invariably you'll find even though R square is good, the residuals are always the problematic. So there, the options left for us are A, transform the data, B, add new x's. These are the two major techniques that we use to make sure that we stabilize the variance and we are able to get a better grip on the residuals. So if there are any more questions, we have come to 2:30. I think the next session is at 2:45. If there are
Yes.
any quick questions, how can human behavior regression, again, it's very difficult trying to predict human behavior, but yes, there is a lot of regression work done in psychology, and you can actually, I'll send you one more reference. It is by Dan, I forgot that woman's name. Daniel. I'll give you the reference. It's a statistic. In fact, I can tell you right now. Just give me half a minute. You can see in my list of books here. Books. This is on R. Just a minute. Navarro, Learning Statistics with R. This is again a very good book and it's freely available online. You can actually, I'll send you the link to that. So, or you could start learning statistics from Navarro. This is a very, very good book but it's an R. Probably your next instructor will probably talk about it. Anybody else has any questions? Okay. Anybody else? People are happy to leave the program. It's exactly 2:30. You have another 15 minutes or a quick cup of tea or whatever it is that you want to do in this 15-minute break. Anyone else has any questions? Who is it? Anushri now? Anushri and or Ritu. All of you are available at that atal.fdp Gmail, right?
Yes, sir.
Okay, so I'll send you this slides, modified version of slides along with some recommended reading list so you can send it to all the people.
Yes, sir. We will share it.
Yeah. Thank you very much. And it's been very nice speaking to all of you. Any more
Thank you
questions?
so much, sir.
Yes, we will share it. I will share it.
We have. Okay. Yes, sir. Kindly
I
share
will
the
share it.
PPT.
See here, and I will share it about Excel file also. Yeah. Thank you. Thank you very much.
Thank you so much, sir, for your enlightening session.
Thank you
We
very
all
much.
are highly obliged for your presence. I'm certain all of us have gained a lot of immense knowledge from this session. We will love to hear you again in future also.
Oh yes, oh yes. I'll just stop sharing. Maybe I'll show you my face once again before I think all of you can see my face now. So
Yes,
anyway, it's
sir.
been very nice. It's been very nice speaking to all of you. I'm going to send the slides. Take a look at the slides. And if there are any, this is a request to all the people who are still around. If you have any doubts, address all the doubts to one person, either Anushri or Ritu or Neha or anybody. You can collect all the doubts in one document and send it, and I will answer all the questions.
Sure.
That way we can close the loop.
Okay, sir.
Right. Thank you very much. Thank you very much.
Thank you, sir.
Thank you. Thank you. Thank you. I'm unable to get out. Okay, thanks to all.
So someone is writing your background furniture is contour. It's Vikas Verma.
Yes, yes. I can't see that. Who wrote that?
From Vikas Verma. From Mr. Vikas Verma.
Yeah. I also, my dog is not, normally my dog also sits.
Effect of your session is clearly visible in our participants.
Okay, thank you very much, Anushri.
Thank you, sir.
Yeah. Thanks to everybody who stayed awake.
Thank you, everyone. You all may have received few attachments for next session on your Google group as well as your WhatsApp group. Please keep that attachments with you for next session. We will continue our next session on data science using R by Dr. Ashish from IIIT Delhi, Gandhinagar, IIIT Gandhinagar at 2:45 p.m. So please be there on time. Thank you.
Hello, yes, sir. Yes, sir. Sir, I can see you, but I am not able to make you the panelist. Sir, yesterday also we had the same problem with Dr. Jignesh. He is also from the same institute, right, sir? Oh, okay. So, sir, that's why I'm now familiar with this problem because what happens, there is, I think, some issue with the ID or something, I don't know. So, what, sir, we can do is, I will tell you another ID to join. Abhi to you have used your own ID, na? Like the email address. So, sir, just use some like other email address. I'm just telling you because otherwise you'll that was the same thing that sir was telling yesterday. So sir, please, we need to. लेकिन कल तो yesterday sir, we it took half an hour. Good afternoon, all the participants, and the speaker for the third session, Dr. Ashish, he has already joined, and we'll be just starting with the session in another 2-3 minutes, sharp 2:45. So this session will be hosted by Miss Dr. Monica, and she is also here among us. So carrying forward to Dr. Monica.
Thank you, ma'am. Good afternoon, sir.
Good afternoon. Am I audible?
Yes, sir, you are audible. Shall we start the session?
Yeah, if participants are there, I'm available. Or are we
Okay, I
expecting some
the
more?
participants have joined.
Okay, sure.
So I welcome all the participants in this third session of day 4, and it will be presented by Dr. Ashish from IIIT Gandhinagar. The session will be all about the data sciences using R. I hope all of you have downloaded the R scripts provided to you on your WhatsApp group. Okay. I welcome you, sir, on the behalf of Indira Gandhi Delhi Technological University for Women, New Delhi, and entire team of ATAL sponsored FDP on data sciences.
Okay.
Before starting, let me introduce you, Mr. Dr. Ashish. Dr. Ashish Fofalia is currently working as an assistant professor at Indian Institute of Information Technology, Vadodara since 2016. He holds PhD and MTech degree from AICTE, Gandhinagar in 2016 and 2010 respectively, and BE in Computer Science and Engineering from Rajasthan University in 2008. He has been working on the medical image processing and analysis using machine learning approaches. Thank you, sir, for joining us.
Yeah, thank you for
Sir,
the introduction. Yeah. So may I start now?
yes, sir.
Okay.
Yes.
So let me share my screen first. I hope it is visible to all of the participants. Hello, is my screen is visible?
Yes, sir, your screen is visible.
Okay. Hello participants. I hope you have downloaded R and R Studio and you can see the screen. Anyone, any issues with the installation before we go ahead? You can have it on MacBook. You have to make sure that you are downloading a correct version for R. There are different versions available for Mac and Windows. Anyone, any other issue? Okay, so let me just briefly introduce what is R. So R is a programming language which is more like a DOS framework. So if you simply install R, it will be give you the feeling of the DOS system, which was like one of the oldest system over there. And this R Studio is a development environment where you have a good uh, maybe a GUI for writing a code and looking at all the variables, plots, and everything. Okay, so this is like a you have to install R as a base, and then on the top of that there is a R Studio which will give you a nice interface or environment to do the coding and everything. Okay, so this is if you see my screen, this is a basic R Studio environment where screen is divided into 4 panels. This is your code part where you can write your code or scripts, R scripts. On the bottom, this is a console where you can execute the command. So R is essentially a interpretable kind of language. On the right side top, this is environment variables where you can see all the variables, their details. If you click, you will see all the values over there. And on the bottom side, there are couple of options available to you where you can see all the files which are there. Then you have some plots. This is a window where we will see some plots we are going to discuss right now. These are the packages, different utility packages available in R, which are downloaded. So those which are downloaded are tick marked over here. So these are downloaded in my machine. So they are tick marked. If you need some other support, you can just click on the package over here and you click on the install. And if you want to update, you can just click over here. So they will be automatically downloaded in your machine. Then this is a help file and then view file. So in the packages, you can go into any package and you can see the details inside those packages. Okay, so over here you can see the first one is user library. So these are the user library packages and these are the system library packages. Okay, some are default installed and few you can require at the time of working over here. One of the most useful for those who are beginners with R, there are few inbuilt packages which are there in the datasets. So there is a package called datasets. You click over here, you will see basic datasets available in the R. Okay, so you can directly use all those datasets. So these are the datasets. So starting from A, so these are the A datasets, then B, C, and so on. Okay, and you can get to know the information about the data set by clicking on any data. So like if I want to see what this hair eye color data set looks like, so this is a description of the data, the name, and what are the entities over there. Okay, so this is a format is 3-dimensional array over here, which has 592 observations on 3 variables. Okay, So three variables are essentially our features. So here I and sex is a feature, and then each feature have these four values. So this is like a categorical data set where hair color can be black, brown, red, blonde, and similarly eye and sex. Okay, so this is a categorical data set, and these are the sources and references. Okay, another data set you can click anywhere like empty cards, which we are going to use in the hands-on session. So this data description is here, and that data collected from 1973 to 74 with 32 automobiles. Okay, so 32 observations are there, and this has 11 numerical variables. So all these 11 features are numeric in nature, so they are values actually, and these are the feature name. MPG, which stands for miles in US per gallon. CYL is number of cylinder in automobile, so 2, 4, 6. Then displacement, gross horsepower, rear axle ratio, weight, QSEC. So all the descriptions are there for each and every feature, and then the source of data collected over here. Okay, so if you click, so this data set package is already installed in my machine. Okay, you can see over here this one. So this package is installed in my machine. If it is, you can check in your machine. If it is not there, you just click this and install. This will be done in your machine. Otherwise, what you can do is you can just write on your console install dot packages. Okay, so if you want any package which is not there, you just click on install dot packages and give the name. It will be installed in your machine. So let's see how empty cards data look like. So simply just give few stacking characters. It will give you the help over here, and then you can just press enter. You can see the observations over here on the console itself. So this is the first observation, which is automobile Mazda R4, R cross 4 or RX4, which has MPG value as 21.0, number of cylinder is 6, displacement value is 160.0, horsepower is 110, D-rate feature is 3.9, weight is 2.62, QSEC is 11.46, and then these are the remaining 32 observations, and then remaining 4 features over here. Okay, so this is how a data set looks like. So you can click on the your package data sets, and then you can see which data set you want to work with and what are the details are available in the data sets. So before going ahead in any experiment or hands-on, you have to be have a better idea how your data looks like, or what are the attributes of your data, what are the features. So over here there are 11 features, and what we want to do is most of the time we use this data set for making a prediction that given the remaining 10 features, what is going to be the miles per gallon for incoming test data. Okay, so we want to predict MPG value or over here, and see whether your data is numerical in nature, is a categorical in nature, or it is continuous in nature. So there are different methodologies depending on your nature of the data that you are going to deal with. Okay, so looking at the data is the first thing that you should make a practice, that look at the data, how your observations are looks like, and what are the features stands for. Okay, similarly there is another package called mass, MASS. This is another library which has another set of data sets where you can work with. Okay, if it is not installed, you can install in your machines if you require some different data sets. And for all those things, there are lots of R blocks available where you can get to know which data set is suitable for which application. And similarly, there is some time series data sets available where you can see the change in the time for some particular value. So those time series data sets available, they require a different handling of the data altogether. So these are the complete list of datasets in dataset package. Then you can have different packages like mass, and there are few different packages available which you can try out. So you can see over here there are Titanic dataset, which is for survival of passengers on the Titanic. Okay, and then you just click, so you will see the description that this is 4-dimensional array from 2201 observations. Okay, so these many samples are there, and there are 4 features. Okay, and then again the labels for here are the class has like first class, a passenger was a first class passenger, or a second class passenger, third class passenger, or a crew member. Okay, so these are the people who were there on the Titanic ship when incident took place. Then whether they were male or female, that is another feature. Then another classification or feature is age, whether the person was child or adult, passenger was child or adult, and then whether a passenger survived or not, yes or no. Okay, so this is essentially another categorical data where we can see how many have survived from first class passenger, how many survived from crew members, or how many adults survive, how many females survive, how many males survive. So all kind of questions you can look from the data. Okay, and then we will use this data set also in our work. So these are the just an overview how your data looks like. Okay, any query so far before we go ahead? Anyone, if one or two quick query? Okay, so now let's move ahead, and we will be mainly talking about the visualization, where in data science, visualization is one of the essential component considered now these days, where this gives more insights by looking at your data. Okay, and there is already a phrase that a picture is more than worth of 1,000 words. Okay, so by looking at the pictures or about the data, this will give more insights how data looks like and what attributes we can derive, or what are the possible analytics that we can do on the data. Okay, so I'll give you in the session overview to some of the well-known visualization techniques, okay, that we have done from the school level mathematics to some updated visualization techniques, okay, which can be used depending on the type of data that is available to us. Okay, so starting with the first technique, which is you can see, I hope you can see, and at the same time I have shared the similar script with the organizers and may be available too at your end, so you can run in parallel with me just to see how things are working. Okay, so if you need more help, you can refer this one. This is a nice online book available by Professor Rob Backoff. This is written for data visualization techniques in R. Okay, so this is the link. You can take a look, and it's freely available. Let's go ahead. In R, we can declare an array by C. So C stands for declaring an array. So I'm just creating a array X which has few random values which I have taken, like 15, 14, 12, 56, 87, 93, and so on. Okay, and then the first very simple technique is to plot a histogram. We have plot histogram in our school level mathematics also, to see how data looks like and spread is there and everything. Okay, so histogram is one of the simplest technique which gives you the distribution actually of the data. So like the major parameter over here is a bin, which is a bin is over here is 20. So our data is divided into 5 buckets kind of bins, and then each bin stands from 0 to 20. So distribution gives a frequency of values or sample values which are falling in the range of 0 to 20, and then there is like no value in between 20 to 40 bin, and then so on. Okay, so histogram is very simple, which gives you a nice idea that how our data looks like. And then bin size is one of the parameters that you can play with over here, which will give you some distribution of the data. Okay, bigger or larger the bin size may not give you much idea about the data. So right now this is a very small data X, which has almost 10 or 12 values, and just to represent over here. The second plot is called stem and leaf plot. Okay, this one is similar to histogram, but it has a different structure where we call we divide the number into the face value and the place value. So stem is something which is like a face value, sorry, place value, and then leaf is the value. So like 50 is like 10 plus 5. So my stem I can make as a 10, and 5 will be my leaf. Okay, so simply by on this line, if I make a run, so this is my values look like. Okay, and then you can change the stem over here. So over here, stem is considered by values of 2 digits, 0 and 1 as a one stem, 2 and 3 as one stem, 3 then 4 and 5, then 6 and 7, and so on. Okay, so my values like 12, 14, 15 are represented as 2, 4, 5. Okay, so the left side is a stem 0, 2, 4, 6, 8. Right side is a leaves. Okay, and this represents 2 simple represents 12 over here, then 4 represents 14 over here. Okay, so this also gives idea how our data looks like. Then the third one is a plot, simple plot function, which will give you the values in a scatter way. Okay, what are the actual values? So with respect to index, this is right now one dimensional array. So with respect to index positions, so what are the actual values? So these are the values which are represented in a circle. Next one is called box plot, which is also called as 5-point summary. So summary, 5-point summary means it will give you median value. It is looking for 25th quantile. It is looking for 75th quantile, and the max and mean value. Okay, so let me run this one. So this is how a box plot looks like. So this one is a bottom bar, represents the lowest value in the data set. This one, upper one, is representing the highest value. These dotted lines are called whiskers. Okay, whiskers, which given by the name of inventors. This middle line is representing the middle value or median value. Okay, this one is 25th quantile value in the data. This one represents the 75th quantile in the data. Okay, so essentially our data is divided into 4 parts, and each part is containing 25% of the data. Okay, so this one is from the minimum to 25th is 25% of our data. Then middle value, this dark middle line to the 25th is another 25%. This is third 25%, and this is the fourth 25% of our data. Okay, right now somehow data is quite separate, well separated, like it look like equal in area. Otherwise, you depending on the partition area, you can see whether your data is very dense in some region or in some quarter, or it is more spread. So depending, it will be keep on changing. Okay, so these are the 4 basic plots that we have seen. And another one in the box plot, what we can have is called interquartile range, IQR, which is defined as 1.5 times the difference between 75th and 25th quantile. Okay, So instead of looking at always minimum and maximum, we look for IQR and then we use the whiskers to find out what are the data which are close enough and what are the outliers. Okay, so some of the data you may feel that data is outlier, which means that it does not follow or closely to the other samples that are available with us. Okay, so let's look at the box plot on one data set called empty cards, which is MPG value and cycle. So this is a representation. We will be plotting this box plot for MPG values and against the cylinder values. Okay, data set we are going to use is empty cards. On x-axis, we'll be representing number of cylinders which are there. Then on y-axis, what are the MPG values? Okay, so let me plot this one. So is it visible, everyone, or I should zoom it? Okay, so in our data set, if you take a relook on the empty cards data set, this one, so number of cylinders are 4, 6, and 8, and then this graph is constructed in such a way that for 4 number of cylinders, what are the MPG values available over here, and then you can see like again data is divided into 4 equal parts depending on the quantile values. So the data is more close over here from minimum to 25th. So it's more dense as compared to the third to fourth quantile or 75th to the max value in the data set. So that is how, by looking at the spread, we can get to know how data is concentrated. Similarly, this is MPG values over here in the automobiles where number of cylinders are 6 only, and similarly this is the MPG values for number of cylinders available are 8 in automobile. Now here is the outlier data which is highlighted behind the whiskers. Okay, so this is called lower whisker and this is called upper whisker, and outlier can be at any side in your data set. Okay, so what essentially we do is we take the 1.5 times of interquantile range, which is IQR, which is based on difference between the 75th quantile value to 25th quantile value. Okay, and then you take 1.5 times. Okay, and then if your minimum value or any value which goes beyond this IQR range from either side, that will be considered as outlier. Okay, so this is represented as an outlier in our data set. Okay, so what that represents is for number of cylinders or number of samples that we have, having a number of cylinder as 8, most of the values are lying close to 15 to 20. Okay, and this is one example where number of values are like 11. So this, given the sample, this is considered as an outlier to the to us. So this is how it represented separately over here. Okay, any query, anyone so far, or we are good to go ahead? Okay, so this is a few basic plots which are available in the inbuilt R. Okay, and then let's look at one of the important library which is called as ggplot2 library in R. Okay, so those who are new to R, they can install this ggplot2 library on their console. So what you can do is either you can go to the packages over here, and then you can check whether it is installed by default or not in your user library packages. Okay, so right now, like there is a tick mark available on over here, so it is installed in my machine. Okay, so ggplot library contains most of the plots available in R, which you can directly use. Okay, so for using any library, so first thing you have to install. So install, either you use on console install.packages and then library name. Okay, once it is installed, you use a library command over here like this one, and then give the name of library, and all the functions available in that package will be available to you for access. Okay, and it creates a ggplot object and will show display on the screen. Okay, so now let's look at the histogram using ggplot library. So we are using iris dataset over here. So this is a simple plot which is called as ggplot. On the x-axis, we are going to use iris dataset with sepal length attribute. Okay, so again, if you wish to see how dataset looks like, you can again go to datasets, and then you can take a look how your dataset looks like. So iris dataset is one of the oldest dataset that been used, and we use most of the time in our machine learning work. So iris dataset is a collection of 50 flower in 3 different categories. So essentially 150 samples that we have, and the samples are having attributes which are called sepal length, sepal width, petal length, and petal width. Okay, so these are the 4 features that 3 species are being classified out of 150, and each class is having 50 samples over there. Okay, so this is the basic description of iris dataset. And now in histogram, we are plotting a histogram for sepal length attribute. Okay, so what is the sepal length of all the 150 observation? Okay, so this is a description, and then it creates using genome histogram function, geometric underscore histogram function. Okay, and there are other attributes available. I'll not be going much into detail, but those who are interested, they can again go to online library for the help, and then you can see all other attributes for beautifying your graphs. And this is giving a title and x-axis values over here. So let me run over here. Just you select all the lines over here, and then you just click on the run. Okay, so there is a warning you can ignore. So this is how your histogram looks like for the sample length for 150 samples. Okay, the same histogram that we plotted over here. Okay, so similarly, let me try like hist iris $sign is to represent uh, the features available in your dataset. Okay, so you can just select directly and then you can place. So this is how with default bin size it will be looks like this one. Okay, if you reduce the bin size, you will get more backend histogram like this one. Okay, now the next one is called density plot, where instead of histogram, we want to see a continuous curve. Okay, so this is we call as a discrete in nature sometimes, and let's see how continuous looks like. So over here, I have generated random samples using rnorm function, which is random number generator function for normal distribution. So that is a rnorm function. Over here, the first is number of samples that we want to generate. So over here, it is 1 lakh. Then it is mean, and then standard deviation. Okay, so rnorm function is over here. So by default, if you simply give rnorm, it will be mean 0 and standard deviation 1. But we are specifying mean value as 6, standard deviation as 2. Okay, so this is one dimensional array will be created. Similarly, in the second, we are creating another normal variable random sample of 50,000 values, and mean is 7, standard deviation is 2.5. Now in R, your data set is defined to be a data frame. Okay, data frame is like a tabular representation. Those which are inbuilt data set are actually in the tabular form, and if you want to create some data set like this one, you use a frame concept provided by R that is called data.frame. So this will create a data frame, and its name is given as caret, and the second one is called as cube. and then these are going to be served as two attributes for our data like wedge. So I'm creating a data set which is wedge, and wedge has two attributes, caret and cube. Okay, so these are the two attributes we are going to have. So let me run this part of code, and then I'm creating a variable, a data set which is called wedge. Okay, and you can also see by typing wedge on the console. Okay, so you can type wedge on the console. Let me change. So okay, so sorry, here is going to be a binding to our data set. Okay, so now we are going to bind this one over here. Now we are going to do using ggplot, and then we are using geom underscore density function over here, which will give a joint density distribution of our two features, caret and cube. Okay, so these are the two joint densities. You can see how data is distributed together, because histogram will be giving you detail about only one feature at a time. So by looking at joint density, you can see different multiple features together, how they are distributed. Are there overlap, or are there they are disjoint completely? Okay, anything like that. So let me just change the parameter values on line number 24. So let's rerun this one. Sorry. Now you can see data is a bit more separated. Okay, and if you reduce the variance, which is sorry, standard deviation, then it will be more separated data. Okay, so this is like two well separated data which are there. So by looking at all the visualizations, that they give more insights instead of looking like there are 1.5 lakhs samples we have. So instead of looking at each and every sample, we can quickly take a look how it is going to be distributed. Okay, and then if you look at the density function or histogram, they will give you insights what kind of distribution your data follows, and then you can apply suitable mathematical properties from those distributions. Okay, so if we say my data is going to follow Gaussian distribution by looking at this figure, then you can use the properties of Gaussian distribution which we study in mathematics and probability, that always you can apply to analyze further properties of your data. Okay, now let's move to the next plot, which is called pointile plot. Okay, so this is pointile, which is in short called as QQ plot. This quantile is depending on the data, how much quantile that we define. Okay, so over here there is a function called QQ plot over here, and what we are using over here is a tree data set. So this tree I can show you here. So this has 31 observations, okay, and there are three features: width, height, volume. Okay, so you can access all the three features like this one: increase width, okay, and increase height. So we want to see how the quantiles of these two attributes are distributed in the data. Okay, so in the tree data set, we are looking at two variables all at a time. Okay, so let me run the QQ plot. Sorry. Okay, so this is called quantile plot between the width and height in the tree data set. Okay, so like how many data falls below this one and how many falls based on the quantile. So you can see a relationship like this one. If you want to find a regression analysis, if you want to perform regression on these two attributes, you can see there is a straight line you can plot between these two. Okay, so there is a correlation exists between these two by looking at the spread of sample. Okay, so they are following kind of a linear pattern vertically with positive angle. Okay, similarly you can plot a QQ plot for width and volume, which is like this one. Okay, then you can have between the other two like this one. Okay, so again, looking at the QQ plot, you can also see if there are any outliers present or not. So like your data, if you look at this point on the right side top, it is completely outlier than the other values which are concentrated on the downside. Okay, and then if you see your data over here for these two features is closely connected over here. Okay, so based on the quantile values, we can look at again different angle of the data. And sometimes to check whether our data actually follows a normal or not, what we can do is we can use a QQ norm function. QQ norm is again a quantile with standard normal function. Okay, so QQ stands for quantile and norm stands for normal distribution. So I have generated a vector which is just 1 to 100. Okay, it is 1 to 100. You can just see incremented by 1. Okay, and then we are going to check whether this data X is following standard normal distribution or not. Okay. Okay, so this is how on the x-axis you will see there is a theoretical quantiles, which is it stands for standard normal from range of -3 to +3. Okay, and then how our sample quantile on the y-axis you will see sample quantile. So how our values are spread. Okay, again this is equal in proportion. So this you can say there is a straight line we can have if we go for a regression analysis, and somewhat our data follows a linear model over there. So using QQ norm, you can check whether your data is following the normal distribution or not. Okay, because sometimes we blindly assume that our data is following normal distribution. Okay, but you can first you can verify that whether it is actually following or not by looking at this kind of visualizations. Then let's move to the next one, uh, which is called violin plot, which is actually resembling the violin instrument. Okay, what happens because in histogram and density we do not get much insights if we want to see multiple features at the same time. Okay, so you can have one or two at a time, and then you may not have all together. So what this violin plot does is it based on the feature, it gives for each and every feature a density plot. Okay, let me show you this one. So these are the some pre-processing that we have to do to make a data frame for plot a violin plot using ggplot2 library only. Okay, and there is a function available called geom_violin. Okay, so this is how violin plot looks like. I hope it is visible on screen. So for the tree data set, this is the first feature grid, second feature height, third feature volume. Okay, and this gives density plot, and it is mirror on the y-axis. Okay, so this is one density plot for the feature, and then it is mirror over here. Similarly for this one, that it is actual distribution of the data, and then it is mirror image just to give you a nice shape of the structure. And then similarly the volume, which is by looking at this we can say it has more spread than any other feature in the data set, because this long tail on the top side shows very small values are available present in the data set. So this gives density plots together for all the features at a time. Okay, so by looking at the violin plot, you can see how your data looks like with respect to each and every attribute or each and every feature available in the data set. So this will be more helpful by and for analyzing whether our attribute or feature follows some particular distribution, Gaussian or left tail or right tail or uniform distribution, or there are bimodal, unimodal or trimodal kind of thing. Okay, so this kind of analysis we can always make or by looking at the Voilin plot. So this will be helpful on such cases. Okay. Anyone, any queries over here so far? Okay. Meanwhile, there are few queries that how to run R in Colab. I have not tried R in Colab, but there are help available. Or if you want, I can share by tomorrow how it can be run. But there are possibilities that in Colab we can run R code. Okay. Meanwhile, any other query? Okay, let's go ahead. So this was a Voilin plot, the last one. Let's see another plot, which is called mosaic plot, which is useful most of the time when you have a categorical data, where your data has a category. Okay, so over here, this ggplot has a function called ggmosaic plot for mosaic plot. But most of the time, what I have seen is the people use a VCD library to have a mosaic plot. Okay, so you can just install a VCD library by just clicking on the data package over here on the right side, or you just type on the console install your packages and then you give VCD. Okay, so right in my machine it is already installed. So this is another library for visualization. So one of the simple one, if you need a time for installing VCD library, I can wait before going ahead. Anyone, if can reply me quickly. These installations will be like can be done in couple of minutes, so we can wait here. Anyone, if facing any problem in installation or running the codes, anyone meanwhile? Okay, so let's move to mosaic plot. So in case of mosaic, we have to give features which are added like a plus sign. So for mosaic function in VCD library, it is a tilted sign, then feature values class plus x plus age, and dataset we are going to use is Titanic. Okay, so for my machine, it is already installed the mosaic library. So let me run a library VCD and then you can run this code. Okay, so let me zoom it. Is it visible? Anyone can quickly confirm? Is mosaic plot visible after zooming it?
So there is no plot visible.
Okay, yeah, let me just check. Is it visible on my screen on the right side panel? Is it visible on right side? Okay, so in Titanic dataset, we have 4 features, but for plotting right now, we have used 3 features. So, hello.
I'm saying it is visible now, so.
Okay, yeah, thank you. Okay, so what Mosaic does is it divides the axis. So like we have first feature as class, which is over here on the y-axis class, and it has 4 categories. If you remember, so first class, second class, third class, or crew members. So passengers were divided into 4 categories. So over here. Now, second feature we had sex, whether it is male or female. So on the vertical side, you can see it is whether passenger is male or female. And then third feature we have used is age. So age is on this side, on the right side. And again, age has 2 categories, whether passenger is adult or child. So it is divided over here. Now, try to understand in mosaic plot, uh, the area of rectangle gives you proportionate idea of distribution of your samples. Okay, this is your like sample is like in category. Like first observation is a person is or passenger is second class passenger, is a male and is an adult. Okay, so now you can see it will be like over here. Passenger is second class, passenger is male, and passenger is adult over here. Okay. Similarly, this on the right side will be passenger is second class, passenger is female and adult. Okay. So it is divided like this way. So first we had a first feature which is class. So our area is divided based on the class. So first class, second class, third class, fourth, and crew member. Then male or female, and then adult or child. So every class is now divided like this portion on the top is the first class passenger which are male and child, this one. So you can see there is no sample kind of observation. So there is no observation which is a first class male and child, and there is similarly no passenger in the first class which is child, who is child. Okay. Similarly, you can see the child passenger, male child passenger in second class are lesser than female child passenger in second class over here. Similarly, in the crew, you can see there is no child male or female passenger. And if you look at overall graph or area of rectangles, you can see the highest number of passengers on the ship at the time of incidence was the crew members who were male and adult. Okay, so that number is the highest present on the ship on the day of incident. Okay, and similarly you can see like number of first class passenger male and female adult were almost equal, because like looking at these two rectangle areas, so they are more or less same. Okay, similarly number of female crew passengers were quite less over here in the adult category. So looking at this kind of graphs, we can derive all such conclusions by looking at the mosaic plot. Okay. Similarly, the next line, you can change the axis. Like over here, you can change the order of features. Like over here, now in the line number 65, I have done with sex, then class, then survive, and then age. Okay, so now I'm using all the 4 sides. Now, so over here, your data will be divided first as male and female, then it will be divided based on the class, then it will be divided based on survive, whether they survive, yes or no, and then the age, whether they are adult or child. Okay, so these are the situations. Like you can see the large number of passengers which were not able to survive were the crew members, male over here, and they were adult. Okay, so this is how breakup is there. And then you can derive other similar responses by looking at yes or no over here on the survive side. Similarly, this one is for female passengers who survive from the first class. Okay, so this is first class category passengers from the female who were able to survive. Okay, so this is the second example. Similarly, we can use another data set which is based on UCB admissions. So this is University of California, Berkeley data set for admission, and this is inbuilt data set available. And then we can see based on department and Zenger and admission who joined which department. Okay. So this is how the features are. Okay, department, there are 6 department A, B, C, D, E, F, and then whether a person got admitted in department XYZ or rejected, and the proportion of male and female over there. Okay, so these 3 features are there. So you can see like a blue color were the male candidates who got admission in the department A, and the pink color were department A rejected male candidates. Similarly, for female, the blue color is more compared to admission than the rejected candidates. Similarly, if you look together, the number of candidates admitted is more in department A than any other department. Okay, so that can be another inference that we can derive. And similarly, number of candidates rejected were more in case of department F, whether male or female. Okay, or number of candidates got admitted in department F is the least among all the 6 departments. Okay, so these are the few observations that we can keep on deriving. Using the mosaic plot, given your data is categorical in nature. Okay, but the drawback of this visualization is that if you go with more than 4, this breakups will become more clumsy and you won't be able to get more detailed insights, and it will not serve the purpose. Okay, so that is another limitation that we can work with. Now, going ahead with another plot. So there are 3D scatter plot which is available in library RGL. Okay, so if it is not installed, again you can install library using install.packages and RGL library. Over there, you can see 3D plots of the data set. So again, I'm using this RGL library and then 3D plot. Okay, so it is not installed on my machine also. So let me just install quickly. Okay, so now let me run this one. And then you can see a 3D plot. Is 3D plot visible, everyone? Or can you run on your machine and then you can see? One is saying no, one is saying yes. Third one, any response from third participant? So this 3D plot can help you to understand your data by looking at the 3D with 3 dimensions. Okay, so you can just keep on rotating and you can see how your data is distributed in 3D, and you can find out the outliers or some separation, which can be like a hyperplane. You can zoom in, zoom out, and you can see separating hyperplanes. If we talk about machine learning classifications, then you can see if there exists a linear hyperplane to classify or non-linear hyperplane possible some kind of things. So that way 3D Geika points will help you to visualize how Geika looks like by looking at three features simultaneously. Okay. Otherwise, you can do a simple 2D plot that will give you a 2D plane over there. Okay, the next plot similarly for the tree Geika set where you can see how your it is distributed. And even in 3D, you can see some outlier Geika sets. So if you look at over here, one point uh, in your screen also, if it is not visible on my machine, you can see on your screen. One sample you will see at one of the very far corner from the rest of the sample. So you can clearly see that one sample will be outlier in your data set. Okay, so that way we can do some analysis how to, or you can explicitly remove, or you can apply some techniques to remove such kind of outliers, and then you can see again how your data is concentrated or distributed in the 3D space. Okay, or can you have one hyperplane which can be classifying the data into two classes or multiple classes and so on. So similarly for 3D, there is a 2D plots which can be more helpful, okay, by adding more attributes over there. Okay, so ggplot library supports some additional functionalities where by in parallel to looking at the scatter plot, we can have a relationship between the features. Okay, whether there are dependent features, there are independent features, or what is the correlation between the data among the features, whether features are related, correlated or not, like that. Okay, so this is one example of from empty cards dataset. Okay, where we have four features: MPG, displacement, drag, and weight feature. Okay, and now this is called scatter plot matrix. Like this one is a matrix representation. We have considered four features, so it is 4 cross 4. Now the first one, the first row second column is a graph, scatter graph between MPG and displacement. So MPG on y-axis and displacement on x-axis, and this is the distribution. Okay, similarly the first row third column is MPG feature on y-axis and drag feature on the x-axis, and the last one in the first row is MPG versus weight. Okay, so you can see how MPG values are changing with respect to displacement feature, then drag feature, then weight feature. Similarly, it's a flip over here. And the second row, first one is MPG versus displacement. Now MPG on x-axis and displacement is on y-axis. Then second row, third column is displacement versus drag, and then the last one is displacement versus weight. Okay, so this is how you can see how data is scattered with respect to features. Okay, and you can have more number of features if you have, and you can see a matrix, and then you can see a correlation whether data follows a simple some kind of positive line or negative slope line, or it is simply a random distribution between two features. Okay, so that will give you there is no correlation exists between those particular two features. Okay, so for having so this one is very simple. So I have used another library which is Psych library, which gives more information that we can plot on the graphs. Okay, so this one is what you can see the distribution on iris dataset. So this is values are correlation values. The first one is called sepal length, which is a histogram and plotted with the density curve of the sepal length. Then similarly sepal width in the second row second column is a histogram with density. Third one is speckle length with histogram density. Fourth one speckle width, and then this one is a correlation. The minus 0.12 is the correlation coefficient between sepal length and sepal width. Okay. Similarly, 0.87 is the correlation value between sepal length and speckle length. 0.82 is the correlation between sepal length and speckle width. Okay. Similarly, speckle length and speckle width, you can see a correlation is 0.96. which is very much visible by looking at the scatter plot in the row number 4, column number 3. Okay, so you can see your data is almost aligned in a straight line. Okay, so that's why your correlation coefficient is very close to 1, 0.96. Okay, so this kind of informations you can quickly add, and you can also see the individual histogram on the same time. So you can see your sepal length is having some kind of uniform distribution, but sepal width can more have a Gaussian, but petal length has a bimodal distribution. Bimodal means there are two peaks you can see in your data. Similarly, petal width is more like a bimodal. Okay, so this kind of analysis you can derive directly by adding more informations in your graph. Okay, or more justifications we can get by looking at the data. Anyone, any queries so far? Maybe quick couple of queries I can take. Or any issues by running the course or your side? Okay, let's move to the next technique, which is called a parallel coordinate plot. So what it means is we can plot all the features parallelly and we can see how values are distributed. So this is called parallel coordinate plot. This is available in GGLA library. If not installed, you can install GGLA library, and I'll show you again on the empty cards dataset where there is this library has a function called GG pair chord function. Okay, and then you give the data, which is empty cards over here, and right now it has 11 columns, so we are using all the 11 columns for representation. Okay, so let me run this one. Okay, so it maybe looks like very clumsy right now, but let me just highlight this one. Now, this is right now is parallel coordinates where on the x-axis you will see variables or which are our features. So MPG was one feature, cylinder is one another feature, displacement is feature, horsepower is a feature, and so on. Okay, on y-axis you will see right now by default this is standardized data. So all the values are standardized in the range of -3 to +3 or standard normal data that has been converted. Okay, so instead of using the default range, we have converted this has been converted into standard normal distribution form, and each line represents a sample from your data set. Okay, so this value is, you can consider one observation which has MPG value around 2.25, which has if you trace the line, which has number of cylinder as -1.2 somewhere, which is converted because of standard normal, and then you can see these lines how they are keep on going. Okay, so right now this is not very much clear, but you can see right now looking at this AM feature. So AM feature is having essentially only two values because all your lines are merged over here. So there are only two attribute values in the dataset for AM. Similarly for gear, there are only three values over here. And similarly for number of cylinder, there are only three values in your dataset. So by looking at this, you can reduce number of features, you can change, or you can use actual range, or you can do the standard normal by changing the arguments in the plot. So you can see how your data are clustered for particular feature. Okay, so like you will look at number of cylinder, so we can directly say, okay, there are three clusters or there are three values in the data set. So right now data set is quite simple or small with 32 observations, but if it is more, so these points will become more denser. But this will help by looking at how many clusters are actually there in the data set. But looking at if you look at the GRAC, wake, QSEC, all the features, because they are almost covering all the range and there is no visible pattern over there. So you can say Geka is more scattered over here. There is no pattern visible right now if you look at this way, but if you can reduce the number of features and you will get more insights maybe. So, or by changing the order of attributes, you may get some better patterns in your data sets. Okay, so this is one visualization by looking at multiple features simultaneously, how data belongs to each and every attribute. On the similar line, another plot is called ridge line plot, which gives a ridge kind of structure. So let me run this code, which is from ggplot library and using ggridge library. So if it is not installed or if you are getting any error, you can install ggridge library and then you can use these commands. Okay, so this is how nicely looks like for empty cards. So this is how your each and every attribute is distributed. Okay, so like you can see the first one is almost like a Gaussian. Second one, there are multiple modes available. Third one is more like a skew on the left hand side. Fourth one, there are two classes available. One is very big and another very small. Then the last one is like more like a standard normal, or not standard normal, but more like a perfect normal. It's actually a Gaussian. And then you can see the ranges of the values of the spread. So like most of the values are in between 10 to 20, which are for all the features, but for some of the features, values goes beyond 20 plus, okay, or 30 plus also. So by looking at multiple things together, that will also give you more insights. Next one is bubble plot, which is representing more like a scatter plot, but it clubs actually the multiple data points which are falling in the same range. Okay, so in this one, the bigger the circle, you can see the nomenclature on the right hand side. So if values are 100 between wake and MPG, if it is values are 100 horsepower, it is represented as a small circle. If horsepower value is 300, it is represented as a bigger circle. Okay, so one is wake axis, another one is MPG axis, and then the third value, which is horsepower, third feature is represented as a different shapes of circle. Okay, so like this particular feature sample has a very small horsepower with the wake as 1.5 somewhere, or MPG value as 31 somewhere. Okay, similarly these are the two where MPG values are same, okay, but weights are slightly different and horsepower is same. So by looking at different these shapes of circles, we can also get some inferences about the data. Okay, and if you can do some more modifications by giving some more colors and all those things. So for again, for empty cars, this is miles per gallon, and then this is horsepower represented with some blue color simply. Okay, so this will give you more overlaps like this one. Then R also supports time series data. If you want to work with time series, like maybe stock exchange data, if you want to do some prediction analysis, some survival analysis, there is a package for survival. If you have some data with time dependency, so time series data can also be represented in R using ggplot library, and then you can use time series or stochastic process analysis on such data. So this is like a raw data which is just plotted, where you can see very high changes ups and downs. But this data can be cleaned and then can be applied with suitable logistic regression or linear regression accordingly by looking at those time series data. Then there is a correlation plot that can be done, which is giving correlation plots between all the features. So this is for our tree data set where it has 3 features, and each feature we can see how much correlation is existing. Okay, so like the git and git, the feature itself has a high correlation always. So all the right side diagonal will have one value over here, and then you can see right now for volume and git the correlation is 0.97, but volume and height the correlation is 0.6. Okay, and correlation between height and git is 0.52. Okay, if I change to empty cards with all the 11 features, it will looks like this one. Okay, so based on the color coding you can also see. So right now values are also displayed inside, and the color coding is given on the right side. So dark blue is towards -1, so they are negatively correlated. uh, Dark red is positively correlated data. So by default all the feature with itself will be always with positively correlated, which has value 1, and then you can see few features are highly negatively related and few are like 0. So this Q set and Q direct, this feature has a correlation value 0.09, which is very less, means they are not related or there is no correlation exists between these two. Similarly, AM and carb, this is 0.06, so which is very less in terms of the correlation coefficient. Okay, so such analysis can also help, that will help you to analyze which feature is correlated with which one, or whether there is a correlation or existence depends, or if there are any independent features or dependent features are there. So we can remove those dependent features, okay, if we get to know the relationship between them. So those kind of analysis will be more helpful if we look at the visualizations kind of techniques before going ahead with the data. Okay, so this is more about the visualization part. Uh, so if any queries before I move on to some different things. Feel free to share if there are any issues or any problem in installation at your end or running code on your side. Anyone, quick query? Okay. In case if no queries, let's move to some other parts. Okay, so let me show you some implementation of maximum likelihood estimation that you have done yesterday with Dr. Jignesh Bhatt. So who is my colleague, and uh, I hope fundamentally or theoretically you know what is maximum likelihood estimation. Okay, so I believe you are comfortable, or should I give you a quick recap? Okay, let me show his slide only. So his slides are visible.
Yeah.
Yeah, I'm sharing again. Yeah.
Okay.
I hope now it will be visible.
Yes, sir. Now it is visible.
Yeah, okay. So there are few estimation techniques that how we can estimate parameters, and maximum likelihood estimation is one of the, we can say, simplest or easiest or tractable mechanism that we can use for estimating our parameters. So what we do over here is we assume we have samples which are like x1, x2, x3, xn examples, which are our observed data or samples, and we want to estimate the parameter which maximizes the probability to have event to occur. Okay, so essentially what we do is, what is the probability that xn plus 1 observation which is going to come is very close to all our previous observations, okay, or going to follow the property which are having the property of these n observations that we have, okay. So we want to maximize such kind of observations or probability over there, okay. So for this purpose, what we do is we define for discrete data, if your data is discrete, we define joint probability mass function, joint PMF. Okay. So what is the probability of happening of event x1, x2, x3, xn? Okay. And if your data is continuous or working with continuous, so what is the joint probability density function, PDF, of happening of this event, where f represents the PDF function, which is x1, x2, xn. Okay, so we want to know that how this joint is going to take place. What are the chances that such event will take place? Okay, and this x1, x2, xn are our observed sample. Now, because this optimizing this joint probability will always be a difficult task, okay? Because we don't know most of the time in the real world also what is the generation process, okay? So what we assume is that happening of these events are independent in the nature, okay? If this joint probability is independent, then it will become a product of individual probability. Now, what we have to do is simply find out what is the probability of happening of sample xi, and then you multiply with each other. Okay, so this, instead of joint, this is going to be product of individual probabilities. Okay, and we assume over there is all the samples that are collected are independent and random in the nature. Okay, so the occurrence of one sample does not affect the occurrence of another sample anytime in the past. Okay, so what we do is, now we can maximize this product easily. Instead of maximizing this joint, we take an assumption and then we try to maximize this product probability. Okay, so what we do is, we know that if we take a log of any two quantities which are in multiplication, they will become addition in the log. Okay, so, and in the school level mathematics, what we did is, if we do the partial differentiation or first order differentiation, okay, and we play equal to 0, this will give us a maximum value. Okay, so we do just maximize the parameter like this way. Okay, so we differentiate with respect to parameter our joint function, which is now a product function, and then equate to 0. So we will get some values which is going to be maximizing the likelihood, first order differentiation. So since our probability function is now product, so what we do is we take log, so that this product becomes summation. Okay, and then when we take differentiation over here, this summation will be helping us to break down this differentiation for respective terms. Instead of taking differentiation for the product term, it will helpful for differentiating summation terms. Okay, so you can have, if there are n samples, so there will be n independent differentiations that we can do easily. Okay, so which is computationally easier to differentiate the sum. Okay, and then we equate to 0 and we can get the parameter value. Whatever is the parameter that we are looking, you can estimate the parameter. Okay, so this is the theory behind ML in a brief. Okay, so now let's see if we say our samples which we collected are following a Poisson distribution. Okay, so what is going to be the mean? So this is a PDF of Poisson distribution. Okay, where e raised to minus lambda, lambda raised to x divided by x factorial. Okay, x is your sample value and this is a PMF, sorry, PMF of Poisson distribution. Now, what will happen? We have observations x1, x2, x3, xn. Okay, so what is going to happen is you just write p of x1, which is e raised to minus lambda, lambda raised to x1 divided by x1 factorial. Then p of x2 you can explain like this one, x3, and so on. Okay, and then you take the log and then you try to maximize. Okay, now remember when you take a log, this term ln x factorial, this is going to be the constant term because we know the sample x1, sample x2, sample x3, sample xn. Okay, that will be some number, and if you take a factorial of that number, that will again a number, and then if you apply log, again it will be a number. So there is no parameter involved over here. So for Poisson, it is only one parameter, that is lambda, that we have to estimate. So this is maximizing the log likelihood of this function. Over here, if you have n observations which are following Poisson, this is going to be the equation. Now, and parameter is lambda, so we'll differentiate this equation with respect to lambda and equate to 0. So this is how we do. Okay, so with respect to lambda, this becomes minus n, and then you for ln lambda, this becomes 1 by lambda. There is no change in the summation terms, and c becomes 0 because it is a constant, and then we equate to 0. Okay, so when you simplify, you will just get lambda hat, which is estimated value will be nothing but 1 by n summation of xi, which is x bar. We call this as a sample mean that we have done in our school level mathematics. Given the sample, you just take the sum and divide by number of sample. That is a sample average or sample mean. Okay, so if we don't know for given n samples which follows a Poisson distribution, we can estimate the mean value or lambda value as x bar or as a sample mean. Okay, so those 9n samples which are given to us follows this Poisson distribution with parameter lambda hat that we can achieve. Okay, now how we can do this in R? Okay, so I'll just show you the code that how it can be done in the R. Anyone, any query on the ML estimation? Meanwhile, anyone, any query on ML estimation? How we do or what else can be done? Okay, I can see few questions. Don't know. Okay, suppose we don't have a distribution function, but we have a data. So can we find MLE? No, ideally, because what we believe is you have a large number of samples. So maybe like 1 lakh or more than that. And then what happens is you don't able to remember all the samples. what are your sample values. So we assume a distribution function so that you just have to remember a function, a small function with some parameters which are like 1, 2, 3 or very small in number, and then you can regenerate your sample as and when you require. Okay, if I know my some process which is generating a number following a normal distribution with mean 2 parameter 5. Okay, so and there are 1 lakh samples generated. Okay, so instead of remembering those 1 lakh samples, I have to remember only a distribution which is normal, parameter which is mean, which is 2, and variance which is, for example, is 5. Okay, so I have to remember only these 3 things, and I can regenerate almost similar those 1 lakh samples instead of remembering them. Okay, so that helps you to find out other properties which are theoretical properties that we can derive from those distribution functions and by looking at the data. Okay, so then you can again cross check your data by plotting, okay, what are your true samples, what are the random samples that you have generated assuming that normal distribution and these parameters. You can see how your data is away from each other, from actual observations and your generated observations. So distribution function will help you to find out more attributes. And MLE is actually based on the distribution formula that you are going to use. Otherwise, it's not applicable directly because it's just standing as a product of probabilities, and then you can't go ahead. Another question, like we don't take log likelihood function for PMF for obtaining MLE. We take a log because log preserves the properties of your function. Okay, so the maximum value will remain maximum in the log, minimum will remain the minimum. It just shrink the shape, okay, in the log function, and log will help you to do computationally easier tasks. Like optimizing a product of probabilities is difficult if, okay, so we take a log and then we convert into summation form, and then again, because we are differentiating, so the property of differentiation is you can break down the differentiation if quantities are in addition. Okay, so that will give you more tractable solutions. Tractable in the sense that you can implement, you can get the results easily, you can solve it essentially. Otherwise, you will not be able to implement them. Okay, there is a question. Rigi Core block is same as correlation matrix of Microsoft Excel software. May be same. If they are giving you the correlation value, they may be same. I'm not exactly sure about how Microsoft Excel software does. I have not used actually. You can check on the same data. You can check in R and you can check in your Excel software. Excel also have capabilities to do all such data analytics jobs now. So you can cross check if you are interested. Okay, any other query? Meanwhile, anyone? Okay, so let me show you MLS implementation in R for Poisson distribution. Okay, so this is what I have generated is, I hope this script is also available to you. Okay, if not, then after the session, I will share with you all. So this is, I am generating a variable X, which is following a Poisson distribution. Okay, and let's see the histogram. Okay, so this is a histogram of Poisson distribution. Okay, and now what we require over here is non-negative log likelihood. So negative, sorry, we require a negative log likelihood. So if you remember, this is a function that we got minus n lambda minus plus lambda summation x plus a constant function. Okay, So this is now taking a negative. So I'm creating a function which is based on the parameter LAM, okay, lambda. Then n is number of samples that we have. So I have taken n as length x. Now it is n into lambda minus sum of x values, okay, into log of lambda plus summation. So either you can ignore this term, there is no issue because it is going to be anyway constant, okay. And then we just creating a function which is we are going to inbuild our function which is NLM, okay, which is maximizing or optimization function available in R, okay. So now we are giving this one to our function which we declared non-likelihood, okay, and value as initial value is 0.5 and Hessian value which is second order derivative is true, okay. So this C.5 which is a p value which is initialization value to check where we can maximize, okay. So let me run this one, then negative function, then there are few warning that we can ignore, okay. So now this is our estimate. So out1 will have a estimated value over here, okay. We are getting a value which is 3.89331, okay. Now we have seen just to cross check that we have seen the lambda estimator is nothing but the sample mean. So I have just taken mean of x over here, okay. So now just to verify whether we are getting a correct estimate or not. So now you can see it's a change in only at the 6th place. So now this is how we can estimate ML estimation. You use negative log likelihood function, then you use non-linear minimization function NLM, which is available in R. You just pass on this non-log likelihood and with initial parameter, and you can make Hessian true, which is second order derivative. You can check over here, and then you just get the outputs. Okay. Similarly, you can do for my different distributions. So I have mentioned over here a few couple of more distributions like exponential distribution where I'm using 1,000 random samples, okay, and I'm generating those samples using REXP. So random exponential number which has number of samples as an input and the parameter. Okay, exponential distribution as a one parameter, so I'm giving its value as a 2. This is true value. And when you again do a small derivation for exponential distribution, you will get this function like this one. Okay, ignoring some constants if they are there. Okay, it's more like a Poisson distribution because they belongs to the similar family: Poisson, exponential, Gaussian, key distribution, and so on. Okay, and again I am passing as a initial value for a parameter as 0.5. Okay, remember I am giving we have given a true value as 2 over here, and this is 0.5 over here. So let's run this one. And this is now estimated value for this case. We are getting value 2.15, okay, as a parameter value, but our true parameter value is 2, which we have mentioned on line number 14. And when we solve exponential distribution for with MLE, it is parameter estimator is going to be 1 upon sample mean. Okay, so I have given on line number 18 as 1 upon sample mean over here, so which has to be same. Okay, just to cross check whether we are doing estimator correctly or not. Then the third example is using Gaussian distribution where we are generating 500 samples using R norm function, which are randomly generated with mean 2 and standard deviation 3. So these are the two parameters, and we have given the value. Okay. Now, when you solve the derivation, this will be the equation for log likelihood, ignoring some constants, and 2 stars stands for power operator, and this is a pi symbol. Okay, so this is a function that you will get while solving the equation, and then we just place it over here. Now we are estimating a parameter. So I have given over here sig value as 3 right now, which is a true parameter. Okay, so over here in this equation, pi and sig values are known, only mu value is unknown, and x is our samples. So only mu is unknown, so we'll estimate only one parameter over here, and we are initializing that parameter with 0 value. So we assume that sample mean is 0, okay, and then we have to do the estimation. Okay, now our estimate is 1.9875, okay, whereas our true mean is 2, exact 2, okay. And then for MLE for Gaussian distribution, sample mean, estimation for mean is nothing but the sample mean, okay. So if we take simple mean for our random 500 samples, it has to be same, okay. So they are very close by. If we increase our estimation, will be going towards more closer to our true mean, which is 2, okay. So this may become 1.99 if we go with 1000 samples, okay. So there are governing principles which are called law of large numbers, central limit theorem, and so on, okay. So your approximation will become more accurate. Similarly, I'm skipping one or two examples. You can relook later on. And similarly, if there are two parameters to estimate, like we are generating 5,000 samples using R norm random samples with mean value 3, standard deviation 10, okay, and then this is a function. Now over here, we are representing parameter vector. So sigma is also unknown, mean is also unknown. So we are representing parvec 2 as a sigma and then mean as 1, indexing 1. Okay. Now over here, this is negative log likelihood function, and now we initialize our parameter as 0, 1. So mean is 0 and standard deviation is 1. Okay, and then we have to estimate. Now, if you look, so this is 2.8 over here, which is a mean value that we have estimated, whereas true mean value is 3, and this is variance value. Variance is 100.96, whereas our variance is 100. So this is standard deviation, okay, and you just square standard deviation, we will get the variance, okay. And the ML estimator for mean is simple sample mean, and for variance it is simple sample variance, okay. So this is now we are getting very close, just to cross check. Okay, so this is how ML estimation can be done over here. Okay, so these are the few examples for ML estimation. Okay, anyone, any query over here?
If you have any doubts, you can raise your queries in the chat box, or you can even raise your hands so that we can unmute you.
Or before closing, let me show you one quick thing for maybe next 5 minutes. This is what you discussed with Dr. Jignesh yesterday for hypothesis testing. Okay, so you remember hopefully the two null hypothesis, alternative hypothesis, and then two-sided alternative, one-sided alternative, and so on. Okay, so for any data, if you have, so what you can do is you remember just a formula that yesterday maybe he has shared the slides with you. So for performing some confidence interval, what you can do is your sample values are 20 over here, okay, and then like if it is two-sided alternative, so you have for the level of 5% significance, okay. So and it is two-sided alternative, so what you can do is you require 0.975, quantile over here. So you use qnorm function. Okay, S is your sample variance and N is number of samples you have. So that will be the error value. Okay, and from the actual value A, this will be the plus and minus of your error. So left side and right side. So you can get the values. Okay, so this is going to be like your confidence interval for your data set. So from 4.12 to 5.87. That way you can estimate your confidence interval. Similarly, if your distribution is t-distribution, if like your number of samples are less than 30, we follow a t-distribution. And if it is again two-sided alternative, so you take 2.5 on both the sides, and degree of freedom will be n minus 1. So you can use this kind of functions and you can again get the confidence interval using t-distribution. So now over here, the interval will be from 4.06 to 5.93 over here. So this is how you can apply hypothesis testing and you can do other things. Okay, there are few more tests that not being taught yesterday also, and I'm not going much into detail, but those tests can easily be done using R. So these are called non-parametric tests. So what you discussed yesterday was parametric, where there are some parameters involved. There are few tests like sign test, Wilcoxon sign rank test, then Man-Whitney test, Kruskal-Wallis test. These all can be done from your dataset directly in R, like whether to accept a hypothesis or whether to reject your hypothesis. So based on your requirement, you can play with all this data and you can check some hypothesis parameters and all those things. Okay, so this is all from my side right now. If we have any queries, we can discuss.
Sir, I'm just going to read some questions that we have received from the participants in the chat
Okay,
box.
sure. Are there
Yes.
visible questions to me also?
Yes, sir. They will be visible to you as well in the chat if you want to read, or else I can also read
Yeah,
it.
please. If I missed out something, so let me know.
So question is, suppose we don't have distribution function, but we have data. So can we find MLE?
I think I have answered this question.
All right. So next is we don't take log likelihood
This one
function.
also I think answered. Or still there are any queries? Maybe I can see Farhan Ansari.
Yes. So you have already read these questions, and I would like to request the participants to just drop any more queries regarding the session, because you have already answered the ones that are already asked by the participants.
Yeah, I think most of the queries in the meanwhile I have answered.
Yes, sir. So there is there are many feedbacks also, sir, from the participants, and they liked your session doing our programming for the first time, but still things are clear to them.
Yeah, this is like a small session just to initiate. So if you like, then you can pursue further. This means it's a very small language, and most of the things are available. But yeah, there is a more familiarity with Python, which is well known. But still, R is used again in the data science community. So those who are willing, they can easily pursue, and it's again open source. So and lots of helps available. So we can always use R also at the same time.
Thank you so much, Dr. Ashish, for your valuable inputs, and I hope the participants are going to have a lot of insights from your session, and I just hope that if they don't pursue this language as of now, then they'll be able to use in future, as they have got the basic insights, and as we are getting the feedbacks that they found it very easy and simpler to understand.
Yeah.
Generally, it's
Okay.
not in the first session always for a programming language.
Okay. Thank you. But thanks to our community, because it's not that much difficult. So most of the things are easily available. So you just do Google search, you will get definitely some help.
Yes, sir.
And just last suggestion. So like those
Yes.
who are looking for CNN libraries and other machine learning algorithms, all such libraries are available in R. You just do a Google search. There are packages, libraries. You just call them or install them, and it will work as it is how they are working on your Python machines. So everything more or less are similar availability in R.
All right, sir. Thank you so much, sir, for
Okay,
the information, and thank you so much for delivering the session. We look forward to have you as a speaker in the upcoming sessions as well, and we'll surely approach you for the same. And I really thank you from the entire team of the FDP, ATAL FDP on data science, and thank you so much, sir, for taking out time.
Yeah, thank you everyone for inviting and have a nice session. So there are very less queries than expected.
So we are still waiting as we have some time left because the session was scheduled till 4:45 and we still have 10-12 minutes to
Yeah,
go.
okay. So I'm available.
And
Even if our
sir,
session is
you have
over.
already, yes, you
Yeah.
have already dropped your email address. That's nice. So participants can directly just drop you a mail if they want to like
Yes,
have
sir.
any kind of queries on this session. And in future also while working on art, I think they can just get back.
If any resource file which I have missed out and have discussed, if then do let me know. I will share.
All right, sir. I can't see any queries, any more queries coming out of the participants. So I think we can end this here.
Okay, yeah, sure. Thank you everyone. And in
All
case
right.
if I missed out any resource file, so then do let me know. That can be
Okay,
shared with
thank
the
you.
participants.
Yes, sir, for sure, for sure.
Yeah, sure. Okay, thank you.
All right. Thank you, sir. All right. So tomorrow is the last day of this FTP, the 5th day. And there will be a test also by the end of tomorrow's session. So we will be winding up the sessions by 4 so that we can have a MCQ test that was already communicated to you all earlier. So we'll be having a test in the evening. So see you all tomorrow. All right.